Da-da-da. the day 2 of our conference. I hope you enjoyed the first day and had a restful night. Just as yesterday, let me share with you a couple of organizational remarks. The coffee breaks and all breaks today will be held same like yesterday in front of the conference room. And for the lunch, we will go to the restaurant on the left for the new participants. During the next week, you will receive a link with all the presentation. I would also like to remind you to fill in the evaluation forms and hand it to my colleagues at the registration desk. If you have anything you would like to discuss with us, please do not hesitate to contact any of the team members. That's all from me. Enjoy the conference. And yes, Antonio, the floor is yours. Thank you.
Hello, everybody. Good morning. Welcome to the second day. I believe that yesterday we had a very interesting day, and today we are going to continue to discuss, I believe, important matters for all of us. The first speaker is Kadir. He's from Ankara Water and Sewerage Administration, and he's the Assistant Research and Development Manager. He's going to be participating online, so as usual, normally online things, they don't work as expected. So let's see if he's able to join us, and so a little bit of patience, please, to see if he can get online. Normally technology always mishap things when you need them, so is it okay? Kadir, good morning. Welcome. Thank you very much.
Good morning, everyone.
The floor is yours, Kadir.
Yes, but I want to share my presentation, but
So we will be sharing your slides, if that's okay. We have your presentation, so we can do this for you, and you will just talk.
I want to share it on my computer, not phone.
Do you see your slide?
Yes, yes.
Okay, so when you want to go to the next one, just tell us next, and we will change it.
Okay, thank you. Good morning, everyone. Again, I am Kadir Çokçevik, Assistant R&D Manager at Ankara Water. Today, I will be talking about innovative hybrid floating solar systems and their role in sustainable energy extraction. Next one. Water space offer new possibilities for renewable energy. Hybrid systems which combine solar with other technology improve the reliability and effectiveness of solar energy. This presentation will walk you the key technology and real world applications. Next one, please. ASCII at Ankara Water, we envision a future where sustainable or technology come together. Our research focus on the integrated renewables like floating solar and energy storage into municipal infrastructure. We are committed to pioneering clean energy solution for the water sector. Next one. Floating PV basics, floating photovoltaic system use platforms to support solar panels on weather bodies. The approach saves land, reduces evaporation, and can even increase efficiency thanks to cooling effects. It's an alleged example to synergy between water and energy. Next one. Combining floating solar with hydropower allows flexible energy production. Solar covers daytime loads, while hydro can be stored and used when needed, maximizing efficiency. This makes the entire system more stable and resilient. Next one. Floating PV generates power during the day and hydropower is using during the evening or peak hours. This coordination ensures energy availability today. It also allows for better interaction with grids demands. Next one. To ensure continuous power, we need storage solutions. They bridge the gap between generation and demand and make hybrid system more reliable. Storage is the key enable for true energy independence. Next one. The graphic shows daily generation profile. Usually shows how floating solar peaks during midday. Batteries and other storage fill in the during evening and night when solar generation is low. Understanding this profile helps use design smarter systems. Next one. Uh, there are various storage options, lithium-ion batteries for rapid response, flow batteries for longer durations, and hydrogen for late decade and station storage. Each has a role depending on system size and objectives. Next one. Battery systems store energy produced during the day and release it at night. They are essential for stabilizing the grid and improving energy reliability. Their modular design also makes it easy to scale. Next one. Hydrogen storage involves converting excess solar energy into hydrogen via electrolysis. It can be stored and converted back to electricity or used in industrial applications. This opens new pathways for long-term clean energy use. Next one. Electrolysis use renewable energy to split water into the hydrogen and oxygen. It's a clean process and cornerstone of green hydrogen initiatives. Advances in electrolysis technology are making this more efficient each year. Next one. Hydrogen can be used for grid balancing, industrial energy needs, or as fuel in transport and heating. It's versatile and environmental friendly. It's also offer a path to decarbonize the sector where batteries fall short. Next one. Floating solar helps reduce water evaporation, carbon emissions, and land use. It's a green technology aligned with our climate goals. Every installed system contributes to more resilient ecosystems. Next one. Cost depends on panel efficiency, plastic structures, storage technology, and grid integrations. Prices are decreasing at the technology future. We expect significant returns as economies of scale take effect. Next one. Challenges include technical integrations, operations in aquatic environments, and initial capital costs. But these are being addressed through innovation. Collaboration between public and private sector is crucial here. Next one. For success, we must meet technical feasibility, economic viability, and environmental sustainable benchmarks. Projects that excel in all their are the three game chains in the space. Next one, please. Looking at IR and digital tools will optimize hybrid system operations, making them even more efficient and responsive to real-time conditions. Smart control system will be a major driver of performance. Next one. We follow a clear roadmap, start with pilot projects, monitor results, and scale up. Data drive decisions are key to our strategy. We believe in starting small, learning fast, and growing with confidence. Awesome. That's all the small presentations. Thank you for your attentions. Hybrid floating solar systems represent and forward-thinking approach to energy. I look forward to collaborations with small stakeholder in the exiting journey. Thank you.
Thank you, Kadir, for your presentation. It was very insightful. I don't know if there are any questions from the audience. I believe that you can hear us, correct?
Yes.
Okay. Any questions from the audience? No? Kadir, thank you very, very much for your presentation, and continue with us, please. Okay? Thank you. Bye.
Thank you so much. Bye-bye.
Thank you.
So, and after Kadir presentation, we are going to have Simone Pozzini from NGR Energy to make us a presentation about the floating solar PV on dam reservoirs and solar hybridization. I believe that he's talking about something that they have done already in Brazil. I believe so. The floor is yours. Thank you.
Hello, everybody. Nice to meet you. My name is Simone Pausini, and I am the CIO of Energy Island. Energy Island is an Italian company with a team specialized in design, installation, and maintenance of floating solar solution with more than 15 years in expertise. We have designed and installed our very first floating solar installation in 2010 in Italy. And from that moment, we have started developing this solution worldwide. We currently have 3 offices in Italy, the headquarters in Milan, the technical department in Imola, close to Bologna, and the operational offices in Viareggio, in Tuscany. We basically focus our activities in developing innovative solutions applied to floating solar in order to reduce the capex cost of the plant and the operational cost of the floating solution themselves, with the objective of trying to allow floating solar to penetrate in all the global market, from the Far East to the Far West ones. In order to be able to provide our solution worldwide, we have started opening offices in the country where we are currently working. We are currently present in Europe by the Italian offices, in Turkey, in India, and in Brazil, where we have also production facilities in Brazil, Italy, and Turkey to serve the different market we work in. Today, I will present you a case study of an hybridization of an hydropower plant with floating solar. We have carried out together with Enel in Italy from 2022 to 2025, and an innovative application of the sedimentation solution applied to floating solar in hydropower plant water tanks. And after that, I will try to give you a brief analysis about the potentiality of the Brazilian market, where we are present since 2022, and that is a market with huge potentiality in terms of floating solar penetration. I don't know if you had the chance to see our product and our technology. We basically provide a floating substructor that has some advantages related mainly to the flexibility of the structures and its resistance and resilient to high environmental loads. We can grant more than 350 kilograms per square meter of buoyancy capacity. That I think it is at the top of the market compared to other solutions. And we can grant also a quite lower density of floaters under our panels that can grant a great level of oxygenation of the water under the floating PV plant. And at the same time, and high power density. We can reach up to 2 megawatt per hectare of power installed. Speaking about the key project I would try to introduce, we were involved by Enel in Italy in the construction of this hybridization solution in a city called Venaus, north than Turin, in the north part of Italy. We were involved in the design, construction, and operation of the plant since 2022. It was divided in 2 sections. The very first one of 1 megawatt peak power was completed in 2022, and the second phase added 1 megawatt more in the same location and was completed in 2025. The hybridization of hydroelectric power plants with floating solar has several advantages and of potential interest coming from the combination of these 2 power sources. Mainly, we speak about the use of the same surface available for the hydropower plant for installing floating solar, granting a reduction of the soil usage and other water basing usage. We basically can share the infrastructure, the connection infrastructure of the hydropower plant, reducing operational cost that can be shared by the two technologies. At the same time, installing floating solar inside of the reservoirs of the hydro, reducing water evaporation, so losses of water for evaporation, can grant to preserve water that is crucial for hydro generation, especially in country where water is scarce, is not abundant. The production of energy between the two different sources combined could grant advantages in terms of balancing of the energy production. Those two sources are normally complementary. Solar produced when hydro could be shut down, even on a daily basis and on a seasonal one. So, for example, in summer or winter, we have different peak of production of the two sources. The production of floating solar can be used to implement and power pumping system for hydrokinetic storage system tied up with the hydropower plants. And at the same time, the integration of those two energy production system can grant an increase of stability of the grid. Because the hydro can reduce the curtailment effect of solar, and at the same time, floating solar can boost the production and the connection in the grid of the energy produced by hydroelectric plant by having an increase in the energy output compared by the two sources taken separately. We had the chance by designing and building these very first experience for Enel and for us on the Italian market of an hybridization between solar and hydro to try to introduce a new kind of innovation in the management of the hydro dams and hydropower plants, mainly related to the management of the sediment. Sediment, as you may probably know, are one of the main problems related to the operation and lifespan of hydropower plants because they accumulate on the water basin bottom. They have to be disposed. They can stop and clog the pipes that collect water to the hydro turbines. And the chance of having the sedimentation solution applied to floating solar inside of a water basin reserved for hydropower plant gave us the chance of implementing a fully autonomous desedimentation system made by two main components. The first one, the agitators placed under the floating solar platform. Those are mainly fans or pumps that are installed on the frame that support the panels and helps to create a slow current, a flow under the platform that keeping in movement the sediment, avoid their deposit on the bottom of the basin, pushing and driving them to the collection pipes where they can be disposed without the need of emptying the basin continuously to remove mechanically the sediment. And at the same time, the combination of this system to a dredge raft, that is basically a floating pump, can be used to remove the sediment outside of the surface occupied by the floating solar. That pump was designed to be fully autonomously. It can identify sediments and it can extract them by pumping inside of pipes and collecting them and pushing them to the exhaust pipe outside the basin or where they can be disposed by avoiding the needs of stopping the hydropower plants. That plant would be is under construction at the moment. It will be completed in June 2025 and will start its operation in September 2025 to complete the desedimentation phase of the pond where the Venaus 1 and 2 power plant has been installed in 2022 and 2025. The main benefit of this kind of application comes from the combination of the desedimentation system and the floating solar that can, from one side, power all the pumps and turbines used to move the sediment and extract them by the energy produced by floating solar. Floating solar itself can help to reduce the formation of algae that are one of the main sources of sediment present on the basin. And at the same time, installing the desedimentation system on the floating solar, we basically give accessibility to all the surface of the water basin because the floating solar lay down on the surface of the basin itself, giving advantages in terms of maintenance of the pond and the hydroelectric dam itself. Coming to the Brazilian market, we are present there since 2022. Brazil is a country that has huge potential in development of renewable energy installation. That chance comes from a law that was promoted in 2012 from ANEEL, that is called distributed generation, that basically give a chance to the energy producers to obtain credit for the energy fed into the grid and use those credits far from where they are produced by reducing the cost of energy taken from the grid. Initially, that chance was reserved to power plants with a peak power lower than 5 megawatt. And that has reduced a lot the potentiality of the market. Since 2022, with a new law from ANEEL, it was introduced the chance for floating solar only to request the authorization for connection and participating to the distributed generation for larger installation larger than 5 megawatt by dividing them in connection multiple of 5 megawatt. So it means that a 10 megawatt installation of floating solar could be connected to the grid and could access to the distributed generation by dividing it in two connections of 5 megawatt each, or the same for 100 megawatt, 150, 200 megawatt. That was reduced in 2022 in roughly 2 gigawatt of requests of authorization for the connection on the Brazilian market for floating solar. That is starting to be built. It has started in 2023, 2024, and will reach its peak, we think, in 2026 and 2027, due to the time of gaining the environmental authorization, civil authorization, etc. We have opened an office in São Paulo in 2022 to follow this market. We have opened a production facility there for producing the floaters and the frames that compose our system. And we have already started the first installation. We have roughly, at the moment, 5 megawatt installed, divided in 1 megawatt PV plant from São Paulo to Rio de Janeiro. And we have under development at the moment roughly 150 megawatt. So we really believe that Brazil for floating solar had huge potential that will be expressed in the next 2 years. That was all from my side. Thank you for your attention.
Thank you, Simon, for your presentation. I don't know if there are any questions from the audience.
Good morning. Thanks for the presentation. Very interesting. I have a question regarding your project in Italy, and I was wondering if with the agitator you have installed at the edge of the PV plant, you will still need to dredge below the PV plant at some times during the operation.
Well, normally no. The objective of installing these kind of agitators was precisely to avoid the need of going under the PV plant to remove sediment. The sedimentation system will start its operation in September 2025. So we will have the result of this application in the first year of operation. So we will be sure that no sediment will concentrate under the PV plant only after, I think, 1 year long test.
Okay, so this kind of agitator is not yet proven, but it will be.
They have been proven not in floating solar application, but in wastewater treatment basin, for example, or pond used for agriculture. So we have, there is expertise on the market in using this kind of system for preventing sediment to be deposited on the bottom of the basin, but not applied to floating solar. So the specific result we are expecting to be collected in the first year of operation.
Okay, thanks.
We have another one.
I have a follow-up question on that. Do you have a rough estimate on how much percentage of the energy yield will be used for the sedimentation or sediment extraction?
Well, the agitators used on the island, on the 2 megawatt island of Venaus, that is the pilot project, have a power consumption of roughly 20 kilowatt peak. For the dredged raft, instead, we have roughly 40 kilowatt of peak absorption.
Okay.
So it is a fraction of the energy produced.
Do you have a rough estimate on how much higher the LCOE will be?
Not yet, because depending on the kind of sediment present on the basin, the quantity of them, we would need different amount of time of operation of the dredged and of the agitators. The agitators were thought to operate during all the lifespan of the plant, so they will be switched on while the plant is installed, and they will be switched off only for maintenance or for the disposal of the plant, but the consumption is really low compared to the production capacity of the plant. For the dredged raft, that is a punctual use of the sedimentation solution. So once the sediment have been removed outside of the PV plant, it will be stopped and not used anymore.
Thank you.
Hi, morning. Morning. I have two questions. One is, what is the source of consumption for the dredger? Is it you use the solar, floating solar as your source to operate the dredging machines?
Yep.
Okay. Another one is, I noticed that you mentioned your floater have a higher capacity in terms of floating mechanism. What is the factor that contribute to that? Is it because you made it thicker, or you have a different material, or is HDP, but maybe in between you have foam? So what are the things that contribute to have that kind of a floater?
You mean the floating capacity?
Yep.
Yeah, if I understood correctly, and the question is about how we can reach this floating capacity, we basically use HDP floats that are very thick, so roughly 1 centimeter of HDP on the border of the float. They are produced by a blow molding technology, and we have those cubes that have a volume of 175 liters. And we use as many floaters as needed to match the buoyancy capacity specifically need for the installation in terms of wind resistance, wave resistance, snow load resistance, or also the chance of making the pontoons not only walkable, but they can be crossed by small trucks or car in order to do maintenance on the plant. So we can add as many floaters as needed to match the necessity of the specific installation we design and build.
Thank you.
Thank you.
Any more questions? If not, I will have one, a tricky one. And tricky because on a certain way, your presentation is connected with the one from Fabrizio yesterday in the morning. And from what we saw, they had the need to clean the basin where the plant is installed, and the second part of your plant was built on ground, let's say that way. My question is related to, let's say, the interconnection of all the activities. Because I believe that floating solar also can have a positive impact, not only directly, but indirectly. So, meaning that if they have the need to clean the basin itself, the system that you are mounting and testing now can be a huge positive impact in terms of not having to clean the basin itself. Are there any calculations of, for example, what would be the positive impact in terms of carbon emissions that are, let's say, that are not used or that will not be released to the air because of your system being installed? Are there any kind of environmental impact behind study impact behind the system itself?
Yes, I don't have numerical values to present, but the reduction of the environmental impact, if this system works properly, is really huge, because the amount of sediment that are depositing on the hydropower plant dams worldwide are really huge. We are speaking about 100,000 of cubic meters of sediment every year deposited in every dam. And normally those sediment have to be mechanically removed and disposed in landfill or other places, and they have to be transported, they have to be moved, they have to be placed there. So the chance of not having the sediment, that means that the sediment would be collected into the rivers where they normally have their lifespan and goes to the sea and to the seabed of the river themselves, will really have a great impact in the reduction of the environmental cost of this kind of solution. And for the test bed of Venaus, we have specifically divided the pond in two areas. In the first one, where the plant has been installed, we have mechanically removed the sediment in order to prepare the bottom of the basin to analyze the contribute of the agitators. And we have left all the right part of the pond where the floating PV plant is not present with the sediment. And that's the area where the sedimentation crane, the dredge pump, will work in order to dispose the sediment. So we will have present in this dam all the condition that allows us to test the efficiency of the system and its potential value.
Thank you very much. Any other questions from the audience? Thank you very much, Simon. Thank you. So, and after Simon, we are going to have a presentation from Thomas Meyer, Senior Project Manager of Fichtner, that is going to talk to about a full floating PV hybridization potential. So, floor is yours. Thank you very much.
So, good morning, everyone. Welcome to my presentation. So today I'll talk to you about the approach for full floating PV hybridization potential at new or refurbished hydropower plants. So the agenda is quite full, so I want to jump right into it. So part of the agenda will be a presentation of 3 different tools that we developed at Fichtner, which are an integral part of the steps towards full hybridization. So quick word to Fichtner. So Fichtner is Germany's leading independent firm of consulting engineers. We're family owned and at the market for more than 100 years. We are basically supporting our clients worldwide in all project stages that you can think of, from initial project ideas to studies, tendering, implementation, and support during operation and maintenance of the projects. So it can be the owner's engineering jobs, or, for example, lenders, technical advisors. So what is the motivation or the background for us to for this topic? So basically, we want to unlock the great potential worldwide for full hybridization of floating PV at hydropower plants. And basically, the motivation for let's say developing this approach came from two projects which we had in Africa. One example is in Zambia, where the hydropower plant was basically very old. It's already running for 80 years, which is somehow impressive. But of course, there was some limitations on the infrastructure there. Very old SCADA and the general INC infrastructure. Yeah, so basically lack of control possibilities, and overall a full hybridization approach was just not possible. There was, let's say, some of the benefits that were mentioned before, like seasonal water topics that could be done, but others not. Another example is a project in Mozambique, where there were refurbishments done, but still, let's say, the overall environment would not allow for full hybridization, even though the location has a great potential for floating PV. So this was, for example, due to constraints from the grid connection point of view, but as well impacts from the grid code, which require additional investment in BESS. And on top of that, existing PPAs that would hinder somehow flexibility in changing the overall approach of operating the plants. Now we want to focus on a few ways to overcome such key issues, and this has to do with flexibilization of hydropower turbines, hybridization modeling, and forecasting. So the topic is about new or refurbished hydropower plants. So if you look into new locations, you may have the question basically where to start. And for this, Fichtner developed a tool which was used, for example, in one of our projects in Germany, where we did a study in one of the 16 federal states to identify locations for pump storage. And so this is a GIS-based tool. And as you can see on the map, even in a very small area here to see, this is like 10 kilometers, quite a few locations were identified with upper and lower reservoirs. And so this shows a great potential. And I'm sure that we'll need more pump storage in the future. And so obviously this mainly is driven from the hydropower side, and you see a capacity potential of 450 megawatts for this one location. But on top of that, you have some reservoirs, some surfaces where you can build some floating PV on, and hopefully we'll manage to get improvements in German legislation that we can use more of the surface. But yeah, let's see how that develops. So once you have identified a new site or you have an existing site, there is obviously the need for optimization so that the systems would fit together. And for this, we have developed another tool, the Fichtner Hybrid Configurator, which is not only, let's say, developed for PV plus hydro, but it can basically handle all kinds of sources for optimization, being it wind, batteries, diesel, gas-fired power plants, hydropower, whatever. And so in the context of floating PV with hydropower, we can obviously optimize on the utilization of the grid infrastructure, taking into account line saturations at the HV level. smoothing seasonal variations, better fulfillment of peak demand, and especially, so this, let's say, one example up here. So we see, for example, the dependencies of load coverage depending on the PV size and the dam height, or let's say any other combination of parameters that we would assess. It's basically looking into technical aspects that from a design perspective that have to be optimized, but obviously it takes into account financial parameters as well. So optimization towards LCOE, NPV, IRR, you name it, depending on the requirements of the clients. The optimization is done as well, as can be seen up here, to optimize, for example, daily patterns, but as well seasonal aspects. Usually the simulations are run in hourly time steps, but if need be, we can go down to 1 minute resolution to optimize in a very detailed way. But we do not want to stop at, let's say, the overall design optimization. And this is then the third tool that I want to present. So the colleagues from the hydropower department have developed a tool over the past 30 years, which they apply basically in every hydropower project, where they can optimize the overall design of the hydropower plant. Besides the many aspects that have to be, let's say, addressed from a hydropower perspective, I will leave these aside a bit. The focus I want to put on is on the turbine types, because we think that if we are able to have a more flexible approach in the use of the turbines, we can get to a smoother and easier operation of the hydropower and floating PV hybrid systems. So basically, with this tool, you want to assess technical and financial aspects, and you want to ensure an efficient system. And so basically, one key aspect is to do sensitivities. So what we want to achieve is that we have more flexibility in the system. That is a bit more turbines, but smaller, so that they can operate more flexible, more in nominal conditions, less in part load conditions, while keeping the same LCOE level. So if you want to have way more information about this, I'm happy to contact you with our hydropower experts that can dive in very deeply into that. I will leave it at this level, just to showcase the possibilities here. So now we talked a lot about this design aspects. So what is needed for a good hybridization that it fits well together. But one important aspect in our view is, let's say, having already an eye on operation. And we see intermittency as a very important aspect that is usually addressed in all PV projects. I've seen less focus on this for the floating, but still we deem it quite important, especially when it comes to the full hybridization. So to give you a bit a flavor of what to expect. So this is real plant data from a roughly 100 megawatt plant in Africa. So not floating, pure PV, but for the intermittency, it doesn't matter. So you see that, for example, if we look at 5-minute intervals, you will have almost 3,000 events in a year where we have a 10% change in power. So that is quite often, actually. And if you go to different time intervals, you will see that the maximum changes are different. So we have like if you look at a 1 minute interval, we have 20% maximum changes observed in 1 minute. In 5 minutes, it's already 50%, and in 15 minutes, changes, that's usually drops, but can happen in the range of 80%. So this is data for a big plant. So if you imagine a smaller plant where you have dense clouds moving, this drop can even be way more significant. And as you can see on this graph here, you see that these times where intermittency can occur is basically distributed all over the day. So it's not that you have, let's say, only, at least in this location, a certain time gap, and say always in the early or late afternoons where you say, oh, now I need to be a bit careful, but this really happens throughout the day. And obviously, these are the, let's say, the percentage changes. Obviously, let's say from a megawatt perspective, the drop can be most significant during noon hours, where the PV is generating most. Taking this into account, we see this 30-minute time horizon as very important to understand what will happen and what the hydropower plant somehow needs to compensate when certain clouds come in. And therefore, I want to give you a, let's say, insight bit on this forecasting approaches and different possibilities that are typically there on the market. So we have the long-term forecasting, which is numeric weather prediction. So it has a typical forecasting horizon of 6 hours to 14 days. Obviously not very precise, but it's really about the long term. You have midterm forecasting, which is based on satellite imagery analysis, which is usually between 30 minutes and 6 hours. And then we have the short-term or very short-term forecasting, which is then for the next 30 minutes. This 30 minutes forecasting requires on-site cameras, which can be either optical lenses or infrared cameras. And they have a update frequency of 1 minute and a temporal resolution of 1 minute. So you kind of really understand what will happen in the next 30 minutes. So if we look at these different possibilities, we see that only with on-site cameras, we really have the possibility to see what will happen in the next 30 minutes. And this we see as very important then for the smooth operation, because you can already start up the turbines, have them ready for synchronization to not have any jumps in the operation. So that the camera itself basically is forecasting irradiation, but all the systems nowadays offer as well this kind of machine learning features to translate this forecasting of irradiation into generation, like energy. And it typically over the course of 1 year, the system knows quite well how the PV operates under certain conditions. So the forecasting gets even better for the energy forecast. And yeah, this is again very helpful then for the operation. One quick aspect about BESS, because this was, let's say, one of the, for example, the requirements that we have seen in the grid code in Mozambique, but this was often mentioned as well in conjunction with PV projects in general. You obviously BESS can be of great help, and it's not that we don't want to have it. Actually, my colleagues from the BESS department would be very eager for me to support it. But we just need to see where it's suitable and reasonable to have it. And the BESS will just be able to passively react on what happens. So it's not able to somehow predict anything. You need the forecasting for it. And maybe there is not the chance to completely avoid BESS if there's need for it. For sure, it should be integrated, but maybe it can reduce even because we did a quick, let's say, analysis on cost, and we've seen if we have, for example, a very short-term forecasting compared to a BESS system, and this is even without exchanging the BESS over time. So this is assume that they really can stand the 20 years life cycle. Then we would be in a range of 10 to 15% of the BESS cost for forecasting, and therefore, already paving the way to a good hybridization approach. So I'll come to my conclusions. So there are a few steps to unlock this new potential for full hybridization. So first, if you do not have a site, there are ways to find one, especially for pump storage. If you have new sites, obviously the optimization potential is very big because you're absolutely free, not absolutely, relatively free to optimize in different ways, like the dam height, discharge rates, the capacity ratios between floating PV and hydropower. And with the hybrid configurator that we have developed, we can do a lot of good simulations there to come to commercially attractive projects. For the full hybridization, we have a few steps that we think are needed. So there's the sizing of the hydropower turbines is essential. Then as well, the inclusion of short-term forecasting we deem very important. And then obviously the later on, let's say, the technical details about a dedicated control system for the entire plant and not for its pieces. So this is, let's say, the key takeaways for the technical part. Nevertheless, I want to mention as well one part which we identified to be important likewise, which is a proactive stakeholder engagement. So we need to talk to the energy off-takers, understanding potential PPA constraints. We need to talk to the grid operators, addressing their concerns, because sometimes it's just really concerns that they have for hybridization. And dedicated grid impact studies or workshops with them can help to reduce these concerns. And last but not least, as well, talking to the people on the ground, so that they're the ones that operate the things at the end. And if we get them motivated to have hybrid plants and having them excited about these opportunities, then I think it's a good step that we can take. Thank you.
Thank you very much, Thomas. I don't know if there are any questions from the audience. No? Oh, yes, there is one. I leave mine to the end, okay?
Thanks, Thomas, for the presentation. So from your presentation, I understand that you have already made or studied at least hybridization between PV or floating PV and power plant. So it means that there are, on this kind of project, there are two systems, two equipments, one that is a dam, one that is the solar plant. I'm wondering if you have faced, or if generally it's how the ownership of those projects that you have faced is made. Like, is it one owner for the power plant, one owner for the PV plant, or if it's two owners, how the priorities are made for production and yeah.
Thanks for the question. So far, it's mostly that the owner of the hydropower plant would somehow want to expand with solar, if it's possible with floating. But we have had as well the examples like in Zambia, where in the end the project was co-located on ground. So it's usually the same owners, but still, let's say the owner of the asset is not necessarily the owner of the grid. And this is where the complexity comes in, that you still have to talk to the grid operator and get the okay for the grid connection and the requirements and yeah, so that's where additional challenges can come from.
Okay, thanks.
Thanks. So I'm very interested in the rapid response to the fluctuating power from the solar plant. It seems to me, as I understand it, in your use case, you have a solar producer and a hydropower producer emitting power, evacuating power onto the grid as a combination, and you're trying to make sure that that power level is stable. My separate question would be is, let's say you use that floating power to pump up the pumped hydro. How significant is this fluctuation in power that you're giving to the pumps, turbines? And to what extent will the battery smooth out those fluctuations automatically?
So maybe the first question, it depends basically on the grid. So if you have already a saturated grid or close to saturation line, you obviously have to keep more or less the level if you do not want to go into a massive grid expansion, which is costly and typically a lengthy process. So it depends. So if there are grid limitations, then of course you need to balance more. If not, then there is still room in the HV line, then you can obviously be a bit more flexible and somehow not fully cut the PV curve somehow, but yeah, have an additional generation profile. And the second question about the intermittency for the pump storage, yes, I would see at least some portion of BESS helpful to not have, let's say, a lot of very small fluctuations. But again, with the let's say this intermittency, depending on the location where you are, it can be that you have, let's say, 300 stable days per year, and then you just need to be a bit more cautious on these other days. But it can be other locations where it's very frequent to have these solid cloud formations, for example, in early afternoons where these clouds would form. And if you're closer to an island location, then you typically have stronger winds, so the clouds are passing faster. So let's say the peaks are more severe. Then it will often obviously have a more higher impact. So you would need to take that into account, but it's very, very site dependent, I would say.
But just to clarify, so the concern is, to what extent are you delivering a stable set of watts to the pumps? It's not, you're not concerned about stability of if you're just feeding that power into the grid using the transmission of the dam. You're concerned about the stability of the supply to the pumps. Is that correct?
Yeah, again, it depends on the project setup. I mean, I would not say that the PV generation would be only used for the pumps directly. So it could be some kind of a combination. So you would not be fully dependent on the profile.
We have another question over there.
Yeah, thank you. Thank you for the presentation. Similar to what you were explaining, in my mind, hydro is like a huge power generation compared with floating. And this, maybe your use case is different. You are pointing to Africa, smaller areas, smaller projects. So why this fine tuning of synchronization and so on? That's my general question about this, because usually I will think of, well, the storage should be like covering these fluctuations of solar. So this fine tuning on solar with hydro, that's why I am a little bit confused. So
Yeah, good question. So obviously it depends on let's say the different sizes of hydropower and PV. So if we have like a 500 megawatt or bigger hydropower plant, and you put like a 3 megawatt floating, nothing happens basically. If it's the other way around, like this smaller project which we have seen in Africa, like for the location in Zambia, it's a 22 or 18 megawatt hydro power plant, but we added a 20 megawatt PV. So that's completely different. And then,
That's making sense. Yeah.
yeah.
We have another question over there.
Thank you for the presentation. One specific question about your modeling software. Do I get it right that this is based on the production assets, but it doesn't take into account any element related from the grid side, like evolutions on ancillary services, day ahead, imbalance, these kind of things? Or is that taken into account in the sizing factor of your PV system, for example? Because it can have a massive impact.
Yep. So the tool is just a generic tool that we developed. So I guess you're referring to the hybrid configurator.
Yes.
So it for projects in which we involve batteries and where this topic about different ancillary services is necessary, we can include this, and as well include certain grid constraints aspects into the modeling, so that is possible. So we can do that in case need.
Thanks.
Any more questions? Okay, so I will have one, Thomas, if you don't mind. The management system, because it's in fact a prediction and the management system that you have for this hybridization, and continuing, let's say, in the same way of on the same path of the questions asked before, how can it be integrated with all the ecosystem of the grid, consumption, everything? What I mean by that is that you have a prediction of the production. I believe that you can manage internally to select the source of the energy that you are producing at any time, or if you are going to use pumping, for example, to use the excess of energy production. But can you integrate it with the grid software, with grid management and so on, or it stays only in the part of internal management and prediction?
Well, we have observed, let's say, for at least in the large scale PV projects, that there's a lot of requirements for forecasting from the utilities just to plan their system. And there is then obviously the system is fully integrated so that the grid operators can, let's say, reliably see that information and all the updates of the forecasting, because let's say this update frequency depends on the way you do the forecasting. For the operators, that's why we emphasize on this early stage hybridization thought. It's necessary to think these two things from the very beginning, and then it can be fully integrated, and then we'll really have the chance to unlock this potential. Otherwise, it's a lot of bits and pieces that you try to put together, and it's a lot more complicated and probably not really working well.
That was the sense of my question.
Yeah.
Thank you very much, Thomas. It was an excellent presentation. So, and now we will continue with Pankaj Kumar, that he's going to make he's director of the Quant Solar, and he's going to make a presentation about Quantum Solar hybridization projects.
Okay, a very good morning to everyone, all the esteemed audience here. I'm very glad to be here on this forum and talk about our learnings, our experiences in the past 8 to 9 years working on the floating solar domain. As we all know, since yesterday, so many presentations have already happened and everybody has talked about the impact floating solar is making across the world now. And all the policymakers are very much ready to accept this kind of technology in a big scale. It is already happening in Europe. It is already happening in Asia. India is also one of the place where a lot of projects are building up now. And in the past 7 to 8 years, almost 40 projects have already happened there. So our company is based in India, and we started in 2016. And we started working on the floating solar technology, development of design, engineering, execution of the projects. So today I'll be talking about our learning, our experiences from one of the projects, one of the recent most projects that we have done, and that was in a pump storage dam. It is the first project in India that has happened on a pump storage dam. So I'll be talking about it. So to start with, okay. So just a brief introduction about our company. So our company, Quant Solar, was established in 2016, and both the co-founders, myself and Siddhant Agarwal, we both are naval architects. So we worked extensively in offshore industry for almost 15 years globally, working on all kind of offshore platforms, ships and everything. So with that background, when we started working on the floating solar, we had the sense of the design elements which we implement in the marine offshore engineering. And with that background, when we started developing, so in the beginning, there was no standards. When we talk about 2017 or 18, there was no standards, very little standard available in floating solar. But step by step, when we started building it up, a lot of experiences, a lot of learnings, we got a lot of insights. And today, where we stand, we have executed almost 25 projects across India, cumulatively around 140, 150 megawatt of projects. And we believe that this is just the beginning, because now with so many projects executed, government has got so much of confidence that it could be a very good alternative source of power. Rather than doing it on the ground, you can do it on the water bodies. And most of the countries are all abundant, having abundant water bodies. So that is helping to this idea. And we are dedicated to floating solar, and we are doing on the pre-feasibility study. We are working on the EPC projects. We are also into the manufacturing, present capacity around 250 megawatt. And that's how we are building up. So just a couple of accomplishments which we had. We got the chance to do India's first megawatt scale project in 2018. And subsequently, we also got a chance to work with DNV Netherlands, working on the recommended practices. That was a very good learning, and working on the real-time challenges which was being faced across the industry. We also worked on a high altitude project where the project was, the plant was laden with snow for almost 2 months. So that also, we got a chance to understand that what are the challenges and how to overcome those challenges. And recent most is the 12 megawatt project that we did on a pump storage dam, where the water level variation was almost 16 to 18 meters every single day. So that was an experience of its kind. So I'll be sharing all those experience and learnings. So to start with, let's talk about the challenges that is offered by different types of water bodies. Water bodies can be of any type. It can be artificial reservoir, it can be open dams, it can be catchment areas, it can be industrial water bodies. And different water bodies, in our experience, different water bodies offer different challenges. For example, if we talk about, say, industrial water bodies, there are a lot of issues related to the bunds. Somewhere we get a chance to do the anchoring on the bunds, somewhere we don't get a chance to do the anchoring on the bunds. Somewhere we are allowed to do the anchoring on the waterbed, somewhere we are not allowed to do that. So we have to have a mix of anchoring systems. Somewhere we have to use the dead block, somewhere we have to use the screw piling or plate piling, plate anchoring. So that way we have to identify the real challenge on the ground, and accordingly we have to take the steps. Again, if we talk about the open dam, in open dam, somewhere the waterbed is rocky. So you have to identify the exact footprint where you are going to bring your entire plant and you are going to put your anchoring points. Somewhere the mud level is very high in the waterbed, so you have to understand that what's going to work there. And so it's very varied. So every project is customized. Every project is one of its kind. Again, aquatic life is another area which is a big concern for many of the water bodies. And for example, somewhere we're doing a project in a aquatic where it was used for the drinking water. So the drinking water safety is very important. Your entire plant should not affect the water quality in any way. So you have to do a lot of testings to ensure that it is not getting affected. Again, there are a lot of places where we had the challenges of aquatic life. It was alligators and all were there. So it was a lot of challenges to ensure that the project is being executed safely. And there are a lot of places where we had to abandon the idea of doing the project at all because it was not safe at all. So this is about the challenges which are offered. So again, when the challenges are there, we also have to ensure that how to overcome those challenges. So we believe that anchoring and mooring is one of the areas which is one of the most critical in ensuring the sustainability of a project. And especially when you are doing a project where the water level variation is very, very high, say 10, 15 meter, 20 meter, now even very high. Yesterday he talked about 55 meter, that's too much. So, so we are pushing the boundaries. We are pushing the boundaries and that is good actually. That's how the technology evolves. So uneven bathymetry is another area which offers huge challenge. You have to decide what are the contours, where you have to position your footprint. Sometimes it has to be close to the evacuation point. Sometimes it has to be away from the evacuation point. So you have to weigh all the options, optimize the project cost. So there, CapEx management plays a very crucial role, that how are you optimizing the entire project. Somewhere again, you have the access to the waterbed where you can do the anchoring. Somewhere we are not allowed to do the anchoring. So accordingly, you have to have a mix and match of multiple anchoring systems. Even within the anchoring system also, suppose the anchoring line which runs, like in the recent MOST project, we used a combination of polyester and steel wire to ensure that the elastic properties support the movement of the plant under different water level variation. So, and soil condition is another area which plays a very significant role in the ensuring the anchoring and mooring. So we have to look on all the options, possible options. So again, innovation plays, I don't need to talk much about it because we all are here talking about so many new ideas, so many developments which is taking place. So we also believe on few points. One of the point is that if we have the mooring layout that is adaptive to the environment, to the local water body, it takes care of much of the problems, and that is very important. Again, when we talk about the floaters, floaters have to be smart so that you bring down the transportation cost, you ensure the fast connections to minimize the timeline of the project execution, and it should have sufficient buoyancy, because as what we are seeing in the past 2-3 years, there is a huge advancement in the PV modules. The capacity of the PV modules, I'm starting from 250 watt peak way back 8 years ago. Now we are talking about 700 watt peak modules. So your floating system should have that kind of buoyancy and strength to ensure that it can sustain even 700 or even 800 in the future to support that kind of structure. And that structure had to sustain in all kinds of weather conditions for years and years. And in the recent times, we have seen that under the impact of climate change, the weather conditions have become very erratic. So whatever we predict, the real scenario is very different from whatever we predict. And that offers another set of challenge. So you have to have a buffer. Everywhere you have to have a factor of safety to ensure that in case of very unforeseen circumstances, the engineering is taken care of. And again, there is a option. You have to weigh the options that what is the cost impact of it. So all these things play a very crucial role. We believe that there is one important area is about the wave barriers, especially very high wind and wave conditions. You have to have a very good wave barrier system to minimize the impact of the waves and wind on the floating structures. That is another area. Then now, since yesterday, we have seen that so many new material or combination of material is being utilized for development of this floating technology. I think that is another area which demands a lot of efforts in the coming time. And we have to monitor stress, tilt, mooring loads, all this on a very real-time basis. So if we can have embedded sensors and all in the future, maybe that can help. Yesterday, you were talking about that. So I think that is the idea which is very, that is very, very important actually. So we need to continuously, we all have to work continuously on that. So now I'll be talking about this 12 megawatt project, the challenges that we faced and how we overcome those challenges. So this project it's a pump storage dam in the eastern part of India. The name of the place is Purulia, and it's the first PSP dam of India where the floating solar project has been commissioned. And here we have a maximum fluctuation of 22 meters, and with a 516 meter maximum water level and a 494 meter minimum water level. So here we developed 2 islands, 6 megawatt each, and that was the dimensions 274, 139 kind of dimensions we had to have. And the mooring lines was 91 lines we had per island. And again, as I mentioned earlier, that to have a combination of polyester and steel wires to ensure the proper load sharing and maintaining the elastic property as well, to ensure that in case of uneven loads coming on the plant, it is taken care of. And the design wind load that was on this project around 363 kilonewtons at 90 degree. That was what considered with a factor of safety of 2. The challenge, one of the biggest challenge that we faced in this project was there were 4 pumps for the pump storage dam. There were 4 pumps, each with a capacity of 160 cubic meter per second. So when it was bringing the water on the upper dam, there was so much turbidity. So it was affecting the flow of water all the time. So whatever you had to do, be it the launching of the platform, the launching the solar plant, or the installation of the anchoring points, every time it was playing a very crucial role. So we had to take care of that impact on the flow of water all the time. And again, there was a requirement of a slack behavior or a tension behavior in the mooring line all the time, because every day there was a variation of water level. So we had to ensure that thing. And we had to also keep the mooring line angle less than 30 degrees to minimize the vertical load coming on the anchoring points. And we used a mix of polyester and steel. That was the innovation that we did to ensure that there's a proper stress sharing amongst the anchoring lines. And high wind and wave exposure was always there all the time. And to add to that, there was a turbidity from the pumps. And and because the water level every day it was rising, that much. So we had a very squeezed window period actually, within which we had to do the installation. And that was the big challenge, because otherwise, what happens that in any water body, we have a team, we have the plan, starting from morning to evening, we do the works, and that's how we execute the projects. But here, the challenge was that when you start, where you start, after 2 hours or 3 hours, everything is very different. So, you had to have proper real-time planning all the time, proper coordination between the ground team and the floating team to ensure that every action is taken care safely and properly. We did a lot of analysis as well under various water level conditions to ensure that how to bring down the dead blocks in the water, how to have the proper anchoring length on the barge. All these things we took care of. There's just a representative picture to show that how the under the slack condition and under the for the different water level, the highest water level and the lowest water level, how the behavior of the mooring line is there. So now, just there are 5-6 points which I would like to share with you. That is the main challenge that we faced, and then how we overcome those challenges. So one was that the distance from the shore to the final point was 600 meters. And that 600 meters, the towing the small islands, launching from the launching pad to the final destination. So it needed a very careful scheduling. That was very important. Careful scheduling so that each of the small island, each of the strip of the plant can be brought to the final location very safely without getting affected by any of the conditions, the local conditions. That was one. Second was about the anchoring. So anchoring, again, the water flow, the inflow and outflow force was huge, and the turbidity of the pumps was adding to the problem. So we had to ensure that the entire operation of anchoring is done, because the precise location of the anchoring points as per the GPS was very important, and that's why all the points were marked before bringing it to the final destination, and then entire movement was planned accordingly. Again, because we are carrying the crane barge to do all the dead block, putting the dead blocks in the different locations. So we had to have a kind of a rope system which we used to ensure that we could resist the flow of water. That was very important, because where you start from and where you end up was different within 1 hour, within every half an hour. So we have to ensure that we are on the right point and going through the right route. So all these things were addressed using some innovations. Again, weather-based work planning was very crucial. We implemented a flexible execution plan to adjust all the activities, be it the launching or the anchoring or the towing of the small strips to the final location. Then team coordination was, of course, very important. It is very important for all the projects. But here also, because the water level was varying, so we had to have a very seamless coordination between the ground team and the floating team. And that's how we could manage to overcome those challenges. And again, safety and structural integrity was another important area, because every strip, when you launch in the water, that time it is the most vulnerable condition. Unless you don't bring it to the final location and you connect with the anchoring point, till that point it is very vulnerable. So you have to ensure that each strip goes from the launching point to the final destination in a very safe manner under all circumstances. So that was the most challenging part, and we had to ensure that, again, the safety protocols and all we had to take care of. We had to ensure that every time, every single hour, all those safety protocols are followed, so that there is no lapse on any front, because you have to save the equipment, save the personals on the ground. And that's how we managed to pull this project. So you'll be glad to know that this project was commissioned 2 months back, and now the monsoon will be starting very soon, so we'll be facing the first phase of that and see that how it goes. But we are very confident that the way it has been executed, we strongly believe that all the factor of safety that we have taken, we believe that it's going to be one of the role model project, and that will pave the way. Now, in India alone, because in so many presentations you talked about the pump storage dam, this is going to be a big phenomena in the coming time. So these kind of projects gives confidence to the stakeholders, and now 23 such PSP dams are planned in India alone. So I'm sure that in Asia also, there in Asian countries also, there are a lot of PSP dams being planned in Thailand, Vietnam. They're planning a lot of PSP dams. And in Europe also some projects are being planned. So I'm sure that this kind of for India it's a milestone project. So we had a lot of learning, and we wanted to share that learning with you all. And I mean, we also learning a lot from you, all the presentations, and so and that's how we have to learn from each other, you know, and we have to move forward. It's a very sensitive technology. It's in the very nascent phase. Still, I believe that although it has seen only 7 to 8 years of life cycle till date, but we have a lot to do, lot to address, and I'm sure that we all of us will be facing a lot of challenges in the future as well, and we have to learn from each other and take it forward. Thank you very much.
Thank you, Pankaj, for your presentation. I don't know if there are any questions in the room.
Hey, one question. During putting the floats basically to its final position, due to the currents and water flows that you mentioned for the pump storage operation, do you have to have, let's say, special measures to get it to its final position and connect all the mooring lines to balance the impact of the water flows?
Yes, that is a very, very, very pertinent question. See, in the beginning itself, we had done basic arrangements to ensure that all the strips that were coming to the final destination, that is coming to the rightmost position. And that we did using some, placing some points with the buoys with the rightmost GPS location. And because it was as per the whatever we had planned on the paper, that this is the GPS location for each of the strips. That's how it has to be positioned at that location. And that's how step by step, we did that positioning of that to ensure that it is coming at the rightmost position safely.
Thank you very much for your very interesting presentation. Again, you mentioned like the weather conditions and so on, but you did not yet mention the electrical aspects. And I was wondering if you have to tow your system for 600 meters, is your electrical cabling also 600 meters away? And do you use floating transformers?
Yes, yes, very much. Although here the transformer and the inverter were on the ground, central inverter was used in that. So we had 600, 700 or 800 meter of cables, DC cables running from the plant to the shore actually. So we had to have that. This is one of the longest cable running actually on the water body. So this for us also it was like it's a challenge, but we managed to overcome that. Right.
There's another question over there.
Yeah, it's a short question. You mentioned GPS, but the accuracy of that isn't the case. Do you actually use GPS or RTK?
Yeah, we use GPS.
Not RTK? I mean, GPS hasn't that good accuracy.
So we were using the GPS, for the coordinates, we were using the GPS on the ground and positioning all the points as per the GPS, the real-time data only actually. So we were having the GPS fitted on the system, and that just we are bringing it to the final location that way actually.
I will have a question, Pankaj, if you don't mind.
Yes, sir, please.
My question is, normally a system is built on the shore, let's say that way, and pushed into the water, dealing with almost 1 meter per hour variation, let's say that way. It means that the launching place, it was already always moving up and down in terms of water level. How did you manage that? Because it's a huge variation to have, let's say 20 meters of water in one day. It's a huge variation. How do you manage that?
So that way, actually, I mentioned that that we had a very squeezed window actually. The window was very little in which we had to do that operation, and we had to have enough buffer actually. For example, when we are starting, that time, say, water level is, say, 0. And after that, it becomes 16. So we had to have enough buffer of the anchoring lines with us all the time, because whatever we are doing the final position actually. That is in the maximum, in the extreme condition, whatever is required, we were taking it along with us. Your anchoring line, your everything was going accordingly. So we were actually, so the answer to this question is that we were always considering the extreme conditions while carrying out the operation, even though we are not in that extreme condition. And that helped us to execute the things safely.
Okay. Pankaj, thank you very, very much for your presentation, for answering our questions. Thank you.
Thank you, sir. Thank you so much.
So, and now we are going to have Don Hogendoom, Dorn, that is the CTO and co-founder of SolarDuck, that he's going to present us about greening the future, shaping the future of offshore solar energy. Don, the floor is yours. Good morning. Thank you. And sorry for my pronunciation of your name. It's not easy.
It's difficult, right? Yes. Yeah. So good morning, everyone. I'm Don Hogendoorn, CTO and co-founder of SolarDuck. Let's see. Yeah, and this is me. This is last year when we just installed our first offshore pilot. So a very happy face. And I want to tell you today a bit about SolarDuck. Last year, our commercial director was here. He told the commercial story. I will tell more about the technical side, what we learned. I think that's way more interesting, in my opinion, at least as a CTO. But solar, why? Why do we want to go utility scale? Because there are many locations which don't have land, just like the Netherlands. We want to build houses, we want to use agricultural. It's complementary to the wind industry, so we really see a hybrid combination of solar and wind energy. And we can use the existing offshore infrastructure already. So the subsea stations, they're already there, so we can make use of that. And by that, it becomes much more complementary. This one we built last year, a pilot in Tokyo. We assembled that in 1 month. It was really to show to the Japanese stakeholders that we also can build a solution in Japan. What's quite interesting, we did this with land-based solar panel crew. So without any experience in the offshore industry, we trained them like an IKEA package. Basically, we delivered and trained them, and they installed it. We used quite a big crane. Lesson learned, we even had to get permits for the air traffic in the area, so the crane could only be used in a certain amount of time. But because there's a concrete wall which is 2 meters high, so else we would have launched it differently, but it was quite difficult to get it over the wall of 2 meters high. And that's installed there in Tokyo and serving as an demonstrating project. Next to that, we installed Merganser. That is our real offshore pilot. It's a 0.5 megawatt, 6 connected units. It's elevated, it's floating, so it's not standing on the sea bottom, but it's moored with mooring lines to the seabed, and designed for 11 meters HAMAX wave conditions, so quite significant. And here you see a little movie of the platform going to the lock of IJmuiden, which is the biggest lock in the world. And here you see the installation process. So we use very small tugboats, which you see in the offshore industry. And here you see some live, no, not live, but footage of the operation, how it's moving over the waves and how the couplings respond to that. These are wave conditions of 7 meters high, by the way. So that's pretty cool. I think we're learning a lot, of course. This is the first pilot, and even during the assembly, the first beam which we assembled together took us 3 months, a bit longer than expected. But the last one we did in a week. So you can see during a project already how much you're learning about how to assemble those things and how to do better. So the rest of this presentation will be a lot about learnings we took. One major achievement is Bureau Veritas certification, prototype certification for 11 meters wave height. That requires a lot of paperwork, checking all your reports, all the calculations. So we're very happy to be able to achieve that. And also on the operational side, we learned a lot, how to assemble the structure, validating the assembly methods we use. We don't weld, we use pins to connect the structure together. We have a patent on that. And getting used to working with that pin assembly method that required some time. Also now we're offshore, so we're learning a lot of that, not only on the technical side, but also on the operational side. Also the SODM, that's kind of the safety police, I would say, of the Dutch North Sea. They went on the platform, they inspected the access methodologies, the maintenance methodologies. So that's quite an achievement to be able to pass their inspection. And we are, of course, measuring a lot on the platform where we learn a lot of. What we learned a lot about the operation side. On the North Sea, there's quite some stakeholder management to do. You need permits, but also for the towing out operation going through the lock of IJmuiden. You have to talk with the lock authorities, you have to talk with the port authorities, you have to talk with the pilots. The lock authorities wanted to have their own tugboats where they are used to. We already ordered our own tugboats to tow the platform out. So a lot of discussion how to get this platform out. We said it's a pontoon which we tow out. There go many pontoons through that lock on a yearly basis, but they see, hey, this is a new structure, it's different. They're very proud on their lock. Will it damage my lock, etc. So it took quite a while to convince those parties, and took much more time actually than we originally anticipated, because we were thinking, hey, it's just a pontoon, we tow it out, it's very easy. In the end, it turned out to be very easy, but quite some convincing needed to take place. Also for large scale, utility scale solar, at a certain point you see that the lock dimensions become critical. So if you fill the entire lock, maybe you can fit 2 or 3 megawatts through it, but you want to connect 10 megawatt plants. So that means that offshore you have to start connecting them. But also there are speed limits in the port. So you should achieve a certain speed in the port to be able to tow out. And if you are too wide, also port authorities start having discussions with you. Can you go out? You should block certain days to go out so they can reroute the traffic in port to get out. So a lot of things which we learned on this topic, which requires some preparation. It's doable, but requires preparation. That's, I think, the main message, and you should start early with it. Next to that, on the data connection, that's the first pilot, so you want to monitor a lot. And it's offshore, it's not in a lake, when it's in a little lake, and you want to avoid that it gets damaged. But if it's damaged and it starts drifting around, it will hit somewhere the shore. With a large asset of 2 megawatts, 10 megawatts offshore, you don't know, you cannot see it. So your data connection is very crucial to know where the asset is, what are the loads that it is experienced, are all mooring lines there, these kind of things. And then the data connection becomes very critical. Offshore, around 12 kilometers, your 4G connection is dropping out. So you need different solutions also there to have a good solid connection. And also your camera layout. So you want to see every component basically with your cameras, because it's the only way to see it. Sending out maintenance engineers, of course, is possible, but it takes time to go out. And if it's in severe weather conditions, you you cannot go out. So you need to rely on your cameras and on your data. Together with TNO, we installed 190 monitoring sensors on the platform, measuring the motions, the mooring loads, cylinder pressures, the structural response, the solar output, temperatures, albedo effects, irradiance above and below the platform, and even in the water column, also for the ecology investigation. And here you'll see the wave profile in the lower right graph with 2 storm events of 7 meters high, roughly. And in the top one, you saw where the data dropped out because a software update was run. So that's also, yeah, a little hiccup, I would say, but it's a key thing to learn and to make sure that your system is before storm up and ready, let's say. Something on the platform, mooring and loads that we learned. So we saw that the mooring loads, the black line versus the simulations are the color lines. The mooring loads were significantly lower than and simulated. So we're investigating where is that effect coming from. We think it has a lot to do with the flexibility in the mooring line, where Oriol, I think, will share a bit later something on. But we also saw that the platform motions were a lot less than predicted. So there's a lot more damping in the system, meaning you have less motions, which is good for your solar output, but it's also good for the loads on your connections. So also based on this, we see that we are quite conservative, and based on this new insights, we can further optimize the design. Then we had these cylinders where we connect the platforms together. There we found that the stiffness is very in agreement with the predictions, but the damping in the solution is a lot less than predicted. That even now led to the conclusion that we don't need damping. There's already so much damping in the system that we can just use springs instead of spring dampers, so that will make the design a lot more easy. And also the motions are lower because the pitch motions are low, also the cylinder loads and motions are lower. In the beginning, we were quite afraid of we had worries about the gas temperature, that it would become too high in the cylinders, and then you could burn your seals. That turned out to be very low, although we see more gas leakage than anticipated, so we should further design for that. The structure itself is very robust. We don't see any strange vibrations. When you have those slender solutions, people are afraid about wave pileup, so that when a wave breaks against the floater, the water will move upward. And the question is whether it will damage your solar panel or it can also experience high pressures. We don't see that during the offshore time, so that's interesting to observe. So that means that we can also reduce the air gap a lot again. On the wind loads, we see that on the edges of your platform, we had wind sensors, and on the middle of the platform, we had wind sensors, and the outer edges experience higher, 2 to 3 times higher wind loads than in the middle of the platform, which is of course also logical because there the wind needs to go over the solar panels, and in the middle you already see more shielding effects. Something on output. TNO did some analysis on that. Offshore, I think that's for the entire offshore floating solar industry. We see roughly 6 to 40% more output. There are less clouds offshore, so that helps a lot. These are measured values, so it's not predictions. We see that the cooling effect is significantly more than inland floating, but also land-based solutions. There's always wind offshore, and the water is cool. So that gives an additional cooling effect on your solar panel, which helps also a bit. And the albedo effect, we see that in the morning. We didn't think it would be a lot, but we see that in the morning and afternoon, there's still quite some reflections on the sea surface, which increases the albedo effect. So that also is increasing your irradiance. We have solar panels with 2 sides, so we take energy from both sides. Next to that, we're doing, of course, research to further develop this technology. So Maring is doing very nice CFD simulations to see what is the effect of wave plus wind interaction. Normally in the industry, people do separate tests, wave test and wind test. We want to investigate what's the combined effect. There we see that wind load has a quite positive effect on the motions of the platform. So the motions become less and there's kind of a air cushion below the platform. So that gives a lot of additional damping. So for that, we're doing CFD tests, but also dedicated tank tests with wind and waves. And I think here you can see it. So here you see the waves, and on the back side you see the blue fans. And what you see here are North Sea extreme wind and wave conditions combined. And that turns out to be quite a bit better than wave alone. So that's quite interesting to observe. And currently we are in the assembly phase of 54 of those platforms for tank testing at Maring in June. So here you see the design, and then we want to investigate on large scale plant of 5 megawatts. 5 megawatts. What are the shielding effects? So what is on large scale, what are the shielding effects and how is that reducing the loads on the wave side and on the wind side? And even building such a model is quite a challenge, I have to say, because offshore floating solar uses quite lightweight structures. And if you want to scale that to 1/20, also the mass you have to be able to build the model is very minimal. So the model can only be 2 kilos or something like that. So it's quite a challenge even to build a model to be able to simulate the behavior. So I think I hope I gave you a nice introduction about some lessons we learned over the last year. So thank you for that.
Thank you very much, Jan. Any questions in the room?
Yeah, thank you for the presentation. I have a question. I saw on video, I think of a competitor of you with a lower system, which is very close to the waves. And I saw there that there was lots of whitewash over the panels. It was really white, either due to salt or bird droppings. So what is your experience with that? Do you see lots of salt on the panels, and do you also see many birds on your system?
Yeah, so because we have an elevated solution, we don't see the salt spray effect or algae on the panels. We see bird droppings, but it's really on the outer edge of panels, and also on specific locations. So it's not the entire plant, but it's really on the east and west side where they like to sit, apparently. And we're also thinking on adding additional features to the platform so that we even steer the birds more towards that direction than on your solar panel. But yeah, currently it's one row of panels basically of the multiple rows you have. So.
Any more questions? Yeah, another one over there. And meanwhile, Don, I believe that this pilot is going to get bigger. I believe that. I believe that there is a project for that. Am I correct or not? It's the pilot is going to be bigger in terms of size, in terms of more platforms, in terms of installation.
Yeah.
What can you tell us about that?
Yeah, so these are 6 connected platforms. So in the end, we want to connect, the next step would be 54 platforms. That's where we are doing those tests to get a further understanding of that. Based on that, we make a next generation design based on these lessons learned, with the aim to build that as well. Yeah.
Any time frame for that planned?
Yeah, I would say in the 2028, 2029.
Good.
Thank you for your presentation. What kind of water depth do you install these plants, and how do you maintain the station keeping? Because offshore, I assume that there'll be a lot of excursion. So would that lead to some stresses on the electrical cables that will be evacuated from the plant?
Yeah. Yeah, so the North Sea is quite shallow. So this offshore test site is 20 meters. You see projects up to 30 meters as well. But we also have requests for even a larger depth, even up to 800 meters of water depth. At a certain point, of course, your mooring lines will become quite expensive. Most locations are in the quite shallow region, so between, I would say, 20 and 40 meters. And that makes, especially the motions, the North Sea, the shallow water depth creates very steep waves. That makes it challenging. So in other locations, you have more swell-driven waves, which are more round, I would say. So there it is easier for the platforms to move over the waves. And on the dynamic cable, yeah, there's still many discussions on what would be the right solution for such applications. And it's also, of course, different for very deep water than for very shallow water.
Thank you. Just a quick question on the transformer. Do you have the transformer on board the pilot, or do you have it somewhere else?
Yeah. Yeah, so here on this pilot, there was no grid connection in the vicinity. So here we have the white container in the movie, and there we have the inverters and a small mini grid solution and some heaters, sorry to tell, but to do correct measurements on the solar system. In the end, we want to have a transformer if you go large scale, you have the transformer on the platform. And go from there directly into the inter-array cable of the wind farm.
Hello, Adnan. Thank you very much for your presentation. I just have a question about the maintainability of the assets. Do you plan to do component replacements on site or heavy maintenance on site, or do you plan to tow the islands to shore for any heavy maintenance of the transporter or the inverter?
You can't, right? If you connect 100 platforms offshore together, taking one out will be very expensive. So you need to be there for 30 years offshore. So the platform itself should have no maintenance. Of course, you can replace solar panels and do some maintenance on couplings, but it should be limited.
Any more questions? Done. Thank you very, very much.
Yeah, thank you.
So we are earlier than expected, what is normally a nice thing, especially for a chairman, because normally we have to manage situation on the opposite way, that is the lack of time. So we have time, so it's okay. I would propose that we are going to have a coffee break within some minutes. I would propose to start the break earlier and to do some networking, because I believe that with all the presentations, with all the people that are in the room, networking is something quite important, and also will give you more insights and more help to all the issues that we have to solve and for our development ourselves. So enjoy the break. I would say that we would be back at 11:15. We will be back on the room, okay? Thank you very much. Hello again. Welcome back after this break. We are going to continue with Oriol Colomés, that is assistant professor in the offshore engineering section of TU Delft. He's going to speak to us about offshore floating photovoltaics modeling, strategies, and challenges. Oriol, stage is yours. Thank you very much.
Thank you. Yeah, good morning, everyone. I'm Oriol. Nice to see that lots of interest in this topic, and today I'll talk about offshore floating solar. We had a very nice presentation by Don before, so you should be a bit familiar of how an offshore floating solar plant looks like. But I did this exercise myself a few days ago and asked ChatGPT, how does an offshore floating solar farm look like? And interestingly, you see something like this. As you can imagine, this might not be a viable solution, so we never have the sea looking like this, and probably we will not have just panels on top of slim floaters, okay? That means that there is nothing there yet where ChatGPT can start learning from. That means that's a new technology that has a lot of challenges. So we need to understand how things will look like in the future. So the talk, I'm going to talk today about what are the key challenges offshore briefly, what is the role of university in addressing these challenges, and what is the road ahead for offshore floating solar. So first, let's look at what are the main challenges and why offshore. Don already touched upon these points here. First, land scarcity, higher irradiance, and more importantly, I think, is the synergy with offshore wind, especially here in the Netherlands, for example, or in the North Sea, where we have offshore wind already deployed, so we can take advantage of that for deploying floating solar as well. Key differences with inland floating photovoltaics. First of all, the environmental loads, higher than inland. We have a grid connection also, it's a bit different. Installation phase, it's more challenging, and also operation and maintenance. Okay, so these are things that we need to think about when designing offshore floating photovoltaics. So what are the key challenges in offshore floating? We have extreme environmental loads, wind, waves, currents. So these are driving environment that we need to account for designing these type of structures that are much more different than inland floating. Mechanical durability. Here we have high cyclic loading that doesn't stop. So fatigue plays a relevant role. Corrosion, we are in salty environment, so that's also very important. Biofoiling, that's shared also with inland floating, but several challenges also offshore. About system challenges, how do we convert, how do we generate the power, how we transfer this power, and how we integrate into the grid? Can we take advantage of installed infrastructure already or not? These are things that have to be considered. And also regulatory and environmental aspects. Later we'll have a talk by Sven. So permitting, what is the impact in the ecosystem, what is the co-use of space, these are things that become challenging in offshore environments. So to address these challenges, we are doing some research, and this is where I will present what we can do at university. I like to see the role of university as an entity that can help reducing risk and accelerating innovations. University is not there to develop new concepts, is not there to create projects, but we can help to reduce risks, and we can help to move innovation forward. Okay, and there are several ways we can help with. One of them is through advanced modeling. And here we talk about multi-physics simulations, hydro, structural, mooring lines, all together. We do a lot of work on data-driven models, reduced order models that can accelerate these simulations and that can later be used for industry to design structures. We also have a lot of expertise in lab testing for structures, for wave tank tests, mooring tests, and so on. Another field where we can bring in a lot of expertise is in field validation and monitoring. We are working with state-of-the-art monitoring techniques and data processing methods. So there, university can be helpful. Open tools and data, the development of standard benchmarks that can be shared throughout the industry, open source software that can also be used for everyone, and also cross-industry collaboration, so we can drive collaborations between different partners. So this is one of our roles. And finally, industry implementation and scaling. So we need feedback from the industry. So that's one of the main reasons I'm here. We need feedback from you, and I hope you also get to receive feedback from university in shared projects. Right, so let's focus a bit on what type of advanced modeling we are working on in relation to floating offshore. So here we need multi-physics modeling, hydrodynamic loads. We also need to account for wind, structural response, mooring, and optoelectrical coupling. So that's also very important offshore because we have a lot of motions. We have multiple solutions that we need to deal with. We have the concept of solar duct with elevated platforms. We have also oceans of energy, for example, will be presented here later. About platforms on the ground or on the free surface or even membranes. And then we have the importance of modularity and have scalable approaches. Okay, so we cannot build something that is not scalable, otherwise it's not viable. Yeah? The same applies for the modeling. If we cannot model a scalable, if we cannot build scalable modeling strategies, that doesn't work for the industry. So this is where we are working on the development of tools that can assess hydroelastic effects in floating, probably flexible multi-platforms. This, for example, a simulation that we did 1 year ago already, where we couple hydroelastic response with waves, and also we are also working with flexible, rigid, or membrane platforms. Okay, and this framework is scalable. Another research line that may be relevant for the industry is dynamic analysis of synthetic mooring lines. So we have seen already in one of the speakers before the use of polyester. These are highly flexible lines which have dynamic nonlinear stiffness. So we are building models that can capture this behavior accurately. One other thing that we do is, that may also apply to inland waters. So let's say that you have a floating platform in a lake and there are ships passing through the lake. The waves that these ships produce are not regular waves. So these are not standard waves that we are typically using in the design of offshore structures. So you need to model how the ship generates the waves, and we have models that can deal with this, and also coupling with, in that case was a floating membrane, but it can be also coupled with pontoon or other type of flexible structures. And finally, the integration with optoelectric performance. Okay, so this is a study that we recently submitted where we try to see what happens to the optoelectric performance, the power output of an offshore floating solar platform when subject to waves. Okay, and here you see that the wave will have, so this is a spectrum of waves, the structure will move, and due to this motion, you will have a varying tilt in time, and this varying tilt in time will induce some motion losses, but also some mismatch, power mismatch losses if you connect the panels in a single string. Okay, so we evaluated how much these losses will be, and this is an example. For example, when you use a large number of floaters, you increase the number of losses of your system. Okay, and this on the right you have an image of the power output of a winter day. So the sun goes a bit, it's low, and you see that when you have horizontal, so steady state, steady solution, you have the blue line. When you count for motion of the platforms, you have the oscillations in red. So you have power oscillations during the day. But when you count for the mismatch between the panels, you get the black platform. So you see here that there is a significant loss of energy generated when you count for the mismatch loss in your platform. Okay, and this is platform specific and solution specific. We also looked in the same process. We also look not only in the optoelectric performance, but also what happens to the mechanical performance. You may want to have flexible structures to lower your stresses, but that will lead to lower power. So you need to find the balance. And then we are working with data-driven models, and you will wonder why I put here this bird. What you can see here is that this bird keeps the head fixed, okay? And the remaining body adapts to the wind to maintain the head fix. This bird doesn't have any sensor anywhere else in the world, yeah? And is able to keep the head fixed, yeah? So the idea that we had for us is, take some inspirations from that. So we embed this into an optimization model to control the motion of a system. Okay, so the bird has these muscles on the neck. So these are the actuators to keep the head fixed. So he has some sensors on the body. These are he can sense the motion and the wind. In the brain, he has some kind of model of the body that you can reduce to make the observation faster. And then you can optimize what is the response of the muscle in real time, such that your output of interest, keeping the head fixed, is satisfied. Okay, so why not adapting this concept to floating structures? Okay, so we have a floating structure. We may have one. Let's assume that we start with one flexible joint that we can actuate. Okay, we may want to put some sensors in the structure, not in the water. Okay, and then based on these sensors, we can build our model, finite element model. I don't know if it should work. No, it's not going further. Got frozen? Oh, too much. Well, there should be something before, but okay. So we have a finite element model of the structure, a reduced data-driven model that allows us to evaluate the response of the structure in waves in real time. And then based on this, using this reduced order model, we can make predictions. What will happen in the following 10 seconds if I change this actuator response? And we optimize the response based on these predictions, and then we fit it back to the structure, and then we have this loop again every X milliseconds. So we can optimize the response of this actuator to minimize the motion of the structure. Okay, so we did that for a floating structure. So we have a flexible floating structure that is subject to irregular waves. Now the structure moves, and at some point we'll start the actuator. You'll see a black line moving sometime soon. Yeah. And here you see we start actuating now, and you see that the rear part of the structure, that's where we are interested in reducing the motions, it is more stable. Okay. And if we look at how much percentage of motion reduction we achieve with only one actuator, it's 0.5%. Yeah, it's 50% of the motion most of the times, and we have close to the no actuation motion only where the motion is very small. Okay, so this tells you that we can already do something to mitigate the response of these structures. Okay. In the same line, we are building these reduced or data-driven models. We're using machine learning techniques to predict what is the deflection and so the tilt of your structure in real time. So if you can adjust for this power, if you can optimize the inverters to reduce the power losses, that's also something that you can do in real time using these type of techniques. Right? What about lab testing? We had a project where we're involved in a project, the Merganser project that Don was mentioning there. We are in charge of assessing what is the dynamic and cyclic behavior of polyester ropes. So these are highly flexible ropes, and we are characterizing what is the stiffness under cyclic. And we do here some tests, and you can see that we can evaluate what is the strain on the line in real time, and this is the setup that we used in our labs. We also have some experiments now going on with flexible membranes and try to understand what is the damping effect of these membranes under wave conditions. But we also have other type of facilities. This is at TU Delft. We have what we denote as the floating renewable labs. Is a set of labs that are segregated across the university, but we can merge them together using these hybrid approaches. All right, then let's briefly talk about our open tools. Here we are, the tools that we are developing are always open source. These are research-based software that we are developing, but we are always happy to get feedback from industry and ways that you could use this software and ways that we could integrate it in your workflow. And finally, what is the road ahead? Here we are going from pilot farms or pilot projects. Don presented one of the pilots that are currently deployed in the North Sea. But there are some expectations in the coming years. I don't know if we'll reach 45 gigawatt peak by 2050, but that was at some point in the table in the Netherlands. And for example, here we have the concept of oceans of energy for 200 megawatt peak power. So you see that there is a 10,000 times increase of the technology of the production. And that means going from a swimming pool to half of the Markermeer here in the Netherlands. Okay, so it's not something that is negligible, right? So what are possible effects? So we will have wind farm, offshore floating solar farms that are subject to wind, waves, and also the platform itself will interact, strong interactions that will modify probably the wind wave climate, and what will be the impact of these effects. Okay, this is something that we don't know yet, and this is why it is important to evaluate. So we want to know what are the turbulent kinetic energy wave patterns, how will it look like when we deploy 1 kilometer square platforms, and also for the industry, what are the platform-to-platform interactions? So can I design my different platforms taking into account the interactions between different plants? So to do that, we just started a new project funded by the Netherlands Research Agency, where we aim at assessing what are the floating solar farm scales effects at the farm scale. Okay, and this is a project that many people from this room are involved. Some people also from yesterday. We had some talks from Deltares. From NEO, we have Sven. Marin is also involved. SolarDAC and Oceans of Energy are also involved. DNV, I think it's also present in this conference. So many partners are already involved in this project. So we hope to get something that can be useful for the full community in the floating PV industry. Okay, that's it. Thank you very much. You'll have everything, all the references in this link. Let me know if it doesn't work. Otherwise, you can always send me an email or a message via LinkedIn. Thank you.
Thank you, Oriol, for your presentation. I don't know if there are any questions in the room. Yes, there are.
Thank you. This may be an unfair and difficult question to ask, but there is also many other offshore floating people from the Netherlands here, so maybe you can get help in answering. But how much is the Dutch government willing to pay for offshore floating? Is there a limit?
That I don't have the answer. I just know that there is some, or there was with the previous government, some push for this, and it comes from the fact that they want solar in the offshore wind tenders, and that's the main driver. I don't know where is the limit. Probably you'll have more insights from other people here in the room. So, yeah.
Anyone? Is there given kind of a goal for what cost it will have in?
I can answer. Again, Don Hogendoorn of SolarDAC. No, not yet. They're still exploring. That's why they make subsidy schemes available to investigate this and to map out a long-term roadmap and related subsidies for that. But it has a lot to do because there is no land. So they see that now currently the wind farms take away quite a bit of the wind. Also on the ecology side, there are questions. So the question is, how does it fit all together if you look at it from the Dutch total landscape? And then we think it's a very viable option into that, because in land, you already see in the Netherlands that the maximum project size is 10 megawatts, and that's it. And there are many stakeholders. If we want to accelerate, you need to deploy gigawatt scale, and there's no space. So it's a different discussion than you cannot compare directly with land or offshore wind solutions, but it has its own place, and the government is investigating what will be the price levels for that.
Thank you also, Don. Thank you, Oriol. Well, no more questions? If not, I will have one. From your modeling and from your developed tools, let's say that way, did you have made any assessment in comparison with onshore, let's say, waters and offshore waters? Is there a comparison possible? Is it possible to be used in inner waters, for example?
Yeah, the same models can be used in inner waters. So the only thing that changes is the wave input. It's much smaller. You may have also currents if you are in a river or sort type of thing. But the same models apply for inland waters.
Okay.
So if you build your models for offshore, then you can use them inland, not the other way around.
Okay. Thank you very much. Thank you very much, Oriol. Thank you. So, and now we will continue with Johnny Meilt, that is Head of Business Development and Sales of Oceans of Energy. He's going to do a presentation about low-cost floating solar at large scale, innovative design and installations. That is the main title of the presentation. The floor is yours. Thank you very much.
Good morning, all. It's a pleasure to be here in Amsterdam. When I was still studying here in Amsterdam, then that was the start of the solar industry. Back then, solar PV was, a bit of solar democracy, like everyone would have the opportunity to put some PV modules on their house and harvest their own energy. That was something that was amazing from a democratic perspective. And in some ways, it was like harvesting your own vegetables. What we see nowadays with solar industry is like that the rooftop projects, they are very small and they are therefore quite inefficient. And therefore the past decade, solar industry moved to larger projects, utility scale projects on, for example, agricultural space, and the past years also on lakes, hydro dams and other locations. However, if we really want to go large scale, then the solution is the space at sea. So what you see here on this image is the first offshore solar project in the world. This was established in 2019, and it consists of a floating energy farm of about 100 platforms, with each about 5 kilowatt of PV modules installed of them. It's located 12 kilometers offshore, and it operated for more than 4 years, surpassing all storms, including like some very scary ones, that when we were at our office, we had some onboard cameras, and every hour we would see a picture coming through about like these huge waves washing all of our PV modules. And then we always saw that there was an image of the sun popping up again, and that our solar system survived all of those extreme conditions. What we also see on this picture is that next to this system of about 100 platforms, there's a tremendous amount of space to scale up the system. And if you take this image and you would multiply this farm by 100, there would still be a massive amount of space available. And if you do that times 1,000 or 10,000, there's still a gigantic amount of space available for scaling up projects. If we want to establish a lot of renewable energies, and if you want to develop 1,000 megawatts, you can do this on land, but you would need perhaps 1,000 projects for that. Solar energy project of 1,000 megawatt, that can be done in one single project of 5 square kilometers offshore space. And for example, the North Sea Basin is 570,000 square kilometers. The Mediterranean Sea is 2.5 million square kilometers. So if we're talking about space and we're talking about solar, then the solution is to go offshore. At Oceans of Energy, we have found the solutions to master this environment. So our company started in 2016 with the full focus of establishing a technology that could harvest abundant renewable energies anywhere in the world. More than 50% of the people live around the coast, and about 70% of our energy consumption is in our coastal regions. So if we have a possibility to develop these projects in those abundance of space, then that's huge. To develop something like that, we immediately looked at how can we make a structure that covers such an amount of space on the sea. For that, the main solution is to have a system that uses the sea to carry the system. So by letting our floaters float in the water, we can use the water to carry the systems, and the amount of materials of the systems becomes incredibly low. It also provides opportunity to scale systems, to very large systems, by just adding more and more of these Lego blocks together. We do this based on an inspiration by nature. In nature, the largest solar collector is the water lily, and the water lily is a very thin leaf that floats on sea or on water surfaces. We resemble that, and we do that in a way with flexibility of moving joints that resemble a bit of a human spine, where we have our bones and we have the more flexible spots in between. If we look at a country like the Netherlands, you can see what a huge game changer offshore solar is. The Netherlands is a wind country, so most of the times it's very windy here, and very few days it's sunny. Most of the times we have bad weather. However, we are one of the top leading solar countries in the world, just because solar works everywhere. In terms of wind, the Netherlands already recognized very early that it was just not enough to build these projects on land. They moved offshore. After 2 decades of successful industry policies, we have now established almost 5 gigawatts of offshore wind in the Netherlands. For that, we have allocated almost 1,000 square kilometers of our sea surface. If we use 25% of this space for solar, which is available in between these wind turbines, we have space for almost 50 gigawatts of offshore solar. And if we would connect the same solar systems as the offshore wind installed capacity, so adding 5 gigawatt on the infrastructure, no additional power export infrastructure is needed. Instead, we can save a lot of cost by utilizing the offshore wind infrastructure better. So by only using about 3 to 5% of the wind farm space, we can double the installed capacity and we can save our society a lot of costs. If we continue this map, we see at Oceans of Energy that there is so much space in a country like the Netherlands that the 300 gigawatt installed capacity is a realistic goal to set. Currently, our country has a renewable energy production of 70%. That means that 83% of our energy consumption comes from fossil fuels. And a lot of those fossil fuels are being imported. So there's a huge import dependency in the Netherlands, and that is at a high cost for the climate, but also for our economy and also politically. So if we want to become independent of energy, the big game changer to get to this self-reliance and to prevent hostile governments to earn a lot of money on our energy, that is to go with offshore solar. We see that also in other countries in the world. What we took here to the right is the level of the number of PV modules installed per capita in the EU level. What is quite extraordinary about it is that it's not the high solar countries in the Mediterranean that score the best. It's countries like Netherlands, Belgium, Germany that have quite moderate solar conditions. What this implies is that it is not the cost of a solar project and the solar modules that result in the amount of renewable energies that are being installed in countries. It is, however, the difficulties with finding land and developing projects. So instead of being restrained by the space on land, a movement is made to sea. There are huge projects possible, and that can really extend the amount of renewable energies gigantically. And just by using 0.2% of the Mediterranean Sea Basin, we can install 1,000 gigawatts. And that would be amazing for our countries, for Europe, for our energy independence, and also for our industrial developments. So, how we see offshore solar, that is a solution for the space challenges on land. And the benefits for that are not just for the amount of renewable energies and the amount of carbon emissions that we can reduce. These are wide societal impacts that Europe needs. So these are the things that are highlighted nowadays in European industrial policies, such as the Draghi report and other things. We need these type of new industries to sustain ourselves. And here we have a concrete case which we presented in Ravenna a couple of months ago, where we won the award for best paper, in which we established a simulation model of an offshore wind farm and an offshore solar project, the amount of benefits that would bring. In the blue bars, you see the wind energy production of a wind farm in the northeast of Italy. If you add the same amount of solar, you add the yellow bars, and that results in an enormous amount of added value for such a project that not only compensates for the investments in offshore solar, but also compensates for the investments in offshore wind. So by adding and integrating offshore solar to the wind energy infrastructure, the gains, they can make the infrastructure work. If we look at the Oceans of Energy system, what we currently established is systems on a small scale, 100 by 100 meters. What we need to establish is very large cost reductions to make this work, and also to scale up systems to a very, very big level if we want to establish hundreds of gigawatts. So for that, our concept is focused on a very expandable system, so very scalable. So the platforms that you saw in the beginning, they can just be expanded more and more and more into larger islands. And those islands bring a lot of benefits. So first of all, we see that the number of loads decreases extremely on the floating farm itself, what thereby allows for large cost reductions on the floating farm components. Secondly, we see that for the mooring and the anchoring system, the perimeter of a system, it decreases a lot when you scale. So if you do the length and the width times 10, your perimeter only increased by 4. That results in very large reductions in numbers of anchors and mooring lines that you need to install and also buy. Power export cables, the differences are even larger, because a 200 megawatt farm, you can connect it with only 2 dynamic power export cables, and a 1 megawatt farm also needs 1 power export cable. So imagine the difference. Same goes for the offshore installation works and also the benefits of making like these systems much larger, being able to connect multiple batches offshore. And in terms of operations, we have very large reductions in the number of components that need maintenance. And in addition, also because of the lower loads distributed over such a system, we also see that the maintenance requirements go down very rapidly. That brings us to the benefits of the Oceans of Energy system. And if we calculate these into economics, then we see that the system cost of offshore solar are pretty much below offshore wind in North Sea regions, and a lot below floating offshore wind that we see everywhere in the world popping up. This is therefore a viable investment industry. We are now at the situation that we have tested and validated our offshore solar farm system for over 4 years. We know everything about the performance, the operations, the management of the systems, and we have now been able to commercialize our system. So this summer, actually in a week from now, we are building up our Hollandse Kust Noord 1, HKN1 offshore solar projects in the port of Amsterdam. This will be the first grid-connected offshore solar project in the world, and is integrated in the offshore wind farm of Crosswind, Shell and Eneco. For that, we made huge steps, not only in the technology, but particularly in operating as a professional company that can meet the requirements and the risk profiles of such highly established clients. Oceans of Energy managed to deliver this project on time and within the quoted budget, which is very amazing for energy projects in general and innovative companies, innovative concepts in particular. So what we see here is already the development of that we have built all of our floating platforms. They have all left our factory. We have them in the port, and we have installed our anchors offshore. The power export cable, it passed all of our factory acceptance tests, and it's ready for operations in the North Sea environment. And in 2 months from now, we have an operational offshore solar farm in the world. We do this based on a team of more than 50 individuals that come from diverse backgrounds and have a plentitude of expertises. They're all impact-driven and aiming for establishing a lot of solar energy projects in the world. Next to that, we can do this for the offshore environments. We can also leverage our capabilities for the inshore solar market. So first of all, we are extremely experienced with developing and designing mooring systems and other engineering works, which can help to establish projects anywhere in the world. Secondly, we see that a streamlined version of the Oceans of Energy offshore solar system is very applicable, in particular for the more rough inshore solar conditions. It is therefore a feasible alternative where other systems might encounter more challenges. So that brings us to the end of this presentation, where I wanted to share with you our story about what offshore solar can mean to this world and why it is important. So I'm very grateful to have you all here in this audience and to share with you this story and to help you on board with this part. With Oceans of Energy, we have mastered the offshore environment, and it is now ready for commercialization and applications on a very large scale. On a very large scale, offshore solar is the most economic solar energy system. And in addition, with our team, we can provide you services also for inshore solar markets. So thank you for your attention, and please follow us with our HKN1 project, for which you will receive quite some updates this summer. Thank you.
Johnny, thank you very much for your presentation. I don't know if there are any questions from the audience. There is.
Yeah, thanks very much, Johnny. I'm really curious to see if all the predictions of the larger scale will come through in the future. And I was wondering about your technology, because you say your platform is based on a water lily, which makes sense, of course. But do you use then micro-inverters, or do you have a special solution for inverter islands?
So we actually have a system that consists of modular platforms, and about 90, 95, 98% of our platforms are platforms that have PV modules. But we also have some specialties that also include our inverter systems, our communication hubs, our transformers, our boat landings. And we bring all of these like as a box of Lego to a client.
Thank you. And I'm sorry if I missed it, but how big was the pilot that you will deploy now?
So the project that we are installing this summer is 0.5 megawatt.
Yeah, thank you. Just wondering, you wrote something, self-cleaning of PV panel using the seawater. We all know that panels and seawater with salt, they are not the best friend. How you deal with this one when it comes to salt on panels, on MC4s, how you cover and protect your electrical component, like such as inverter, whatever.
Yes, thanks for a very good question. So what we see is like that all maintenance that you would have to do in an offshore project is very expensive and also comes also as a safety concern. So what we aim with a technology design for an offshore solar project is to have zero maintenance or the minimal maintenance. So to deal with questions such as salt and bird droppings, etc., we had to, from our design stage, decide upon how are we going to tackle these questions. For that, we saw as the best fit to use the sea and the rains to clean the PV modules. So what we have is actually that our platforms are so low to the sea surface that we have waves that wash over the PV modules and provide the self-cleaning capabilities. And once the water is passed over the floating platforms and the PV modules, we have a leakage system which makes sure that the water doesn't evaporate with the salt on the PV modules. So by doing that, we have a self-cleaning mechanism which has successfully helped us during the past 4 years.
I didn't get you, sorry. I need just to understand how you deal with the salt water on the panels, if you just can explain this.
So the waves, they wash over the PV modules.
Yeah, with
and
salt
then,
water.
Yes, and then there is no salt that stays
come?
on the PV modules because it washes off with the waves.
With salt water.
So the waves itself, they consist of salt water.
Yeah.
And this washes off the floating platforms. So the waves, they don't stay on the PV modules.
But they leave the salt on the panels and the connectors, etc.
We haven't experienced anything like that because actually we have a system where the water leaks off the platforms, and because of the wave motions, we see that actually the water passes over the PV modules and therefore leaving no deposits.
I think there was a question over there also.
Yes, thank you for your presentation. I was just wondering, when you scale up, so now we have 0.5 megawatt, and that's one island, I guess. And if you go to 10 or 20 or even 1,000 megawatt that you had up here, will that then be several islands?
It would be the same island.
Okay, so
by
one
connecting the island to each other, you create a lot of benefits in terms of like that you need way less mooring lines. And by having these connections, you create actually protection for the whole structural integrity of the island.
Yeah, so then my next question is, if you have this huge, what was the number, 3,000 by 3,000 meters, what do you do about the mooring system?
So the mooring system becomes very easy if you have a 3,000 by 3,000 meter system. So we use for offshore solar, we use perimeter mooring systems. And the larger the system becomes, the shorter your perimeter becomes. And that results in that you need way less mooring lines, way less anchors to connect to your offshore solar farm, thereby reducing a lot the cost of the components, the cost and the operations of installing them, the operations also during the maintenance of those components. And at the same time, because the platform and the island has increased in size such a lot, the amount of loads per megawatt have reduced by also similar levels of 80, 90, 95%.
Yeah, the loads per megawatt is reduced, but the load that the mooring line sees is still significantly higher, kind of per mooring line.
I'm not sure from which organization you are, but if you could please send me an email, we can forward you also to our engineering teams. One of the things that we are working on together with the Marin in the Bamboo project is to showcase this. And so far, all of our testing campaigns have showcased the viability of this solution, and that actually the mooring lines and the mooring loads, also at the mooring connection points, they decrease significantly, resulting in incredible cost reductions for your mooring and anchoring system.
Okay, thank you. No, thank you. That sounds very, very interesting. I'm asking because I'm from Moss Maritime, so we also do have the technology for offshore floating, and we don't see that effect, but that could be our design, of course. So very interested to hear more about that.
Thanks.
So, Is there? There are no more questions. So, Johnny, thank you very, very much. I believe that there are no more questions. Thank you for your presentation and your answers. Thank you very much.
Thank you.
So, and now we are going to have Aurelian Kroc, that is the CEO of Solar in Blue. That Aurelian is going to make us a presentation about floating offshore solar and timing 9 meters waves. So, Aurelian, the floor is yours.
Hi, everyone. So I'm very happy to be here, and the presentation of today. The idea is maybe to skip through the most generic part and maybe get back to the feedback that we have and the latest news since the presentation of last year. So I think my fellow colleagues explained very well the rationale behind floating offshore solar. Basically, the idea is we lack space, for sure. The Netherlands lacks space. But it's also the case in France. We install most of our PV through very small scale installs. That's completely inefficient. And plus, that's not at scale and not to the extent needed to really decarbonize our electricity production. And the idea is, of course, that we need to find some solutions to deploy very large scale projects quickly. So how to achieve that? Basically, going offshore. You got it, no land use competition there, no visual impact, very important. And in France, it takes like somewhat 10 to 15 years before deciding where to put an offshore wind farm. Some countries are better at that. But basically, having no visual impact is a very, very strong argument in favor of a fast deployment of the technology. We are able then to settle very close to shore. That keeps the connection cost as low as possible. And we get additional irradiance. So as you know, offshore wind, part of the business case is that you would get more wind offshore. It's also true for the sun. You get more sun on the seashore. So you can see for yourselves. It's true everywhere in Europe. It's true in England. It's true in the Netherlands. And it's true in Germany. In Germany, you can also see for yourselves that, for example, the northern part of the country, which is full of wind, has a nice irradiance in the Baltic Sea. It's counterintuitive, but it's the kind of irradiance that you would find usually in Nuremberg if you're looking only at latitude. So basically, you can, and of course, it's the same result for France, for Spain, Italy, etc. So you can see that when you go offshore with solar, you also get for free from 5 to 15% more irradiance. And if you look at the average irradiance of each country, then it's even more, of course. The 5 to 15% is really conservative figures. The idea for offshore solar is to deploy in, of course, collocation with offshore winds, but not only. There's a ramp up in the deployment of the technology. So the idea is, first of all, to deploy where decarbonized electricity is the most needed and on projects that are relatively small scales. That's basically decarbonizing port and industries and the blue economy in the context of the Fit for 55 framework. Then we're looking at islands. Basically, if we look at French overseas territories as well as European overseas territories, there is a lack of deployment of renewables there. There are basically no options. You can't do much onshore solar because you have very high constraints on land use on islands, for sure. You can't go for offshore wind because, of course, it's very expensive and that's small projects that you would find there, so it's not doable. And if you do onshore wind, then the visual impact of it is basically not in favor of tourism, which is often where the sector from which the island gets most of its revenue. So basically, you're left with the option of going offshore to get some land, and with the technology of floating offshore solar that you're able to deploy easily on small-scale projects, close to shore, no visual impact, etc. I'd like to add to that that we currently are in the process of deploying a project in an island where we will also demonstrate that the shadow brought by the solar panels helps also the ecosystems to recover from overheating and UV and ultraviolet radiations that they get, and especially corals would get better habitat when they are under the panels rather than whitening due to the climate change. And last, as you understood from my colleagues, the deployment in offshore wind and solar collocation, which is, of course, the market that's the most massive and with the broadest perspectives in Europe and worldwide. So where are we now? So as for Solar in Blue, we have a demonstrator that's deployed in the Mediterranean Sea since the end of 2023. These are the two floaters that are deployed in Sète, so that's close to Montpellier or Marseille. The strength of our design is basically to elevate the solar panels, because we strongly believe in the fact that the solar panels need protection from the very harsh conditions that you will get offshore. They don't like breaking waves, they don't like, especially the junction boxes and the DC cabling, they don't like too much movement or being submerged for too long. And also, we want to keep the cost as low as possible, so we will be elevating, but for sure not too much. So the idea is that our technology is able to ride the waves, you'll see that in a minute, which means that just by elevating the panel from 3 meters, we are able to sustain waves of far more than 10 meters, okay? Which of course helps with the economic equation of it. So basically, this is the small snapshot so that you can see for yourself of what happened in, last March. These were very harsh conditions. The waves here are around 7 meters. And you can see the floaters going up on a crest of the wave. Then seconds later, it's a trough. Then you can't see them anymore. Okay, they are in the bottom. And just a few seconds later, then they appear back. You can see for yourself the two floaters appearing back again. So you really have to imagine that all the mooring and all the connection between the floaters is made so that they are really able to float next to one another, keeping a consistent behavior, and they are always aligned, no collision at all, and they follow the movement. But still, the panels are always protected, and you can believe me that when it's in the throat, the panels are for sure entirely protected from seawater. So it's always hard to have visuals of this because basically the drones can't go there because there's too much wind. But in the next video, which I hope will work, it will not. So in this video, it's conditions where we can definitely have drone views. So it's just 2 to 3 meter waves, okay? But then you can see how we are going to climb up the wave and then go down. So that's the exact same principle which I showed on the picture. Of course, it's less impressive in there, but then you see the principle and the idea behind the technology. So we're very happy basically with the results from Sunset, and we're happy with the results, but also the time we spent at sea. Basically, we are deployed now since almost 18 months, and we are now able to have a real track record over the long time. So basically, we got the worst conditions possible. It's 9 meter waves in March 2024. It was just a few months after the commissioning. And basically, this is almost the 50-year return wave. So I don't know if we are lucky or unlucky, but basically, it was demonstrated since March 2024. And this year, we got a little bit less. It was 7.7 meters. But basically, the idea is to show that over the long run, you can have a system working fine and sustaining very difficult conditions. Then there's the question also, of course, besides the structural part of it, of the electrical production. And there we were, I'm sure, just like all of you, very much concerned about what would happen with our fellow birds. And the idea is that in the Mediterranean Sea, we have very dry conditions. So just like you understood, when you get the panels washed by rain and everything, then the bird droppings, they go away very easily, okay? Rain is sufficient. But we were really wondering, what about a full summer of sun, 6 weeks, not a single drop of rain, then what happens? And the good news is that we have these results, and basically, even 6 weeks without rain, if you get a first rain of 20 millimeters, it's not that much, it's just a small rain, then the panels are washed and you get almost nominal conditions for them. Due to the location in the Mediterranean Sea, we could also test how things work when you have other sources of soiling. And basically, I'd like to highlight that the only other possible soiling is basically coming from sandy winds. Okay, so that's the Sirocco, Föhn. It has many names, okay, but it comes from the Sahara and carries lots of sand particles. And you can see that just 3 days of dew, no rain, is sufficient to wash the panels. Again, I'd like to highlight that these are the two only soiling mechanisms that happen on our technology. The idea is that there is no, just like my colleagues explained, the sea crust or whatever is something that just does not happen. And I'd just like to remind everyone that this idea of sea crust, it comes from the places where you produce salt. Actually, you wait for on a still water area. You wait for the water to evaporate and nothing moves, there's no rain, no nothing, and then you get a sea crust. But that's absolutely not the case on 5-degree tilted solar panels exposed to rain and where you have, of course, no amounts of water blocked whatsoever on the surface of the panel because it's glass, it's tilted, so it's, of course, evacuating. Then we also, so this is really the latest data that we have. We could also start to draw some comparisons on the electricity production that we get from 1 year to the other. So when we say that the soiling is basically under control, then there's still the question of do the solar panels like being at sea? And the answer is pretty much yes, they like it. You have it from the 24th of April 2024 to 24th of May 2024 again, and same thing for 2025. And you can see that when you normalize the production ratios, basically they are in the exact same range between 2025 and 2024. And if you do a bit of a statistical analysis, then you can, in very conservative way, say that you have a less than 0.5% degradation between the same period in 2025 and 2024. That's basically saying that you would get the exact same on the ground. And basically, we are just like a floating solar car park canopy, and you can tell that's really the case here. It's the same, the solar panels are protected and they are not affected whatsoever by the offshore conditions. That's very important. I'd like also to highlight the fact that the solar panels that we are discussing are not the latest ones with offshore certification and everything. They are completely mainstream. You would find the exact same on any onshore project. They are just bifacial, anodized aluminum solar panels. That's it. Okay. So to summarize a bit the key findings that we have. Basically, we have a production that's fully in line with expectations. We get additional production thanks to the use of bifacial panels. We get a bit better production thanks to the lower temperatures that we get offshore than onshore. The de-optimization of the tilting has no effect on the production. The main reason for that, we'll discuss it in a minute, is basically that when there's a storm, the irradiance is low. So when basically the panels are moving, in the photos and videos I showed you, it's almost the night time, right? So it's fine. That's no impact on the production. Natural cleaning with rain and dew solves any issues regarding birds and sandy winds. And plus, we get the finding that the solar panels, which have the best capabilities onshore, are also the best offshore, which simplifies a lot, of course, the procurement and the business case for the technology. With the success of this first demonstrator, these first 2 floaters, we'll be moving by early 2026 into Megaset, which is a 1 megawatt project. Basically, the idea behind Megaset is to have floaters that are far bigger and also higher energy density. The floaters that you saw previously were in around 10 kilowatt peak each. Here we are discussing more than 100 kilowatt peak per floater. Okay, so it's 10 times more per floater. Also, we'll add a cable to shore and a floating transformer unit that you can see in the shelter at the top side of the farm. And the idea is that this pattern of 1 megawatt can be scaled and deployed virtually with no limit, but the space available at sea, for example, in between wind turbines. When we are speaking about these large deployments, there's of course the question of how will we do O&M. Of course, floating offshore solar is a nascent technology. We still have a lot to learn regarding O&M, but there are just one idea that I'd like to highlight. When you look at the economics of O&M, and you take the example, for example, of offshore wind, then you see that, for example, a wind turbine would break during a harsh event in December. And when the wind turbine breaks in December, the conditions are horrible, very expensive to go there, very difficult, etc. Plus, you lose a lot of money because there's lots of wind and you can't go, or if you want to go, then you have to pay a lot. For offshore solar, it's exactly the other way around. The weather is bad. Great, we don't lose any money, right? Because it's in December, January, the solar PV production is very low, okay? And then we get to wait until the weather window is far better to intervene, and this is in synchronism with basically with the economics at stake. So I think that's really one very, very important rationale to understand behind offshore solar, is that you remove the notion of emergency with offshore solar in terms of O&M. Plus, I'd like to add to that as you've seen, and as you may have experienced onshore, the solar panels, they are very resistant components, and it's not necessary to plan on any kind of maintenance for solar panels. The only components that require maintenance on an offshore solar farm are basically the inverters and the transformers. Okay, you may run into problems with the junction boxes, but then if you have then the economic impact is very little. So again, the only things that you have to be worried about for O&M, inverters and transformers. So it simplifies the scope a lot. Then we are, of course, on our way to move towards floating solar and offshore wind collocation. I think you got from my colleagues most of the rationale behind it, and basically same connection, same substation, and then you can add to 30% more electricity by adding offshore solar to offshore wind, and you use just 10% of the area, so it's very easy to deploy inside an existing offshore wind farm. Just to draw some perspectives, the idea is that the market for offshore solar is rising. It should rise faster, but we see some movement in the Netherlands, of course. We see some movement in France, first demonstrators in Spain. Italy is looking a lot at the deployment of floating offshore solar and collocation with offshore wind as part of the deployment of floating offshore wind in the Mediterranean. Malta, Greece, etc. are moving. We see some interest emerging in the Caribbean and Southeast Asia. It's starting with nearshore project, but the more they go, the more they are reaching out to harsher conditions. And China, as you know, is moving fast, and they already have done a lot of fixed bottom offshore solar. Now they are moving to floating and also have their own demonstrators already running. So basically, the message here is we have technologies, we have the vision, we have a lot of needs in terms of decarbonizing of the electricity production. So we strongly believe that the offshore solar market is to rise, very fast in the upcoming years. Thank you.
Thank you, Aurélien. I don't know if there are any questions in the room. Yes, we have one question over here and another one over there.
Can I go first? Okay, thank you very much for the presentation. You just mentioned that in terms of operation and maintenance, the only components that need maintenance, it's the inverters, transformers, and sometimes the junction box. What about the moorings? Do you have to do some preventive maintenance on the moorings or?
Sure. So the idea is more that for the structural part, the design lifetime of the asset is 25 to 30 years, depending on the client, the customer requirements. For the mooring lines, definitely the design lifetime is the lifetime of the plant. So you would definitely want to perform some inspections, basically ROV based, but you don't plan on replacing any mooring lines.
Okay, thank you.
Thank you for some interesting perspectives. You mentioned that regular modules is the best also offshore. Of course, many of the top producers have some sort of offshore modules or marketed as offshore modules. It can be some coating on the glass, IP68 junction box, of course. Do you go for any of these or not even the slight modifications?
Basically, behind the choice of the solar panel, there's one thing is what is needed from a technical standpoint. Then I would tend to say that maybe there is some marketing in the offshore solar panels, and that's for sure. But there's another part of it, it's the warranty that you get. And the idea is that you will increase the bankability of your project if you are to use solar panels, which come with a warranty on them, and that basically they will not be willing to provide such warranty unless if you go for their offshore product line. So, yeah.
Thank you. One more, if I can. You said you normalized the performance ratios.
Yeah.
Couldn't you show the real performance ratios?
Sorry, what? Yeah, sure.
Yeah, and also what did you normalize it against? The starting, your baseline starting PR or?
No. So basically, the idea is that the system that we have deployed is not connected, right? So basically, we are dissipating by Joule effect the energy. So basically, the PRs, they do not include the inverters. So if I show the figures, then you are going to find them high. And of course, because there are no inverters, right? So that's why we normalize by 1 on the 2024 average, but it's just to show that they don't move from year to year. I wouldn't like to tell you that we have 120% percentage ratio, performance ratio, for sure. That's not the message here. The message is that the performance ratio does not move from one year to another. Voilà.
Thank you.
Yeah, I have just 2 questions here. Yeah, thank you. The first one was just I want to understand, can you give us some figure about the cost of the mooring for such a system?
For the, sorry, the what of
mooring,
the mooring? The mooring, yeah, basically. So the mooring of the system, well, of course, it's very site specific, right? But the idea is that you will get mooring on some of the perimetric floating solar units, okay, on the perimeter of the farm, okay. That this is where you will install some mooring lines. You are to focus especially on the corner floating solar units, okay. And plus, the mooring for such a system is very asymmetric. It really depends on where does the swell come from.
And the cost. What about the cost comparing to the cost of the whole system?
Comparing to the cost of the whole system, it's going to be somewhere in the 10 to 15% of the cost.
Okay. And the second question, you have mentioned 200 kilometer per hour wind, which is about 56, 57 meter per second.
Yeah. So basically, this is only about the top structure because basically there's no wind issue for the bottom part of the.
Interesting on the force below the panels. Do you have done any calculation or?
Yes.
You have some calculation which has been done by the manufacturer, and you have.
No.
And etc. So I'm just wondering about the force under the panel.
No, so the 200 kilometer wind is the maximum that we will look for. For Megaset, we will not pay for the profiles to sustain the 200 kilometers per hour wind.
But
Okay.
you cannot manage it, right?
Oh yes, you can. Just like onshore, you can if you oversize if you size appropriately any onshore solar farm, then you are to sustain such winds. That's done. I can give many examples for that onshore. But then if you are looking at this top structure, of course, we made it lighter. But we did the computation because what matters is the mass, the additional mass that you will get when you do the top structure to sustain the winds over 200 kilometers per hour.
Yeah, but my question was about the force. Do you have made any calculation?
Oh, so I'll have to get back to you on the exact force. I don't have it in mind, okay, on the pressure. But the computations have been done.
And relatedly, I'd just be curious to know what models you use to do the simulations, to look at the loading under those conditions.
So basically, the software that's used is basically OrcaFlex for almost all of it.
Yeah.
And the CFD software, I don't remember the name of the CFD software that they use, and the structural is done via Abacus.
So, no more questions? Brilliant. Thank you very, very much for your presentation, for insights. Thank you. So, and now let's move to the last presentation before lunch. So I have Sven Trollings. Yes. Yeah, thank you very much. He's a senior researcher at the Dutch Institute of Ecology. He's going to address us a presentation about pathways toward a natural, inclusive, floating solar future.
Thank you.
Thank you very much.
I think I have the wrong presentation.
Don't tell me.
Yeah, I'm quite sure. I'm very sure, actually. I'm really sorry. I think I sent you the wrong one. I will quickly fix this, because otherwise you get a very different story. My apologies. Hopefully that solves it. Well, otherwise, I will just give the other one. Don't worry about it. It's also interesting. It's also about FPV, so at least it's in the right frame of mind. So just to briefly introduce myself, so I can skip through some other stuff. I am Sven Teurlings. I'm from the Netherlands Institute of Ecology. So I'm an ecologist. I know I'm probably in a slightly unusual place here as an ecologist. And to make matters worse, I'm going to talk about everyone's favorite thing, environmental legislation, which is not purely my own field. Most of the time, I'm quite happy to just be outside and look at organisms and things like that. But it's quite an important one when we start talking about the energy transition. So if we think about the energy transition in general, a very important aspect there is, of course, our energy targets. Yes, there we are. Thank you so much. Sorry about that. I'm going to take the Netherlands as my case study for today. And the good news is we have a lot of energy targets. So if we then think about inland FPV, essentially, if we want to meet those energy targets, we have to upscale. We have to upscale quite massively. Currently, we have quite a few plants in operation, but they're all, well, I would say, on water bodies that are not the largest ones we have, nor the most important ones from an environmental perspective, and that has its reasons because of environmental legislation. The good news from an ecology perspective is we also have environmental targets. Quite a lot of these are European-based in essence, or even global-based, and put into Dutch law in one way or the other. So we're talking, for instance, about the Bird and Habitat Directive, also known as Nature 2000. The Convention on Biological Diversity just had some new targets there. And not unimportantly in this context, and this is the one I'll focus in on most, is the Water Framework Directive. If we look at some of our indices and whether or not we're meeting those targets, well, we're the Netherlands, we don't actually meet environmental targets. That's not how we work. That, however, does have its issues, as we'll come to. So this is our current state of the Water Framework Directive for all water bodies designated as such in the Netherlands. This map needs to be green by 2027. Yeah, that's not going to happen. That's the nasty story. However, that has all sorts of reasons, and a big one is a lot of ecological basis and chemical basis. So essentially, this one shows all different elements that come together into the top part, ecological state. And I guess so this one needs to be green, and essentially everything for a certain water body needs to be A-OK for that to happen. Yeah, there's always something wrong. Very often it's both chemical as well as ecological. That, however, does have consequences. It has consequences for the ecology as a whole, but also for the FPV sector if you actually want to do anything on water. In 2027, we need to meet those targets. Everything needs to be in a good ecological state. If not, we're probably going to get some fines. Well, okay, we might be able to pay those. We might get some legal action from NGOs. Well, I guess not might, we will get some legal action from NGOs. But not unimportantly, we'll also have a much bigger issue in permitting because the water quality should have been good, it's not good, so unless we actually have it in a good state, it's very unlikely that we'll be able to give out a permit to do anything that might impact the water negatively. So if we're not in a good state, we're not going to allow ourselves to deteriorate water quality any further. Okay, but does FPV do that? Well, the burden of proof to show so is on whoever wants to do something with that water. So the water management side will say, prove to me that my water quality will not deteriorate further because it's already bad and I want it to be good. So I'm already in trouble. Is your project going to bring me into more trouble? Well, let's have a quick look at some of the recent work that's out there, or less recent even, on what FPV plants might do in inland waters. So this is a study from 2021 actually, and the conclusion of the authors here was, well, we see some effects, but it's not all that major. From a purely ecological point, I'm tempted to agree. However, that's not how environmental law sadly works, because environmental law is going to look at this and say, well, if we compare the blue line to the dashed blue line, the blue line being a reference location, the dashed blue line being a location underneath the FPV plant, there's a decrease. That's an impact, that's a problem. Yesterday we looked at some of the model results. Wilma showed these earlier, and the conclusions we drew ecologically is, well, we can allow some FPV coverage, because essentially not much happens to, say, the oxygen concentrations initially. There's only sort of a big drop after 15–20% coverage. Good news. However, if we look very carefully, we do see a small decrease. So there is an impact, and that is not a positive impact. So if in 2027 this water body is not in a good state, you can't build that plant, not with 1%, not with 2%, not with 15%. To make matters worse, if we then think about what you would actually need to measure and monitor to show whether or not there's any changes in water quality, that is not just oxygen, that is not just chlorophyll or something that you can easily measure with a sensor. The Water Framework Directive is based on biological quality elements, and that's in many cases everything from phytoplankton to fish to macrophytes, so plants in the water, to macroinvertebrates, which are small, which is a huge group of small organisms from snails to insect larvae that are very often assessed on a very low taxonomic level. So you really need to know which species is it to say something about that. That is not something our models can actually do, realistically speaking. So we're not able to tell you with a model, it will definitely go well if you do this. That is a huge issue, because essentially we're now looking at what is best described as a gridlock. To make matters even worse, yes, we're going into the lunch in a very positive manner, I know. We know that ecological recovery, but also ecological degradation, does not happen instantly. It has quite a long time lag sometimes. It has nonlinear impacts. So there's a good chance that even if waters are already in the process of improving, we won't see that yet in 2027. So maybe it's actually would have been okay to put that plant there, but the water hasn't recovered yet. It might take 10–15 years before it actually does. So we'll have to wait even longer. Now, I'm going to add one more block of negativity, and then we'll try and move towards something slightly more positive. We did a nice little project with a local water or regional water manager in the Netherlands, and then our results said, well, in the current state, actually, it's pretty piss poor already. We don't really see an effect. So is there now a problem? And then their legal expert said, yes, but we are planning on taking measures to restore this state. So the question we should be asking is not, does it have an impact now, but will it negatively impact our chances to meet our targets in the future if we take all those measures? So you're not even looking at, is it problematic now? You're looking at, will it be problematic given the potential recovery in the future? Well, that seems very hard to prove to me. And then I'm the one that's supposed to be advocating for the environmental side, right? This seems problematic and essentially putting us in a state where, if we look at it purely from this lens, I would say in the Netherlands at current, with the current water quality we have, it's very unlikely that we're going to upscale FPV in inland waters in a meaningful way. That doesn't mean no one will get a permit, by the way. Yeah? You can still get a permit for certain locations, but it's very unlikely we're going to roll out FPV on a large scale in the coming years. If we approach FPV as something we want to do on water, we go ask for a permit, and the permitting will say, well, it's already bad. Can you prove to me it's not going to have any impact? So this is clearly not the way to go. So now let's see if we can find a way out of this. But let's also first acknowledge why that legislation exists. It doesn't exist to make our lives difficult. Well, it does make our life difficult, but it does so for a very good reason. Because that water is actually a very valuable resource to us. We use it for all sorts of things, from drinking water to swimming water to recreational activities. And if we don't have that water in a good ecological condition, it's actually way more expensive to use it for drinking water for society as a whole. It's not going to be able to supply the services we need in terms of swimming water quality. We won't be able to eat a lot of the things we take from that water. So there is clear reasons why we actually are striving towards those environmental legislative targets. We're not just doing that to annoy FPV developers. Just so we're clear on that. We're now in this conflict. Will we go for green energy goals and clean energy, or do we go for environmental goals and clean water? And that doesn't seem like a place we should be in. And the good news is we have a good starting point to start from, because in the end, both to some extent want the same, namely to address the triple planetary crisis. In the end, we're looking at climate change, pollution, and biodiversity loss, which is hampering both humans and nature. So it's not the case that it's only about nature or it's only about humans, it's about both. If we think about FPV, there's definitely a role for that, and as a global solution. It's just at a different scale. It's not about that local water body, it's about the planet as a whole. We're going to be able to decrease our carbon emissions compared to conventional energy generation. We're going to halt further climate change with a bit of luck. That in turn will help us to limit biodiversity loss globally, which is actually all the more relevant for freshwaters, because freshwaters are the ones where biodiversity loss is the most pronounced. That's not tropical rainforest, that is our actual freshwaters. So if we don't stop climate change, if we don't make that energy transition, we're in trouble globally. However, how do we then translate that into a local action, say in the Netherlands? Well, that starts by recognizing that we're essentially trying to do the same thing for the same reasons, only we're coming from a different spatial scale. To take it one step further, we have to put nature quite centrally in our understanding and in our way that we address this. So this is the Nature Futures Framework. The Nature Futures Framework is a framework developed by IPBES. IPBES is essentially the IPCC for biodiversity and ecosystem services. And it is based around recognizing the diverse value of nature for people in the broadest sense of the word. So both looking at the intrinsic value of nature, nature for nature's sake, say biodiversity because we want biodiversity, but also looking at what nature directly brings us as humans, but also accepting that there is a cultural and relational value of nature. And if we try and design our future visions for our waters with all these different values of nature in mind, we actually have a much better chance of moving forward. Now, if we make that more localized and concrete, what could that mean? Well, this is a very nice example, I think, from the Netherlands, where this has been operationalized not with this framework in mind, but in a nice way where it's about ecosystem restoration as well as incorporating solar panels. This hasn't happened yet. I'm really hoping something like this is actually going to happen. So we're looking at a part of one of the larger lakes in the Netherlands. That larger lake is not currently in good quality. There's all sorts of ideas about what's missing there. One of the things is shallow zones. So this plan says, okay, we're going to make these shallow zones. Within those shallow zones, we're going to make room for solar panels. And there we combine energy generation with ecological recovery. That sounds real nice. I also understand practically that means it's hard to do because this is not going to help your business case, right? So we really need to address this as a joint responsibility of the water management that needs to get to that good ecological state, combined with a plan to actually incorporate solar in that to also serve that global goal of clean energy generation. If we then think about how we could move one step further and use that to get to an upscaling, there's essentially two basic approaches to get there. One is, I would say, a more quantitative mapping, where we try and take all the things that matter to find the optimal placement in the place where solar panels are best placed in the Netherlands. Say, space availability, your governance barriers, where are those the lowest, what are the environmental constraints in different lakes and places that we could place them. And we do an optimization strategy, we throw it into an optimization algorithm, and geographically we come to a solution. That needs models. To be exact, it needs models that include both air, water, the plant itself, but it also should probably even go one step further than that, namely including a lot of the wider landscape context. We've seen some nice examples of first steps towards these models in the conference, I think. So we're on the right track to actually be able to do this in the near future. However, if we do so, we are missing out on some of the more contextual value. So at the same time, it could really help to also think about more of a qualitative approach, where we start from desired futures. What is it we actually want from our waters? What does that future look like? What's the place of energy generation in that? What is the place of water quality in that? And how do those two things come together? And then we're talking about future vision, but also things like use value, benefits for nature, benefits for people. And that could lead to a desired strategy of placement. These two can then start coexisting and feeding each other by, on one hand, more value-based design, and on the other hand, using the maps we create with our models to fuel that discussion. And in the end, it's going to be a bit of both. We need data and we need quantitative assessments, but we also need the qualitative negotiation that forms a part of the local and regional and national processes to get to optimal placement strategies. That's something we're currently trying to tackle in a large national funded project, where actually we found out we're trying to do both approaches at the same time. I'm not sure if we should have, but we're definitely trying. So if anyone wants to think along with this, has ideas about this, by all means, don't hesitate to reach out. We're very open to collaboration in that respect. And as the main takeaways, I would say the current legislation will not allow for FPV's upscaling in the Netherlands if we just approach FPV placement as a construction activity, because that construction activity is going to run into the legislative framework that's in place and the fact that we're just looking at crappy water quality. However, we need it at the same time. It is very important that we get this FPV upscaling underway. That requires integrated and joint work from both water management as well as developers, operators, and hopefully by doing so we can safeguard those values of water, both as a way to save on land, but also maximize the benefits for people and nature. And I'm seriously hoping we're going to get there. So with that, thanks to everyone that contributed to this, and of course also funding agencies and so on.
Thank you, Sven, for your presentation. I believe that we are going to have some questions in the audience. Lots of, as you can see. And let's start by them, and then we'll continue, okay? Thank you very much.
Yeah, thanks, Sven. It's very clear that there is, let's say, conflicting interest in water quality and our energy goals, and it would indeed be great if we can combine them. But if I look at the situation in the Netherlands, so far the Netherlands has been one of the front runners in floating PV, so permits have been given. Is there now a recent change in the attitude of water authorities towards floating?
I think the attitude has always been there. It's the deadline of the Water Framework Directive that is going to amplify that. What you've seen is that a lot of the permits went through the innovation departments, and they've been fine as innovation. The ecologists have always been giving heavy pushback from the principle, our water quality is already not good, how are we allowing this? Because, for instance, just for the perspective, if you want to build a small floater in front of your house, there's a good chance at current even that will not be allowed by your local water authority in the Netherlands due to this. So somehow we've managed to do much bigger floating structures under the principle of innovation, but that is going to run into a issue.
Hi, thank you. Sorry. No, didn't. Okay, just one question then about the legislation. Is this also applicable on, how you call it, on more bassins or man-made reservoirs that are practical use, let's say for agriculture or for water providing or?
Yeah, so there's two things there. Technically, yes, the legislation applies to everything. The Water Framework Directive is about all waters, not about the designated waters only, formally speaking. Practically speaking, the implementation of that will be different, but the rule that they cannot get worse will still apply. So, and which is the major issue, I think, moving forward. However, even if we would let that go and we accept, well, they're basins anyway, if we just look at the basins, the sand mining pits, etc., those are not going to give us the space we need to functionally upscale.
Yeah, I was just wondering, we're working with another project, another field of aeration and oxygenate more oxygen into the water. Would that be, could anyone help me to tell how much dissolved oxygen would we need it to offset the negative consequences? Give me a number of that, and we can see if we could, do something with the other technique.
Yeah, I think this is one of the ways that we need to start thinking, right? So we're having an impact. Great, can we compensate that impact in a meaningful way? But that shouldn't just fall to the FPV developer, I think, because it's not just because of that installation in its own right. We're already in a bad state. We should be going to a good state. So it's not just about the compensation in itself, but it's actually about true restoration. That's the direction I would like to see it.
Yeah, but that's where this technology comes from oxygenating waters that is totally dead. So that's where it comes.
Okay, can I? I'm a little bit puzzled by this. Always looked at negative impact, but in fact you could also have a look. The same as Lars said, it's easy to oxygenate, and you have the energy to do it. Otherwise, pumping water, oxygenating water costs a lot of energy. So the societal cost will be big if you want to make a better water quality. If you put floating PV unit, yeah, you have a cheaper option to do that. What you have to do anyway. But you have also a possibility to look at what are the positive effects. For example, I come from an agricultural research institute. Certain fish species have problems because the water gets too hot in summer. You cannot grow them anymore. Coverage with floating PV can help this. So there's also possible positive benefits. And that's a pity because I haven't seen any presentation which tells about something positive about environmental impact, which I think there also is. For example, I know a lot of waters, Belgium and Netherlands, I come from Belgium, which have problems with the exotic species, water crassula and so on. I even know in nature environments, the only solution they have, they simply drain the pond and then it dies. Then we have a lot of better water quality. It's simply not there anymore. If you cover it, the plant dies, the part which is covered. So I think it can be a lot more nuances.
I think there's, so what you're describing, I understand the underlying comment, and I think it's very valid because yes, we could be using this technology as a part of a restoration or a improvement measure, and we should. However, first we need to start reframing it as not we're gonna put something on your lake, because as long as we frame it as just another construction and not part of a solution, you're going to run into this legislative issue. So that's more my message. We need to reframe the way, the reason and the way that FPV has a role to play, not just as a construction, and yes, we want to make money for clean energy, but as part of a broader solution, both globally as well as hopefully also locally. Because otherwise, yeah, this is where we're going to end up. And I'm not happy with where we end up, to be honest.
Okay, so I think we have another question from the end, but then we have to leave.
When you're like comparing the water body's quality, is that compared to like a national baseline, or is it individually compared to like within that water body's targets?
Yes, so the Water Framework Directive implementation in the Netherlands has national baseline set for each water body type, and then they're allowed to be regionally set again for the specific water body. So they're starting off from a national baseline and then adjusted to the regional conditions. So technically speaking, all of these are already adjusted targets. So we're not looking at sort of, oh, we strive for this and actually that wasn't realistic. No, this is the targets we have very much set ourselves as the Netherlands. So we can't just shove this off on, well, Europe made unreasonable targets for us.
Okay, I believe that we could continue to talk with Stephen for all the afternoon, but we have a lunchtime now and a lunchtime break. So thank you very much for your presentation and for your answers and so on and so on. Thank you very much, Stephen. So just give me 2 minutes, okay? We are going now for the lunch break. I would ask you to be here at 2:05, please. We have the afternoon sessions to go on, and I wanted to start it on time, if possible. So please be here at 2:05, okay? Thank you very much. Have a nice lunch. So, hello everybody. Hope you enjoyed the lunch. I know that the conversation networking is quite good anyway. We have a presentation now, and we are starting with Andrés Franco. Andrés Franco is the CEO of EasyGenere, that is going to speak about the key learnings on design and project execution of floating PV projects. Okay, Andrés, the floor is yours.
Okay, good afternoon. Thank you, everyone. Today, I would like to speak and share with you some of our experiences in floating solar plants since 2008 when we started in this domain. I want to try to make this as real, life-oriented with specific examples, so hopefully you enjoy it. We started in floating solar in 2008 with the design of the first floating solar system, and this is the first one that we built in 2009. This project is in the south of Spain. It's still operational, but of course, with something and the first version of the technology, we have learned a lot of. You see that already things that are happening in these artificial reservoirs, like water level variation, and the structure needs to adapt to the slope, so it needs to be flexible. How to make it easy for people to do the O&M so that there will be enough buoyancy when they are moving. And we saw also, not after the first year, but after several years, we have seen some issues and learnings from the materials and the way it has been designed. EasyGenere, it's a Spanish company. We are a manufacturer of floating solar structures, and also we are in charge of the engineering of the floating solar structure and the anchoring and the mooring as well. We have a system called Easy Floating that we have already installed in different types of reservoirs, from artificial irrigation ponds, coral lakes, natural lakes, or even in hydroelectric facilities already. And as part of the idea of bringing the benefit of floating solar to the end clients, we believe in building an ecosystem of companies. We don't want to vertically integrate, but we want to be a specialist in the floating solar structure and work together with our clients and bring in engineering companies, EPC companies that are specialists in their own domain, and also bring in the bank, the insurance companies, and creating this ecosystem to accelerate the deployment of floating solar projects. We believe that if we try to do everything, it's going to be much lower. Better to partner with companies and not to compete. In 15 years, we have never developed our own projects, and we have never installed our own project. We bring other partners to do that. Basically, what we do in a project is the engineering design of the floating solar structure and the anchor and the mooring, and we work with the client of the optimization of the electrical part, because there are certain decisions that, depending on the preferences of the client, might impact the CapEx and the OpEx of the projects. We do the supply and the different material related to the structure and the anchor and the mooring, and then we train and do quality control on the execution done by the EPC company. Here you have a sample of some of more than 100 projects we have already built in 5 continents. As you can see, it's different type of reservoir, and I want to try to gather some of the experiences and conclusions related with the design and the execution of those projects. Starting with the design, what is important to keep in mind is that there is not a one-size-fits-all design. Depending on the conditions, and this is, of course, a simplification, but basically you can have like 3 types of projects that will be like a standard, advanced, or challenging, and I'm giving you some of the parameters that we take into account. Some of them might be relevant, for example, water level variation on the size of the waves that has also been discussed quite a lot. And there's another one related with the snow. And the message that I want to give you today is you should look at these parameters not on average. Many people say, well, on average, usually this reservoir only goes down 1 meter. The usually is not enough. It might be even a problem, because you need to design and to build a plant so that in the exceptional circumstances under design, the plant will behave well. We have even had cases, you say, okay, water level going down, but what about water level going up? So that's flooding. Now, that can happen, and there are many places that are susceptible. Climate change is making things more extreme, so you need to try to mitigate those risks. It's impossible to eliminate them unless you're willing to pay a lot of money, but you need to take that into account. So depending on the conditions of the site, there will be implication in many different aspects. So the type of structure that you're using, the surface, how much is going to be covered, if you really need to use a structure that is flexible, the anchor and the mooring, should we use large elastic system or can we do with a non-elastic? What are the pros and cons? Because in certain cases, there could be different options that you can use. And always, when you're looking at the design, take into account that you need to find the right balance for you and your project on the CapEx versus the OpEx. There can be certain investment in higher CapEx that will reduce the OpEx, and you can make the math on that one. But the most difficult variable to incorporate is the risk. Because I was having this conversation with somebody at lunch, they said, okay, but you could replace the item before the expected lifetime. Okay, if the plant gets to the expected lifetime and you change the components, that's perfect, just an extra cost that probably you already had in your model. But what if the components fail before the replacement? You're gonna have failure of the plant that's gonna be even higher cost and problems in the project. So let's talk about 6 of the main challenges that I wanted to share with you on design and construction. We have adaptability, we have the anchor and the mooring, the logistics and space, the tools and components used, the buoyancy, and also the electrical components. So starting with adaptability, as I said, climate change is becoming more extreme. When you look at winds, there are always these extraordinary events. I believe that Eurocode is not updated. It's not relevant for today's conditions. If you think, oh, usually Eurocode wind, it's 98 kilometers per hour. We have had in Spain and in Europe several plants that have even more than 130, 140 kilometers per hour. It's not what usually happens, but it happens. And you only need one extraordinary event with really strong winds that have not been taken into account to have problems in the plant. So on that, what we try to do is, why fight nature? So let's try to dissipate the mechanical stress, and that's why we started first with 10 degrees of tilt in the flow in the panels, and it was open. Remember the first picture I showed you. We have reduced it to 5 degrees of tilt, the PV panels. We don't do more than 5, and also we have closed the back of the PV panel. So the float is actually elevated so that the wind, when the wind is hitting on the PV panel, it doesn't hit on the panel itself. It's hitting on the float. So the float is a wall. It's not when the PV panel works as a sail. And in a floating solar plant, you have thousands of panels. All of them are sails. So you want to reduce it. And here you can, this is a calculation comparing 5 degrees with the closed back and 12 degrees with the open back. So the CP factor that engineers calculate on the wind load on the structure goes up by 440%. It's not 1040, no, it's 4 times higher. So why try, yeah, I know, I wanna do it at 15 degrees because it maximizes energy production. Yeah, but that means that depending on the latitude, could be 3-5% more, but you see how much you are increasing the load of the structure. And if everybody, you have heard, most of the industry is using HDPE floats, so the material, it's kind of the same. So if the material is gonna be suffering these loads. Another thing, the adaptability on the extreme changes in temperature or the snow that will create additional weight on the structure. This is an example in Germany, one of our plants, and the significant accumulation of snow. What happened when water level goes down? In this example, the owner of the pond, they wrote in a contract that water was never going to go lower than the black part that you see, that it was going to be above that level. That's what is written, but then reality strikes you and says, no, it went down in a severe dry season in Spain. They had to use the water. They didn't get the replenishment of the water. And the structure was able to sit on the slope, bending, given the design that we have that is flexible, that we'll talk about what is the benefit of that on the dissipation and the elasticity to not accumulate the forces. And you can see also that it was even on top of the tubes of the entrance and exit on that one. And it worked. And you need to think that that's going to happen more and more. We are seeing this is a project in Spain. You see even that there are bushes around. So it's not that there was a couple of days that they had no water. So there's for several weeks, and they haven't appeared bushes on the sites. And what happens at the bottom? Well, it's not flat like your bathroom, so it's full of mud. So you need to think on how are you going to design to manage this special condition. And probably the most extreme is when a floating solar project becomes a ground-mounted project. So this is, again, this is a dam. Also, by the government of the region, they said, by law, it's never going to go lower than X level. Until, again, a dry season, and it was a debate, what are we going to do? Are we going to use the water for human consumption and for irrigation, or for the hydroelectric facility? What do you think the politicians said? I have more boats with the population, so use the water, and this is what happened. And in this case, the client, we have advised them, look, why not put this farther away? Why not put this extra safety on water level variation? The client said, no, no, no. I don't care. It's going to be like that. And at least the client was consequent, and they said when this happened, yes, they said yes. It was us who decided to do that. You advised against that, so we're going to cover everything. But still, we don't want to have this situation. We want floating solar to be successful and that everybody is really happy about the project. So think about those exceptional circumstances. Another exceptional thing, you will never control what's going to be the water level of the place where you're going to be installing. You have an idea of what might happen. We talk about, in this case, this is a project in Latin America, in Chile. There is almost no water. You can see the bottom there, the rocks at the bottom. So the structure needs to bend all the slope to get to the bottom. And imagine in a big dam, that can also be very difficult to control. So we have had cases of projects that during the construction of the dam, of the plant, the water level has been changing. So need to change the installation area quite a few times to work in a productive way. And what about when you have not a lot of space to put it? So in this case, this is in the Netherlands. You see there's almost only 1 meter. So you need to build this type of a structure to bring the components and to do the installation and then to put it down. The bending that is happening here between those connectors is more than 45 degrees. If there is not a flexible connection between the floats, if it's more like the traditional, it will bend and it will get damaged. And in fact, you need to check out the warranty because sometimes the warranty, the company have a maximum tilt that the floats can bend. If not, you lose the warranty in there. And anchoring and mooring. You can start with the basic anchors and moor. If you have a easy place, you can go for onshore anchoring. You can use the traditional polyamide cables or ropes, or you can use chains. But what happens when you go to extreme conditions? This has been a real life 20 ton of concrete dead weight with spikes that we use in one of the largest dams in Western Europe. Why? Because the place where we had to locate the floating solar plant, it's not flat. It was in a tilt, and it's 70 meters of depth. We could have tried to go for other type of anchoring like helicoidal anchoring, but imagine the cost of sending divers to do that, and also to check later if the condition during the OPEX, what's going to be the cost? It's going to be potentially very high. So you need to take into account what's going to be the proper design, and again, not just on the CapEx, but also on the OpEx. That's why in challenging conditions where there is significant water level variation, we work with Cflex. We believe that in several conditions, Cflex is a really great option to maintain the tension in the plant, to reduce the peak power, and also to do things in an innovative way. Imagine that you have a floating solar plant in a dam. You could optimize the design with some mooring and anchoring that is not the traditional perpendicular that you see in many designs. In this project, if we were to use the traditional way of designing, we would be having 44 mooring lines. But with the combined use of Cflex and also putting the ropes, the mooring lines in a diagonal way, we were able to optimize to reduce it to 20 mooring lines only, and keeping that always at any time there would be 10 mooring lines working to support the environmental loads. So this is additional insight on that you can always try to fine tune. It might be that for the CapEx, I cannot tell you if this CapEx is going to be higher or lower, but think about the OpEx. If you have half of anchors and mooring lines to check, when you need to send the divers to do things, it's going to be much cheaper. And you're going to be doing that, and especially in challenging conditions like a big reservoir, quite a few times during the lifetime of the project. Third challenge on the logistic and space. Well, we are seeing more and more clients that they ask us about, especially for big projects, if they have enough space for logistics. We have built our system with the idea that it can be very efficient from a transportation point of view. So you can put one float inside each other. So this is depending on the comparison between 2 to 3 times less space than other technologies. And this is the installation area for a 7 mega project. You see that there is not a lot of space that is required. Maybe in this case it's not too relevant, but we are seeing that authorities in the environmental impact studies, they are asking more and more how much space will be clear of vegetation for installation. So if you say that you need a lot of storage and a lot of clearing, well, authorities will probably not look in a very nice way at the project. And also, if you need a lot of storage, you might need to get temporary storage to keep part of the material with the added cost of transportation from the temporary place to the site to do it, especially, again, in big projects. And also, you have the challenge that what if there is little space? So how can you, in certain conditions, especially in agricultural areas or places that for example, industrial projects as well, you don't have a lot of space to do the storage of the components. Talking about components, important, and again, think about the CapEx and the OpEx. We believe that you need to work with components that have been tested to sustain the expected lifetime of the system. This is the type of test that we have been doing. This is a real-life scale. So we are putting that, and we are replicating big waves. In this case, it's a 1 meter wave, but especially high-frequency waves. So it's one wave and the next one coming right after the other, because that's a great way of really looking at the fatigue of the different connectors and the components. And what you see is that basically the structure, what it's doing is kind of surfing the wave. It is not absorbing the mechanical stress in certain components, but it's more trying to dissipate the mechanical loads. We have also been doing a lot of testing internally. We have built specific tools to understand what is the behavior, and looking at 3 of the main tests that we check is tensile test, fatigue test, and wave simulation. So in the tensile, it's more about when are things going to break. It was mentioned at some point, I think it was in Lars' presentation on the connectors, what the maximum that they can sustain. So we can test what happens on the fatigue, the combination of cycles, but also by the forces that are put into the structure, and know what are the deformation. And we can adjust, we have been adjusting the shape, the thickness of the float. And the most important and interesting is this on the wave simulation, to actually have and replicate in a specific component different heights, and we can leave this by weeks to understand what happens after a lot of cycles and different frequencies and sizes of the wave. And when you go to more challenging conditions, imagine, it was mentioned, but I think the gentleman from India talked about the big waves and the wave breakers. In this project, this is a place that, given the fetch, you can get almost 2-meter waves when the wind blows really hard. In this case, we put a wave breaker that is made of ultra-high durable concrete that floats. Even with that wave breaker, you see all the movement that is happening inside. The wave breaker is out. This is a normal day, so the waves are not too strong. It can get much stronger. And even with the wave breaker, you're not going to kill the wave. You're going to reduce the size of the wave, but still there will be a lot of movement, and that means fatigue in the components. A few things that we believe it's important that you keep in mind during the construction and putting together the components. It's first, try to bring into the project EPC that already have experience with floating or at least working with water. Water, it's a different environment, and sometimes people oversimplify things, especially related with anchoring and mooring, the temporary anchoring and mooring. We have had cases where, let's say that the installation day, you see, okay, it's a nice day, we don't think nothing is going to happen. Weather can change very quickly. So you need to be doing the temporary anchoring and mooring similar to the definitive anchoring and mooring. Then it's important also that to bring the manufacture of the floating solar structure so that they will do some quality control at the end of the process. And finally, the maintenance. We see many clients that they say, okay, this is working, it's floating, why should I do additional maintenance? No, it really requires maintenance, and I know it's an extra cost, but the fulfilling and the full protocol of the manufacturer of the structure on the maintenance is crucial. It's really important to keep that in mind. If you don't have the numbers, ask the manufacturers to give you the numbers on the estimated cost of the OPEX. Put that in the model. You don't want to be saving on that part. Next topic is on buoyancy. Buoyancy is becoming much more relevant given the safety standards in the Western world. We want to move away from this type of buoyancy situation that is not going to be safe for people doing the O&M. This is the way we have designed it. You have here 9 people, and you see that there's still some difference between the level of the water. So that gives you an idea that you can install inverters, you can install the cables, you can put other components top, or even you can do automated cleaning with robots. These robots tend to weigh about 100 kilos. And what happens when you have all of that, and again, you get snow. So it's not going to be the normal operation, but you have all these weighty components, and then you get additional snow. So it's important, and the snow is basically physics. This is how many flows do you have, what is the volume of that one, and you can divide that by the amount of snow. So make that calculation yourself. And it's also relevant, the buoyancy, to facilitate O&M. If there is high buoyancy, people can move in a safe way. You can also, at some point, bring materials. You can carry things as if you were working in a ground-mounted installation. And this is relevant not just from a safety perspective, but also from a cost perspective, so that the operation of O&M will be productive. And finally, on the electrical challenges. Electrical, you can choose many different configurations. And how are you going to do the cable evacuation? Do I go for the most premium type of evacuation, where you have this type of trays that is very easy to access, that is not made of metal, it's a polymer, that it will reduce the fatigue or the potential problem that any metal tray might, with the movement of the water, start damaging the protection of the cables? Or how to install the inverters. Is there going to be enough buoyancy to support the inverter and the 2 people that might need to change the inverter in 5 or 10 years? Is it going to be a safe operation? The evacuation of the cables, there can be several options, but also, again, look at the local regulation and think about what might happen if water at some point gets in. and work together to make the design that from an electrical point of view will be optimal, but taking into account the potential additional cost of the CapEx and the OpEx. And you can also decide at some point to put the inverter, the central inverter, or in the water. That will add additional cost from the pontoon and also from the anchor and the mooring. You need to make the number. There is not one definite answer. We have done it as transformers in the water, but also outside. So happy to talk about those different challenges and what can be the best solution for your project, and to continue learning from each other and the experiences. Thank you very much.
Thank you, Andres, for the presentation. You are 2 minutes and 46 seconds later.
Thank you.
Anyway, it's okay. Any questions in the room? I believe that you were convincing. Fully. No, there is one question over there.
Thank you. Is there, you mainly produce the floats. Is there any chance of cost reductions with increasing volume for the floats? And you also say that each project is special, but of course, if you have enough projects, not every single one have to be special.
Yes, so the components at the end are going to be similar, 90% of the components. So it's just how you combine those components. And yes, there are economies of scale, mainly when you're talking about buying the raw material, if you put an order small or large. And also when you block the manufacturing of the floats, we don't produce them ourselves, we subcontract that. When you go to one of those companies and you say, I'm going to have your machines running the next 5 months, they're going to give you a better price on that one. And the third economies of scale, it has already been mentioned, is from an anchoring and mooring perspective. When you grow an island, you double the size of the island, the anchoring and mooring doesn't double because the perimeter grows smaller than the area. So you can, in larger projects, you can get economies of scales. And we have seen from 0.5 mega to a 10 mega that you might be reducing the overall cost in 50, 60%, compare the two options. More questions?
Thank you. Probably you already answered, but about the modules size. So I see that your floaters is for a specific module size, but you can vary depending on the modules, or is fixed?
Yeah, very good question. And we have a strong opinion on module size. We don't believe that you can go to any size on modules. Why? Because this is even happening in rooftop installations. You don't see the 700, 750 PV modules being used in rooftop. Why? First, this is done manual installation. So if you have 2 people carrying, it's more weight, and especially any light breeze that arrives when the people are carrying, this is a big sail and it's gonna fall, and there have been already cases documented of people injuries of that. Second, if you have the bigger the sail, the higher the mechanical loads, and the forces of the wind grow in a quadratic way. It's not linear. So you have a higher, so you're going to be suffering more with a bigger, and they're already manufactured like Longi, and they have released a report that they say that they don't use the M12 modules, because with the movement of the water, and again, the water is moving a little bit always, you're going to have this fatigue that might create micro cracks in the float. So they just don't build M12 modules. So we believe there is a maximum size with the current, let's say, technical specification of the PV modules. If they change it and do it in a different way, maybe we can use larger modules. Okay. Anyone else? Yes, gentlemen.
I think we have to continue. Maybe save it for the...
This is the last one because we have to finish, okay?
Thank you. Thank you, Andres, for a great presentation. My question is about grounding. How do you plan, like, if this is within the contractual requisites that the floating PV has to be grounded, there's the potential event of grounding. How do you plan for this for a safe grounding way?
So we talked with the client to understand what are the potential condition of the grounding. So if it's relatively flat, the system can adapt to that. But we have had cases in dams that in the past they had the town was there. So this cannot work if there is the tower of the church or there are big trees. The structure will fail. So it's important to talk with the client and to agree what are going to be the working conditions. Doesn't mean that we can adapt to any grounding. There will be some cases that we have said, no, we cannot give you the warranty for such conditions. Because, or if there are big objects below, it will not be covered. Okay, thank you very much for your time.
Thank you, Andres. Okay, and now we are moving to Mazen Bell. Mazen Bell is anchor lead from Spera, and he's going to talk to us about advancing concrete gravity anchors for floating solar. Mazen, the floor is yours.
All right, good afternoon, everyone, and thank you to LeadVent for allowing us to speak today. My name is Mason Bell. I'm a civil engineer by trade, and I'm the anchor lead at Spera. Many of you have already spoken with us at our booth outside the front door, but today I'll be sharing how we are advancing our concrete gravity anchors for floating solar. I'll start with a quick overview of Spera and what we do. Since I last presented in Berlin last year, we've changed our names. Many of you have already recognized this. We've changed from Arcam Technologies, and we are now named Spera. Spera is derived from spes, the the Roman goddess of hope, and terra, which is the Latin root for earth, which reflects our goal as a company, hope for the earth, delivered through better infrastructure. Founded in 2017, Spera's mission is to build a new foundation for clean energy, using advanced manufacturing to drive down the costs, reduce the environmental impact, and to support the local production for a portfolio of concrete products. Our core expertise lies in 3D concrete printing. This is additive manufacturing. We can flexibly create structural products that are customized to site-specific conditions and designed to maximize your ROI, all while avoiding the cost, the waste, and the emissions associated with traditional concrete formwork and steel structures. We also work with novel, low-carbon concrete materials and additives, which helps us reduce dramatically the overall carbon emissions associated with these structures. This approach enables Spera localized manufacturing using local labor and locally sourced materials, which shortens the supply chain, creates good regional jobs, and improves the resilience to tariffs or global logistics disruptions. We currently operate 2 research and development and manufacturing hubs, one in the Port of Los Angeles in California and one in upstate New York. We are also expanding internationally with 2 subsidiaries, one in the United Kingdom and one in Denmark. In addition, I'm flying to Jordan on Saturday this week to help commission our newest facility in Aqaba, Jordan. The purpose of that facility is still confidential, but keep your eye out on our LinkedIn. We'll be announcing it in the next few weeks. Those facilities support our material development, our reinforcement integration strategies, and subscale prototyping of each of our concrete products. This is everything that we need to validate and scale new products. Our New York facility is actually home to the world's largest 3D printer. It's 14 meters by 14 meters at the base and is modularly capable of, it can be modularly installed up to 25 meters tall. So it was originally fabricated to print wind turbine towers. We have 4 target markets as a company, starting with floating and canal solar, wave energy, port decarbonization, and offshore wind. While our team's background is primarily focused in the offshore wind realm, where we continue to develop the larger solutions needed, we're actively focused on the near-term markets with smaller applications that allow us to deploy now, demonstrate the performance, and build towards the scale. So as I mentioned, we have a product portfolio of concrete products. We're developing all of them, and they fall into 4 main categories. They're all, again, manufactured using the same machine, materials, and workforce. We've secured non-dilutive funding to advance each of these in parallel. The first bucket is anchors, which are designed for floating solar, blue economy applications like aquaculture and wave energy, and offshore wind. Second, we're developing concrete foundations, which include fixed bottom canal spanning structures for canals, offshore platforms for offshore wind, docks, barges, things like that. And third, floating platforms, such as our floating construction station, which last week we secured our first funding for to continue developing. And fourth, we have a subsea energy storage, pump storage hydropower technology, which is a pressure-based energy storage solution that is basically concrete spheres on the seafloor. Our anchor designs include gravity, suction, and torpedo anchors, which are all based on standard offshore oil and gas solutions, which are typically manufactured from steel. We're adapting each of these anchor types into reinforced concrete versions, which are more cost-effective, lower carbon, and better suited for localized manufacturing. Today, I'll be focusing on the gravity anchors, as I mentioned, for floating solar, which is our first product in the portfolio that's fully developed and ready for commercialization. I don't need to explain this to anyone in this room. We've said it many times today and yesterday. Anchoring in floating solar is a challenge. It doesn't just present technical challenges, but it's also a major cost and risk driver for floating solar. As we learned yesterday through the IEA PVPS Task 13, anchoring and structural components are the largest contributors to the 25% cost premium. In addition, anchoring and mooring also represents one of the highest failure points for floating solar. I think Lars's presentation yesterday did a good job of showing the floating solar floating away. Failure of a single mooring line or anchor can lead to the domino effect and the entire project being ruined. Now, in general, floating solar systems have two anchoring approach. One is based on the shore, and the next is bottom. Shore anchoring is more common for small or narrow reservoirs, but it can lead to crowding and shoreline constraints and environmental impacts that we learned about yesterday. Bottom anchoring, where the anchor is placed on the bottom surface of the water body, is preferred for deeper waters or multi-array systems, but introduces challenges with permitting, installation logistics, and overall cost. There are also hybrid systems, which sometimes combine both, which we saw in Andreas's presentation. But in either case, anchor selection plays a critical role in the performance, the durability, and the project economics. Now, looking deeper into the bottom anchor types, there's three main ones. This is going to be the helical screw anchors, drag or plate anchors, and then gravity anchors. Each has its own case depending on soil conditions, installation equipment, and the design constraints. Now, gravity anchors are typically used when the other anchor types are not feasible. For example, in rocky or soft soils, sites with impermeable liners, or where soil contamination or extreme water depth make diving not feasible. Conventional gravity anchors are crude, they're oversized, and they're inefficient. Most are designed with a one-size-fits-all or a few-size-fits-all approach, and casting using standard concrete molds, which also leads to excessive weight, material use, and installation costs. They rely almost entirely on their self-weight rather than geotechnical resistance, with little to no engagement with the soil. They're often overbuilt to account for uncertainty rather than for precision. And because they're typically made from solid concrete, they also carry a high embodied carbon, which becomes significant at scale when you have hundreds of anchors. So our approach to gravity anchors, addresses each of those limitations to conventional gravity anchors. So we offer a customizable, low carbon, and locally manufacturable solution for floating solar projects. By combining digital design and 3D concrete printing, we're delivering anchors that match real site conditions and not generic assumptions. This includes ballasted shells to reduce 65% of the total concrete, shear key skirts to engage with the bottom surface of the soil, like the tread of your shoe, and other features which allow us to improve the overall capabilities of these anchors. The first step is a digital design of our anchors. They're designed and scaled for the specific site conditions, including your design load, your mooring line angles, which would include your water level variation, and your soil type. This allows us to reduce the unnecessary mass, improve the geotechnical performance, and integrate the custom shear key skirt to lock the anchor into the soil, which allows us to once again tailor each anchor to every specific anchoring point. After each anchor has been digitally designed, That every file is sent to a 3D concrete printer, and it's uploaded to its system. The printer rapidly fabricates the shells. The shells in this picture here were printed in about 15 minutes apiece. They're about 3 tons total weight, so that gives you an idea of how rapid this manufacturing process is. And what's shown in this image is a 3D concrete printer located in a distributed indoor facility. But when projects get larger, you can also relocate your printer directly to the shore. This can be relocated almost anywhere. These systems are being mounted to the back of flatbed trucks. So if you can get a flatbed truck there, we can get a 3D concrete printer in there. This enables full-scale, on-site production, streamlining both your logistics and eliminating a lot of your transportation costs. Once the anchor shells are printed, they're filled with locally sourced ballast material, typically gravel or a high aggregate cement or high aggregate content concrete, and they're rigged with the required hardware for mooring line attachment. From there, they're deployed using the conventional marine equipment like cranes, excavators, or float bags, depending on the site and the installation equipment availability. As an optional design element, we're also exploring how to make these anchors more environmentally beneficial, not just lower carbon, but more actively beneficial for the marine environment. By incorporating specific geometries, materials, and surface textures, we can encourage marine biodiversity to thrive and grow on the anchor itself. These features are especially valuable in reservoirs or coastal waters where habitat enhancement is needed and required or desired, and they can be included if the developer or the permitting authority sees the added value. Next, I'll walk through how we've developed this technology over the past few years, from early prototyping and lab testing to a full-scale prototype fabrication, and what our next steps are in the development path. We started development in 2022 when we won a Department of Energy funded design competition for solar energy. With that, we were able to do the concept design, invent it, shear key lab testing with Sandia National Laboratories, and a half-scale prototype. Since I've presented last year, we've made a lot of progress as well. We've advanced to technology readiness level 5, developing in-house design software, ran geotechnical and structural simulations, and fabricated our full-scale prototype. And this is that prototype. It was designed utilizing design criteria provided by a floating solar developer on an installed floating solar project, has a 33.87 kilonewton design load, a 20-degree mooring line angle, and it was designed for sandy soil, so there's no geotechnical shear key. This anchor was printed in 55 minutes in our facility in Los Angeles, so a bit slower of a printer, but it's a smaller system overall instead of the distributed gantry crane you saw in that other picture. The next step to advance our technology is deployment, getting some concrete in the water. We're now focused on validating this technology and this anchor in the field under real environmental loads. This includes proof testing, integration with an actual floating solar mooring system, and long-duration monitoring to advance from TRL 5 to 7 and beyond. This is our current piloting opportunity that we're actively advancing. EDP has established a floating solar living lab at their Alto Robago site. It's at a reservoir in Portugal. It's been operating since 2016. It's got CL at Terre floats, Lars's C-Flex mooring lines, and 8 helical screw anchors already installed. This site is ideal for validation of our anchors. It would be in the extreme category, 60-meter average water depth, 30-meter water level variation, snow loads, and wind speeds up to 31 meters per second. We're now working with EDP to engage the Portuguese Environmental Agency to permit the installation of a 9th anchor at the array, which would be our gravity anchor. And in addition to pilot opportunities, we're here looking to collaborate with any of you in this room, early development partners, floating solar developers, technology providers, EPCs who share this vision of additively manufactured concrete gravity anchors. If you're working on a project and want to explore more, happy to connect with you at our booth outside. Whether it's performance, permitting, or carbon reduction, we'd love to talk to you. And thanks again for your time and attention. I'm happy to connect, and let's get these anchors in the water. Thank you.
Thank you, Mason, for the presentation and for keeping the time. Okay, thank you very much.
Made it up for us.
Any question on the audience?
Thank you, Mason. Normally, when a project is decommissioned, the idea is also that the anchors are removed, but if you introduce these biodiversity islands, is the idea that you leave the anchors behind when decommissioning the project?
Yeah, it'd be specific to the permit, and if you could convince your regulatory agency that that's, you know, going to make sense. But in my point of view, pulling that environment out after the end of its life is a harm to the environment. So I think there's an argument to not need to decommission an anchor if it's a reef.
Have you already discussed this with like water authorities or parties which give the permits?
We haven't yet. That's really on the next phase of getting into the water and validating a lot of this. We've started working with marine biologists to help us figure out what features and what textures are actually important to the native species. So you're not allowing a non-native species to thrive. You want to use, you know, you want to encourage the natural biodiversity of the area.
Yeah, it would be good to hear their view on this. So thanks.
Thank you.
Any other questions? If not, there is one.
Asking about costs again. Thank you for a nice presentation. Have you made any assessment or evaluated how much cost reductions you think can be possible?
Yeah, we're doing a lot of work to actively advance on that. We have preliminary cost models that we're not entirely confident with yet, so the early deployments will help us validate that. The ultimate goal is to match the cost of what the traditional block would cost. If it was a 10-ton block and we have a 6-ton anchor that's optimized, we'd hope to match the cost of what would be needed for that traditional concrete gravity anchor.
Thanks.
Thank you.
I'm sorry, that was more or less my question, so it's done already. So, no more questions. Thank you very much, Mason. It was a pleasure. Thank you. And now let's continue with Jasper Lemons, team lead global practices from DNV. That is going to do a presentation regarding the standards and the DNV design standards for floating PV floaters and mooring. The floor is yours. Thank you very much.
Thank you for the introduction, Antonio. Yeah, good day, everybody. I already spoke to a lot of you, so let's see, standards. The topic that you've been waiting for all day, all 2 days. Some of you at least, and expectations are high. Hope to manage that. About myself a bit, I'm indeed the team lead also of the solar team in DNV of Northern Europe. So spread over several countries leading the solar team and also global practice lead floating PV as a part-time effort. But still, I've been doing that for 7 or 8 years. As you know, let's see, where's the point? This is the pointer, I suppose. So the design standards for these for floats and mooring, as you may know, we've been working with several of you for 2.5 years on these standards. This is the year that it shall be published. I'll tell a bit about it. To be honest, I'm not the content expert. My background is in solar physics, the industry. So floats, materials, and especially mooring, anchoring. It's not. We have other experts, and of course also the consortiums. I'll tell about it later. But first, maybe about if you don't know DNV yet, 15,000 employees globally. 100,000 plus customers. So yesterday night I was doing the math. It's like 6.5 customers per person. I don't know how that works, but that's the average. We do in the offshore industry. We're a ship classification body, energy advisory certification in the digital solutions towards cybersecurity, and maybe also from the management system certification aspects. So myself, I'm from advisory, but funnily enough, the floating solar business that we do is going towards certification. I say towards certification because there's not real standards yet, so it's more about verification, validation that we do at this moment. And this is also something that we have been showing the last years several times to see which steps we're making on this path towards standards and certification. Maybe a quick recap where we started. No specific standards or best practices 2019, the well-known handbook for practitioners from by Ceres. That time we started also the recommended practice developments with the consortium, which led to 2021 DNV recommended practice being published on floating solar, with also not far after that technical reference from Singapore, or actually, yeah, also Ceres is involved. Here we go. Next steps: component standards. TÜV made this cable standard. And basically now we are heading at number 4 with this international FPV system design standards, say IEC, DNV. So actually it was 3 weeks ago when I met Thomas Reindl again at the Intersolar conference. He is also heading the group working on IEC standards for floating. It will take a few more, much more time, but I mean, he is also looking forward to the 2 standards I'm talking about today to incorporate or maybe refer to from IEC, such that we're not doing the same thing in different standards, you know. Yeah, it was, yeah, that was that. So the ultimate goal, of course, to have a framework of standards and methodologies. I was wondering, should I say something about why we do this still? You know, I think the whole room here is quite looking into quality, safety for design and durability. I don't have to show any more the pictures that Mason already did just before me. I was wondering, are they coming? I don't need to do that, but we know that that's the reason, of course. We want to have it to do it safe. And given the many players in the industry, like yesterday we heard the 80 suppliers, they are not all in the room, many different contractors and other parties. So it's a shared, I think it's a shared effort. I'll show you also. Several of us have been involved in achieving this. So, topics of today. I'll talk about the update of the recommended practice I just mentioned shortly. Then the 2 standards, one for the design of the floats for floating PV and one of the station keeping of floating PV systems, so the mooring aspects. Here is the one, the short one actually on the recommended practice update. If you don't know it yet, it's a broad kind of 150 pages plus guideline document addressing over 10 topics, from site assessment to decommissioning. So it's kind of a high-level document that refers to several other documents, being it other recommended practice or standards in DNV or outside of DNV, for example, ISO. Yeah, see now the updated RP is expected in the second half of, and I sent yesterday the new version, which should mention 2025, of course. With some updates in the yield assessment chapter, but also the design considerations and the floats and the anchoring and mooring parts, because those have to be updated, because with the new standards, we want them to be consistent to each other and refer correctly, and also not having double content. So where we go deeper in the floats and the mooring standards, we don't have to go, well, so deep as if we did not go so deep at the time, but we had to adapt it. Okay. Now, well, a bit on these 2 standards. Here is how it works. So we, 2.5 years ago, we started with this consortium. We developed with the consortium this a guideline document, basically. So we write it, we discuss it, workshops, we have a lot of interactions, and we end up with this guideline document. Then this guideline document is taken by us and transferred into a DNV standard. Maybe on the timeline on that one, and also for the other one, is that we are just finished. We're finishing with the drafting of the standard, and then it goes to our internal hearing, as we call it. So we have a house of rules and standards that really closely look at what we have produced, and then say we have to do these 100 or 200 things, change it, and then it's ready for external hearing. Yeah, so we are almost ready for external hearing. So in a few weeks from now, I expect that we can share this with industry. It will be on not publicly. Don't push it online for downloading, but you can one-on-one get access to it to provide final feedback on the final draft. So after implementing those comments, we will publish the standards, and that will be in the second half of this year. But I assure you those external hearing is coming soon. Yeah, a bit on these standards. So well, if you are interested, the code is STC 108 for the floats. It's roughly built up of 5 blocks. One background, although the design principles are quite important, I think, to set the scene for the whole standard. The second block is about the tools. That's really the preparation for the design and the checks that are being done in the third block, and then additionally some other chapters and appendices. First, let's have a quick look on the design principles that I mentioned. I think that is interesting to look at. So it looks at, okay, what do I want to design for? What kind of, we call that consequence classes. So you have on the right side of the table, you also see the same economic, political consequences, environmental pollution, or human injury and loss of human life. So there are different categories or classes of the consequence in these in the standards, from low, medium, high, very high. And we try to relate that either to the RP, recommended practice, or to, for example, Eurocode. So this is the first step that being taken. The other one is location class. So that's that is in the standard based on the wave heights. And for your reference, it's mainly inland waters and nearshore applications that we're looking at. And the classical sentence is that for offshore, you can use it still as a guideline. But that's basically how we, look at the consequence and location classes. And then there's the choices that you have to make now in the beginning on the design format. So you can use a partial safety factor methodology or a structural liability analysis. That's mainly referring to the table on the right side, or have a limit states approach. And all these the different ways of approaching the safety and the design, so that. And here the design approach, I must say, you can have it done by calculation or by component testing only, which is specific for this floats standard. Let's go back to this slide again, and I'll now just have the highlights on the right side. So with the design principles I discussed, then the tools, so to say, the design basis. This is basically a very detailed. It says that you have to have a detailed description of the system. So product description, but also looking at the different life cycle phases, these consequence and location classes, functional system requirements, and also loads and actions. So this is a starting point that we expect there, and this, for example, also that we review in the verification projects that we do for technology providers that start with, hey, can you help us with looking at our product? We start at the design basis. The next one for the floats is, of course, it's the materials that are used. One part on metals and concrete, and also one on polymers and composites, either non-reinforced polymers or fiber-reinforced polymers. Many details in them, so I can't treat them now for the sake of time. The failure mechanisms I'll skip a bit. I think it's explained for themselves, but still important to have a look at. The structural analysis methods is the part to say, okay, which procedures will I follow to obtain the loads and to calculate the load effects on the structure. This is all input to checking the design in the end. So, okay, this is what you do. Now you're going to do like, okay, I've made a design, I have my criteria, and does it comply? Does it fail or does it not fail? That's basically what's is being done here. So we're looking at the requirements for floats, the structural elements, connectors, and this is actually quite a broad, longer part where this actually design check is being done. Then this is the last thing about this standard actually here. What I said, okay, there's also part of prototype test requirements, so not only the theory, so to say, but also for prototype, and also the option that if you can't do it for some reason, you can also leave it by testing the components, but with the limitation, of course, that it only will be applicable for the test conditions that you have tested it for. Okay. Yeah, maybe some exemplary requirements. I mean, this is maybe not really into, yeah, it's a bit the obvious, I would say, if you work with polymers outdoors. I used it also 3 weeks ago at the Intersolar conference, where there's not much of floating solar people there, but polymers shall be protected by additives, by UV blockers, for example, and also have a qualification test to demonstrate sufficient resistance over the design lifetime to the sunlight. And yeah, this would be, for example, in the appendix of the standard, to elaborate a bit on. Okay, then go to the next one for the mooring. Again, a bit of a different, almost the same consortium, I'll say, but also we have here, for example, these observers that are independent knowledge institutes, basically, that have also looked during the process of the development of the guideline documents and also in the standard description. So, now, mooring, this is a bit on the scope. Also to provide the requirements and guidelines for the design of the station keeping system, safety, reliability, commercial success. It's a bit of the same of the previous one, but like I said, applicable to sheltered waters inland or near shore. And what is now the challenges? So the build-up is basically roughly the same. Safety philosophy and design principles. Again, we see consequence categories, limit states and safety. Environmental conditions and loads, mooring system modeling, that's a challenge to address. Also one for extreme environmental loads, and the last part on equipment. But I think part 2 and 3 are the main is the core of the standard. Again, here, these design principles. This is the methodology for establishing the load effects on the mooring systems. The definition of consequence classes comes back. Again, you see the same economic, political, environmental, and human injury classes. And the design of it can be based either on the partial safety factor method and reliability-based design. So there's one lesson for the floats. If we look in this to the second block, it's about the environmental loads. It gives a detailed description of what you should do, how you should look into the environmental loads and determine what they will be for the site. So drag and lift loads, wind tunnel tests, supplemented by CFD for wind. In the wave, there's things like mean loads, frequency loads, varying forces and model testing. But also for current, there is a flume test or similar as topics. So I'm not going into the details, I couldn't, but this is what you can find there. I think the third block, which was also one of the interesting ones, and that's been also main contribution from the joint industry project, and the research has been done and the analysis, is about how to do the modeling of the system. So you can have a numerical model of an FPV unit. That's quite simple, and you see. But what happens if you go to the whole system on the right side and you have individual floats or structures that may be combined floats or not with several PV modules on one float. But then it becomes a bit challenging regarding the computation time that it would take to do that. This is a bit of a messy slide, to be honest, but there will be some pictures. In the standard, there are some different approaches that you can go for. So, say sheet-based, group array-based, multi-body array-based, or part-based model. So the sheet-based, it also gives you guidance on, okay, when can you apply this? The sheet-based is the most simple one, just have one big sheet and do as if it's all fixed. It's more simple, but it's simplified as well. So there are some limitations on how easily you could go for this. The part-based model, that would only be looking at, like it says, a part of the system. But I think it's more interesting also to look at on the right side. Okay, what is there? Is there an intermediate solution to be in the sheet-based or the full multi-body array-based analysis? So the group-based one. Again, I did totally not do this assessment or the modeling, but this is at least what is how it's being guided in the standard. Okay, to make your choices on what you should do according to the outcome of the discussions of the whole industry project. Okay, so yeah, basically that's on a high level my summary of those two standards. I'm going to skip a bit the extreme environmental loads and the mooring equipment. I mean, that is for later reading, I would say. Like I said, call for action to finish the talk here. Both standards are going for the external hearing soon. And just contact us, anybody, me, or who you know in the topic to get invited to participate. Thank you for attention, and yeah, that's it. Thank you.
Thank you, Jasper. I don't know if there are any questions from the audience. One.
Yep, thanks a lot for the presentation. Very interesting. I have one question regarding if you have in one of the two documents, if you are talking about at some point installation, about some anchoring system, and about maintenance of either the floaters or the mooring.
No, I think it's really a design standard, right? So it's not really. I've you know, like I said, I'm not in the detail, but I have to go through the both standards in detail to see, okay, what should I present and what not. I didn't see. Yeah, I think actually in the floats there would be one on O&M as well, operational maintenance part. But I think in the moorings one, it's not. I didn't see it. There's also a bit of a difference in the length of those standards. So the floats one is like 150 pages, a bit less, and for the mooring is only 40 pages. But it's like, you know, that gives a bit idea. I think it's really good, both of them, but that's a bit also give you a perspective of what you would get if you get to read those. Yeah.
Okay, thanks.
Yeah.
Any more questions from the audience? I'll have one more, if you don't mind.
Sure.
We heard this morning all the developments that are being made in terms of offshore floating PV. First part of the question, will part at least of your standards, let's say that way, or golden rules can be applied to offshore, or are you thinking about the possibility of having their own rules, let's say that way, in the practices?
Yeah, it's a good question, and also interesting question. And when we started, and I think we're still there, is that you know, these standards we develop for industries that are a bit more advanced, and there are people and companies that actually can make a lot of use of it. So yeah, there has been a pull to go offshore, indeed, also with the standards. But we had to keep the scope, and also, you know, we have to keep it confined, because otherwise it gets really big, and that is that's why it's not yet there, and yeah, that's yeah, basically that's the answer on that one. So totally looking forward to also go offshore. We do provide offshore advice and, like I said, fire verification services. But it's too early to have a full global consortium of 25 companies that participate and everything. Yeah.
Okay. Thank you very much.
Thank you.
So, Jasper, thank you very much. It was a pleasure. Thank you. So, and to continue, before our coffee break, Benoit Vengade is going to his marine renewable energy floating solar from Inocea, and he's going to do his presentation regarding freshwater installation and construction.
Okay, perfect. Okay, so thanks for having the chance to talk today. I'm gonna talk about technical topics. Some of you may know a bit this point, some will not, but I will try to be as much simple as possible. I will talk about hydrodynamic. So we've seen both on offshore and inshore applications that we have a floating solar is a unit that is floating, that is moving, that is following water level variation, current, waves, etc. And I'm gonna try to explain a bit what are the different strategies to model this, the fluid interaction with the structure. Before this, so that's the summary, a quick introduction of our company, explanation of hydrodynamic in offshore industries and floating solar, and how important instrumentation, but also testing and gathering data is for floating PV calibration of methodologies and design. So first of all, our experience. So INOC is part of a large group called ABL. We are offshore experts, engineering and consultants on 3 main markets: renewables, maritime, and oil and gas. So we have a global footprint on more than 40 countries now. Here, the name of the offices are the renewables offices, and in red, it's the offices that are actively acting on floating solar. So the core of expertise is in France, but we have also an office in Ho Chi Minh that is looking at floating solar quite deeply, and also in the US, both North and South America. That's our background and experience. So we've been able to work on many different projects and studies over since 2017. Many different countries that help us to see different regulatory frameworks, different site conditions, different social, environmental issues, permitting issues, etc. So on some projects we see typhoon, on other we see old munition that have not exploded. So plenty of different conditions. Each project is really specific, and we've been able to work with different technologies. So we are not technology provider, supplier. We are not a project developer. We are a consulting and engineering company. Then, if I move on our services, so we tackle from the very early stage of prospection up to the detailed design and also to construction. So our main clients are developers, so IPP, owners of projects, development banks, and EPC. And we act with those clients either as owner engineer on our side alone, or in consortium with more experienced owner engineers that cover the full scope of owner engineering. Either we act as independent engineering, so we are able to tackle some specific mooring and anchoring design, for instance, and hydrodynamic design. That's what I'm gonna talk about after. Or as general consultancy, so tendering, costs, management, etc. Our main core of expertise on floating PV, so it's hydrodynamic, hydraulic, geoscience, electrical, and site supervision. And the last one, more on the construction side, so our owner engineering or EPC advisory and support, but I'll let you look at this in the presentation that will be shared later. Yes, sorry, on the operation part, it's also interesting. That's what I will talk a bit later on instrumentation monitoring of FPV farms. So okay, let's move on floating solar. So the last few years, during different presentation and events like this one, we've been able to present sort of segmentation of floating solar
type of reservoir. So that's a list that is probably not exhaustive at all. But in general, for hydrodynamic, we try to segment those kind of reservoir in 2 or 3 type of families. So small lakes, large lakes, and nearshore and offshore. So why we do so? It for hydrodynamic, small lakes first. It can be very small dam lakes, but most of the time it's quarry lakes or irrigation ponds or industrial ponds. And we consider by small lakes that do not have dynamic. By dynamic, I mean wave dynamic. So if we just have 20, 30, 50 centimeters of wind waves, we can consider that we are in small lakes. So it means that this dynamic will not have a significant influence in the design of the floats, in the design of the mooring and anchoring system. So then we move on large lakes. It means when we have significant dynamic, so significant for floating PV and inshore floating PV, it can be considered above 50 centimeters. We can have, if we have, I don't know, half of the year, 30, 50 centimeters. We could be in between, but from operational and risk of fatigue issues, we are in between. But during extreme events, we can go up to 1 meter, 1.5 meters, even 2 meters on some large lakes, very large lakes. And then we need to take into account dynamic effect in the design, but also in the construction operation, and of course in the inspection and maintenance plan. I will not talk about nearshore and offshore hydrodynamic design a lot. It has been tackled by TU Delft earlier today, but I will make a bit of comparison from how we try to inspire our methodologies of design from offshore industry. That's a bit what I will not focus a lot on those 2 slides. Sorry, I come back on this one. It's just the key results of our speech the last couple of years at this event on small lakes and on large lakes. So it's our key lessons learned. You will have all this in the presentation, don't worry. But it's our key message and key takeaways of the years before. So as a summary, the message to bring home of the last event were between small and large lake. On small lakes, we can consider that design is more simple from a development and technical point of view, whereas on large lake, it's more complex due to this dynamic. So in any case, we really need to invest and to plan the right survey, so geotechnical, bathymetry, wind survey, current, hydraulic survey at the right time in the development of a project. Sometimes it's the role of the developer to do it. Sometimes from a strategic perspective, it's better to let the EPC to do this kind of survey, but you really need to plan this to assess the risk of your project. Then on mooring and anchoring, so it's one of the major challenge on mainly large lakes. So I will come back on this later. And when it's complex, it's not because you have the right data that you use this data effectively. So you really need to have some experts to be able to interpret the data and how they impact the design of your farm. Okay, so now let's move on hydrodynamic. So yeah, why hydrodynamic is crucial? I start from the bottom. It's crucial for the design. So for the design of your floats, as Jasper has been explaining before, it can be extreme events. It can be also fatigue events due to operational dynamic, operational waves. So small waves that are here quite often. It's also very important for mooring and anchoring design that has been not covered by the station keeping that has been explained by DNV just before. But in general, we will see how we move from how we inspire our methodology from oil and gas and offshore industry and how we apply it for floating solar, why we need more R&D projects, why we need more data to standardize our methodologies and return of experience. So yeah, I'm gonna divide the topic in two situation that depend both on the site conditions, so on the type of waves, so the height of the waves, the length, the wavelength of the waves, and also the size of the floaters. So situation one, it's when we have the waves that have a larger, let's say, size than the floating unit. So we can easily understand that the unit will follow quite easily the wave. On the situation two, it's when we have not necessarily small waves, but it's when the wave's size or wave length is smaller than the units. This segmentation will help us to have two different strategies of hydrodynamic, and we will not use at all the same methodologies to solve it. So, coming from offshore renewables and offshore oil and gas, we have quite good standards, quite good methodologies, and 100, let's say, return of experience on those type of floating platforms. But most of the time, the points the similar points between offshore floating wind and offshore floating oil and gas platform is that we have one unique unit that is rigid, that we can call monolithic structure. So it means from a mooring point of view, if I pull on one side, the full floaters will follow. The size of it is huge, the weight of it is huge, but it's one unique monolithic structure. For floating solar, it's quite different. So we've seen plenty of different technologies the last 2 days, but even with the, for instance, solar duct that has one of the most rigid, that we consider the most rigid structure, when we assemble the different solar duct elements or both the one with each other, it starts to become different multi-bodies that interact one to each other, that interact with the waves, etc. When we move to Sealetter system or other pure floater system, then we have a sort of matrix that is following the waves, and we have hundreds, thousands of floaters that interact with the waves and interact one to each other. So we see that we have clearly different topics. In offshore, we can consider that hydrodynamic can be solved quite, not easily, but can be solved with the theory that solve the small structure compared to the wavelengths, whereas for floating solar, for offshore, and some technology, we have the same, I would say, the same way to solve the issue, whereas on very short wave period and pure floater technology, typically, we are on a different way to solve the hydrodynamic. So, yeah, that's different way to solve general hydrodynamic system or problem, depending on the accuracy we want and the computational efforts that is needed. A bit similarly as what has been presented just before by Jasper with the what he called the sheet-based or part-based. That's what I call analytical approach. So we simplify the problem as much as possible. That's very useful at first design, to design at early stage, at pre-feasibility, feasibility study. But it's also sufficient to use this kind of approach when you are on a very small lakes without a lot of dynamics. That's sufficient. You do quasi-static analytic approach, that's sufficient. When we move to a bit more dynamic, we want to go to potential flow theory, and that's very useful to solve the problem one that I've been sharing before. So very useful to solve big monolithic structure in offshore conditions. It exists also, you know about CFD, or you heard about it. That's very useful to solve very complex topics, complex interaction. But well, so in general for offshore, when we use offshore, but also for floating solar, we use those different approach. So at early design stage, to technology design for potential flow theory and for very fine tuning for CFD. The issue for floating solar is that today we are able to do analytical approach. We are able, or we are starting to be able to do potential flow theory. It means that for some technologies, now it's still not possible to do potential flow theory, and it will not be possible because for family 2 of the problem that I've shared before, it's not possible with potential flow theory. So I will explain how we can solve it just after. And CFD is very nice to do, for instance, some interaction between some floaters or current analysis below the floaters, but you cannot solve a full scale, I would say, with thousands of floaters, dynamic issue with CFD today without extensive computational effort, and even with this, it's not possible. So coming back to this slide, let's say that for floating solar, on the family 1, we can use potential flow theory. And in family 2, when we are on large lake, we start to be at the limit of what we can do. So what we try to develop, it's new models, new methodologies of design. I will not enter in detail in this one, but this one that we have published at OMAE last year, it's a way to discretize the multi-body element with a finite element model first, with the model analysis after, and then we move to frequency and time domain analysis. But just to show that we are still at research and development to be able to model a full-scale pure floater technology, for instance. What has been shared yesterday by Heliorec on hydrodynamic model, let's say, is still also something that is at research and development. Digital twins are not yet ready to be well, you understand. In any case, if I explain a bit more now that I've tried to vulgarize or to explain the different approach for hydrodynamic, in any case, in any approach, we need to validate those approach, okay? So for this, we have 2 main ways to validate the approach. Either we use tank test, or we use site instrumentation, or we use both of it for sure. So tank test is very useful for technology design, technology maturity increase in their design. Instrumentation, it's more to validate the design methodology after the first pilot and demonstrators. What we can measure plenty of things, site environment, but also mechanical stress, connection, mooring, anchors. That really depends on what we want to focus. I'm talking about only mechanical instrumentation, not about ecological. That has been very well covered during this event. So us, for instance, at INOC, that's the kind of things like TU Delft is doing. We are doing this also on our own tank test and instrumentation. And the last 2 slides, I will explain some instrumentation projects where we are currently involved in. So there is one that has been finalized this winter, where you have a nice report. This is a link free to download. So we've been able to do some research through the Trust PV research project, so European project. We've been able to put some instrumentation on 2 sites in France, one of Urbasolar, one of Sergi, so 2 developers. So one with Sungrow technology, one with Ciel et Terre technology. We put instrumentation on the mooring and on the mechanic, so on the float, to be able to measure the motion, the acceleration of the floats, the tension in the line, etc. So to do so, we define a strategy of instrumentation, what we want, what data we want to collect. Then we wait a year to have sufficient data to make some statistical analysis. From this, we've been able to identify some inspection that were needed at some point of the farm. And we've been able also to correlate the results with the design that has been done, so to see if there were sufficient mooring lines, if the fatigue was well assessed, etc. And to validate the model of the design that was used, and to see the CapEx-driven improvement that could be done for the design at later stage. So what has been over-designed, what has been under-designed, and if we have to redo the exercise of designing from scratch, what we would change. So all this is explained and publicly available, so I invite you to go through it. And in continuation to this project, we are involved in another European and French granted project named Steward, where some of you are part, like Heliorec or Fraunhofer for the ecological instrumentation. We are responsible of the mechanical instrumentation. So as what has been shared by Théophile yesterday, we are responsible of the instrumentation of Heliorec pilot project. So it's a nearshore project. So we've been able to install different sensors, and we start collecting the data these last few months for a period again of a year. And the goal in parallel is to build a full hydrodynamic model with different, like at least 2 different ways to model the farm. One that has been shown by Heliorec yesterday that seems to be used for digital twins, let's say, and one with our new methodologies that I shared before and that we published an article on a year ago. And yeah, we are just waiting now to confirm and to play with the results, or to analyze the results and to compare it and to try to calibrate our different models. Against all this, the goal is to share the results with the industry, to make some publication and to raise the knowledge of everyone on those topics. So the message to bring home here, FPV is moving to more and more complex environment that needs hydrodynamic modeling that was not needed at the beginning on very small lakes. Numerical model can help, but they need to be developed, like new methodologies and new ways to model need to be developed. Calibration of those models are necessary, and for this we need tank test and complement this with in-situ data. And yeah, I think that's the main message for me today. So yeah, happy if you have any question.
Thank you, Benoit. I don't know if there are questions from the audience.
Thank you for the presentation, very nice. In your model, do you have a limit of how many modules you can analyze?
On which model? On the, let's say, OrcaFlex typical model, or on the
elastic, this one?
No, for now there is no, let's say it's thousands of nodes, so there is no limit of it. So now we are just validating the model in the article with a very simple geometry that is not even floating solar geometry. But the goal is to adapt or to use this for thousands of modules to simplify this to a sort of mattress, deformable mattress that is split into different modal, as you can see on the second picture from the left.
Thanks.
So this might be early days yet, but what is your sense? Is this kind of analysis leading to a reduction in CapEx or an increase in CapEx?
On our report here, this one is to decrease the CapEx. So on this analysis at the end of the report, we see some over-design in this project. Typically, the over-design are the results of 2 points. The first one is the wind data. The wind data that have been used here are coming from Eurocode and are over-conservative because the site has some sheltering effect with the surrounding topography. So playing with site conditions is a way to reduce over-conservatism. And the second results show also some over-conservatism in the aerodynamic coefficient that have been used by the float technologies for this site. It seems that either the drag, either the shielding coefficients are a bit too high and yeah, are over-designed. So that's a good news for this project. We are doing over-conservatism, but it doesn't mean that all the projects have the same conclusion.
Any more questions? I have one, if you don't mind. We know that there are authorities, and especially to get permits to build, that are over-conservative. And normally when they are over-conservative, they go on the Eurocode and they say, look, the wind load that we are going to have is this one, and so on and so on. My question is much more, I would say, politic than scientific, okay? Is how it is the dialogue between you and those kind of entities. Normally, what is their acceptance of your approach on the opposite for the data that they are getting from the Eurocode?
Yeah, that's really dependent on the country, on the agency inside the same country. So, for instance, in France, in quarry lakes, we don't have issue with dynamic, but we can have issue with flooding. So we have high current and high water level variation. And so for this, there is some documentation that's part of the permitting that we have to respect. But there is also some additional studies and hydraulic studies that help to either tune or define the value of the amplitude of the magnitude of the flood. And so this, with a scientific or technical study, we are able to convince the local authorities. For wind conditions, for instance, that's similar for waves, because for waves in dam lakes, in large lakes, it's not covered by any regulation. So doing technical studies is, let's say, sufficient to convince the local authorities most of the time. For wind conditions, that is a driver for the CapEx and for the number of mooring that we will install. As you said, it's covered most of the time by civil engineering codes. And here it's much more complex to convince the local authorities. So we have some example where we have been able to convince them, doing some hindcasting, calibration with meteo station measurements surrounding the dam to decrease the value of wind speed design. But it's more tricky.
Okay, thank you very much. No more questions? Benoit, thank you very much for your presentation.
Yep, thanks.
So we have now our last coffee break. We have half an hour, I would say, of a coffee break. Let's get here again about 4:15. And so enjoy the coffee break. Thank you very much. See you in half an hour, more or less. So, hello everyone again. Let's continue. We are going to have a small change in our program because we have someone that has to take a plane. So we have to move the panel that was going to be at the end of the day. We are putting it earlier to allow that person to easily return home. So, but for now, we are going to have Jonathan Schreiber, that is Vice President of Development of Black Beauty Ventures, to talk to us about unsinkable floating photovoltaics XLPE foam floating bases. The floor is yours. Thank you very much.
Thank you, Leadvent, for having us, and thank you for being here at the end of a very long conference. I am from Black Beauty Ventures, BBV, and this is a case study of a 4.5 megawatt project, DC project, that we built that was required to cover an entire reservoir, including flanks. And just to talk about that and the associated challenges, just very quickly, to give background, we have developed our own proprietary floating FPV system for utility scale and large CNI projects. We provide a completely integrated solution from floats to anchors and mountings. And it is proven bankable technology that is operating today with real operating history. Also today with us is Guy Gavish. He's the founder and CEO. He's an experienced marine engineer who created the system after having 5 or 6 years of installing and maintaining FPV systems. We currently have 35 megawatts of projects operating, with another 37 megawatts on order for the coming year. Basically, our system is a catamaran configuration. I'm actually lucky enough to have sort of a sample here, and it's based on solid floats. So you have four, generally in our standard configuration, you have 4 panels. For our 2.0 version, we recommend 550 to 580 watt to get the maximum efficiency in terms of materials. It is a line connected of tables, what we call them, connected by flexible hinges, which is anchored on one side, and the other side is connected to a floating walkway, which also serves as a protected cable run, DC cable run. We do have a newer system that can go as large as 750 watts. We're panel agnostic, and it's simply a decision of working with the developer to come up with the best solution for the project. Our manufacturing partner, whose material we use, is Palziv. They've been in operation for over 50 years. They have manufacturing in Europe and in North America. And they offer a 15-year guarantee for the product. So this is an example, a mini example of the solid foam. We've been operating for 5 years. We have yet to have to replace a float. We also have tight integration with SolarEdge, which provides a lot of advantages. It reduces balance of system costs. It reduces installation time and costs because of our ability to put together very long strings. And because you get to see down to a panel level, it also not only helps with the operations and maintenance, but it also helps with the commissioning. And it also increases production. We've been able to eliminate issues caused by mismatched panels. And very importantly, it's all done in a very safe cyber envelope. So for example, Guy can look at any project that we provide supervision for, and he can see down to a panel level. Our Some of our advantages are that we do offer shore-to-shore cover, even on uneven bottoms. In our project on the top left, that is, we actually custom cut a lot of our floats to land on different sides of the reservoir. We're also able to ground and take off from rocky and uneven bottoms. Of course, as what Andres said, it is within limits, but it generally is not an issue. And at the same time, it's designed to allow to adapt for wind speeds, where regardless of wind direction, the panels adapt and tilt and go flat as the wind gets higher, while at the same time, we have no right edges. We allow complete free flow of water within the reservoirs. So again, we have advantages of durability. Our flexibility enables us to have a lot of synergies with the reservoirs, and we do have cost savings in terms of easy installation and lower volume of shipping. But now to the Mitzpe Ramon project. Here, this is an aerial, a drone photo when they're just about to put in the last line. So you can also see how the tables are put together in a conveyor belt on a very small area and then pushed into the reservoir and then anchored. So we were supporting a developer who had to win a competitive bid for a 25-year lease from the municipality that ran the reservoir. And the incentive was a fixed-priced PPA worth about 6.2 cents a kilowatt hour and automatic grid connection. But it was going to be a 3.5 megawatt AC connection. The reservoir, that is a mistake, is actually the area, water surface area is about 37,000 square meters. The flanks are at a 15-degree slope. The reservoir itself is 7 meters deep, but there's a 4 to 5 meter annual change in water level, which for us is not that big, and compared to what other projects we've seen here and what they did is not that big. But they, generally because of the desert conditions, they were losing 1.5 million cubic meters of water a year. So the requirement set for the tender was that, of course, you could not affect the operations or maintenance of the reservoir, especially as the reservoir was a source of revenue, that this was recycled gray water that was sold for agriculture, and that there was a requirement to cover the entire reservoir. That was set by the reservoir owner. And our goal, what we were able to do, is enable Energy, the developer, to win the bid while offering a price that enabled it to get its 8-year ROI, which was its threshold, financial threshold. So challenges, of course, is first not damaging the HDPE liner, which would result in legal action against the owner of the reservoir if that were to happen. We had to maximize capacity to enable the developer to generate as much revenue as possible to meet their financial criteria. So we had to find ways to also install on the flanks and the ability of the array to change its shape, because as with the 15-degree angle of the flanks, as the reservoir would drain, the array would have to adapt its shape to the new shape of the reservoir. And we had to be able, we worked with SolarEdge because of this change in shape, you would have many different mismatches due to different angles of the sun, while you wanted to have as long a series of panels as possible. So we worked with SolarEdge on solving that issue. And of course, we had to cover the entire reservoir without interfering with the maintenance and repair or operations of the system. So that was what we had to get done. So even though we don't serve as the EPC, we're a sub, we work with the EPC and the developer to design the project and develop solutions for most of the issues. So for example, the anchoring had to be in a way where it would not damage the liner or prevent access to critical parts of the reservoir for maintenance. And we had to work with our design to come up with the independent engineer for bankable production forecasts, while also working to answer the requirements for both physical security, because as we put this up, this area had not been fenced in, so it would have to be fenced in and provided physical security with cameras, while also ensuring that there could be remote monitoring in a safe way. I guess you can also see that the surface area is about 265 meters on 137 meters. And all doing this while getting it. And of course, working with the developer, especially in this case, we did side anchoring as the best solution. And just to make sure that all the geotechnical work and bathymetric work is done properly to plan that. And again, us working to build these key issues with the EPC and the developer. I don't want to go through them all and drag out the presentation. So a key part of it, of course, is the mobilization, equipment delivery and storage within a small area and manufacturing within a small area. You can see the assembly is done in a conveyor belt fashion on land and then pushed in. It's done row by row. And we have found that as teams get more experience in doing that, that the rate of installation increases dramatically over the entire length of the project. And while we don't do project management, we do the training and we do project supervision to make sure everything is installed correctly. And then before commissioning, we provide the final approval of the work, review and approval of the work. So even though we don't do the project management, we are not an EPC, we partner with EPCs, but we're working throughout to make sure that it has been done correctly. So here's an example of the flank installation when the water level is actually relatively high, and how it changes where you have different panels in the same series on the same, different panels in the same series at different angles to the sun, and how working with SolarEdge, we created a solution where each panel is producing at its maximum, and there's no situation where the entire series is being knocked down because of one panel that is either not operated or dirty or at a different angle, while at the same time enabling complete free flow of water, which also has the added benefit of not only enable us to adapt for wind speeds, because this is on a high desert plain at about 800-meter elevation, but also the additional space and wind current helps with the cooling effect, although there is less of a cooling effect because the water here is pretty warm in the desert. So in the end, we also have to provide, as you can see on the bottom right, access to each of the panels and between each of the panel for maintenance and preventative maintenance. We have online constant monitoring so we can be proactive about maintenance and seeing if there's an issue with any of the panels. And this monitoring is also done securely, but also helps the client, the developer, keep track of their production and make sure the utility is paying them the right amount and paying them on time, because the utility needs reminding constantly. So the achievements, the project beat the deadline for construction set by the utility. It was completed several months before, or more before, the interconnect was ready. It has exceeded the independent engineers' PVSys production estimate by 5%. So it has, I think, the last year produced close to 8.4 gigawatt hours, which is 1850 hours of production per kilowatt DC, and has reduced water loss by evaporation by as much as 30% or more. There's an argument about how much that has, but the reservoir operator has been able to increase their throughput, and therefore the reservoir operator has been able to increase their top-line revenues from the sale of water for agricultural irrigation. And for us, it was the first project to cover an entire reservoir, including the flanks. So altogether, it was a 4.5 megawatt DC project going into a 3.5 megawatt AC. And that was found to provide the best balance of production versus cost and the highest ROI for the customer. So that has become, for us, a standard of oversizing the DC. You do get clip power, but overall, it's the highest return. We used 8,194 Jinko Solar 550 watt panels, 41 of the 90 kilowatt SolarEdge inverters. We are now in our latest projects using the 330, which can have strings of up to 80. Together with optimizers, there was 2,050 base floaters, and we got 60% shading over the reservoir. And we are actually producing last year closer to 8.4 gigawatt hours to the grid, about 1850, and that's with no cleaning. And again, overall construction from notice to proceed to grid connection of 7 months. So this is a view of the complete project next to the water treatment plant. These are more examples of projects where you can see where we're working on working reservoirs, revenue generating reservoirs, where we are reducing evaporation, but at the same time enabling the reservoir to continue to operate seamlessly and generate more revenue for the owner. So, thank you.
So, any question from the audience? 1, 2, 3.
Okay, again.
Yeah, I'm not sure to have understood exactly the float that you are sharing here and that we see on some picture compared to the very first slide where it was pipe. No, it was not.
Which? Well, I guess if I could get the.
I mean, you have only one. Yeah. No. Okay.
You see, so it's 4 panels, 2 floats.
Okay, but that's not. Okay, I thought it was pipe here, but it's those floats. Okay, triangular floats. Okay, no, that's clear now.
Yeah, and they do produce excess buoyancy where someone can easily work on them without it really changing their level in the water. We do have experience with that.
And what's the manufacturing? How do you manufacture blow molding or?
Oh, these are solid foam. It's cross-linked polyethylene.
Okay, that's the
So
foam.
If
Okay.
you want, we have some examples here or samples here, and you can touch
Okay,
it.
that's foam. Perfect. Thanks.
Jonathan, you mentioned the evaporation, yeah, 30% less, yeah. Can you quantify that or give us an idea per megawatt or per, I don't know, 100 kilowatt?
That
is
is
a rule of thumb.
We still don't have exact information. That is the number the reservoir owner gave to us. We have some people claiming it's higher, so we've kind of picked that number, but we've found that is a very it's been very hard to quantify exactly water effect and lack of evaporation. So in this case, we have functionally covered the entire reservoir, and our production has exceeded the IE estimate. But we're also seeing that, for example, some of our best producing panels are actually on the southern flank, so they're almost never in the water, but they might just have a better angle to the sun, because our generally standard, we go from 5% to 8%. You know, the first couple of rows are lower for wind reasons, and then as we get farther in and they're more protected from the wind, we go up to about an 8% incline. So there are some that produce better than others, and sometimes we don't have the exact explanation for that. We have a new project that we just put in where we're getting crazy good production, but they're very high winds there. It might be from that, you know, but it's very, you'd have to really create lab conditions in two identical ponds in the same position, completely cover it, and then do an example. You know, it's very hard to test. We're very leery about giving promising numbers on water effect and evaporation because it's very hard to measure.
Yes, I have just one question here. Using Solar Edge inverter, can you give us a picture of the price?
It's generally, a lot of times the EPC or the developer will buy directly. It's a combination of inverter and optimizers. It's generally more expensive, but we had one project, I think we'll talk about this in the panel as well. We had one project where someone bought a much cheaper inverter and no optimizers, but they had so much trouble commissioning that all the money they saved on the equipment, they spent plus on commissioning costs. And now they're going to get less production. So we're...
But if we go back to one picture where you have the reservoir and you have some modules on the side, right? I had another picture.
Well, yes.
Yeah, maybe this one. So what will be the difference or level of water between the one laying down and the one in the middle? Like,
well,
what can be?
Ironically, on the southern facing flank, those are our best producing panels.
No, I mean just how much can be the difference between those laying like this and the one laying down on the top of the water?
I think it can, what about, Guy, what kind of angle do you think the hinge can handle?
It depends on the daily, it might be the same, but because it's the same string and you don't have an optimizer.
I'm just talking
So
about
what's the physical angle, a Zavita maximale?
the difference.
In this reservoir, it's about 12 degrees, and the water is 0. So it's also the elevation to the sun, the southern sun, is when it's float, it's about between 7 to 8 degrees, and when it stands, it's about 14 degrees.
Is there a physical limit?
On the worst case, I just want to come to one point. In the worst case, where you have your worst case.
Place is, it depends where the sun is.
Well, no, the question is just physically,
10 degrees, I guess.
what is the most you can bend on the hinge? Let's say if you fall at a very...
The hinge is like 45 degrees.
How you deal with the cabling between the string? How?
It's copper cabling, and
No,
they have
copper cabling for the DC or?
DC.
Yeah. So between the panels, you're connecting strings because you don't have only 3 panels in one string. You have at least 28 maybe in 90.
There are two ways where you can do a cross, or you can have another follow-up cable. So if you have like two strings, all the strings go to that side, and that side there's the hut with all the inverters. So if you have three strings, you'll have at the end like 5 cables, and the last one of the last panel.
So you are putting extra length of cable to manage this movement, or because the DC cable, they can't be flexible.
Sorry, guys, I have to interrupt. You can continue that discussion after the session, because otherwise we are going to be completely late, okay? Sorry. There is the last question on the end. Just one more. It's okay? No,
Yeah, it's okay. Okay, great. Yeah. Yeah, thank you for this presentation. I think it's the first time that I see optimizers used in inland floating solar project. To my understanding, the reliability of those optimizers are not that great. So I was wondering, what is your experience with that?
We haven't had reliability issues with them, but they do offer rapid shutdown, so it makes O&M a lot easier and a lot safer. And again, that's what offers us the ability to not have a very long series of panels knocked down by no production of one. So for us, we've only had benefits for them, but then again, we've been inland freshwater on man-made reservoirs. So put that offshore under saltwater conditions, that's a whole different ballgame. But we're inshore and protected. We're not offshore. But so far, basically, for example, Guy can look at any of the projects from his phone and look down the panel level. And that has so far has only been a benefit for us.
Okay, Jonathan, thank you very, very much. Don, I will suggest that we can continue the conversation after that. So what we are going to do now is to move to our panel discussion. The moderator is going to be Joaquin Roop, and the panelists are going to be Aurelian Krog, Don Hagen-Dun, Pankaj Kumar, and Jonathan Schreiber. Please join the panel, and so have a great panel, okay? Thank you very much. Sorry.
Good. After all these exciting projects and nice pictures, yeah, with sunny Caribbean islands. Sorry, not Caribbean. Yeah. I guess yeah, back to the hard realities, yeah, of cost, yeah, and financials. Yeah, it seems it's always me, yeah, with these topics, yeah, on stage, yeah. But very happy and looking forward, yeah, to discuss, yeah, that topic, yeah, with the fellow panelists. CapEx management, effective strategies. Yeah. So I guess yeah, already from the agenda you can see talking about cost reduction strategies and also financial planning approaches. Yeah. I guess what came out of the last couple of days now, yeah, it's not only about cost reduction. Yeah. Obviously, it's about the trade-offs. Yeah, you have to take. Yeah. So I guess we're going to be very careful talking about cost reduction. Yeah, we have to keep in mind, yeah, well, the implications, yeah, in terms of the OPEX and well, also yield and all the rest of it. Yeah, but diving in, yeah, maybe just a quick introduction. Joachim Rapp, yeah, Apricum Group, yeah, strategy and transaction advisory. Maybe just a quick introduction, yeah, from your side as well, and then we are off. Yeah.
BBV, you just heard me talk too much.
I'm Pankaj from Quant Solar.
Good. Then let's start off. Yeah, cost reduction strategies. Yeah. Well, maybe just starting off with an example again. Yeah. What is or was the most effective cost-saving measures you've implemented in one of your projects as of recently.
Should I start?
Yeah, sure. Yeah.
Okay. From our experience, I believe that a lean procurement strategy is one idea which we believe that works well. That how do you procure your material? How do you place your manpower at the site? And accordingly, you plan everything. So that matters a lot. And apart from that, the other important thing is that how do you how do you engineer your project? Because there are many avenues where you can optimize your cost. So these are the two areas I believe that we should always focus on for a proper, and cash flow management, of course, is also very important, very, very crucial, that how do you manage your entire cash flow for the project.
Can you give an example on the design, design impact on the CapEx, real life example?
Sure. I can share with you that when we go for a big scale projects, say like 20 megawatt, 30, 50 megawatt projects, then how do you distribute the entire project into multiple islands? That's going to define that how many floaters you are going to use, how many structures you are going to use, and how is the cable laying arrangement. So an optimized design is all about reducing the cable length, optimizing the anchoring points, and about the floaters, structures, your time of execution. So all these are directly correlated to the proper design optimization.
Okay. Well, I guess also, there are conflicting interests between sometimes the different stakeholders, so developers and EPCs and investors, Any insights on that? How do you mitigate or how do you deal with that? Anyone,
It's challenging because we operate in an environment where we have a lot of developers that want to do a quick flip. So again, we had our experience where we wanted them to work with SolarEdge. They refused, and in the end, the project ended up costing more. So sometimes it's hard to explain that there's equipment cost and then there's overall project cost. And then, of course, the other things is getting enough scale on a project is helpful, and standardization is helpful, and trying not to over-design without being irresponsible.
Okay, done.
If you look at the North Sea, it's also, and you want to install large-scale projects, not small scale, then also you see that days offshore become very important. So how much mooring lines do you have, which weather conditions you can install those, but also the logistics. So at the assembly site, at a certain point you can not go quicker than what you can install offshore. So there it becomes a lot of, it's a complete logistic puzzle with the supply chain coming in and out, and that is also driving the design on large scale. Furthermore, we see for our design is that you have those steps in technology. For the first pilot I showed today, that's really a pilot, and you should also see it like that. And then, as said, at the end we did with the last truss, we did it in 1 day, but we should go 2 minutes. So there's still a complete step in automation, which in your first projects you cannot do, but how bigger the projects come, you have your own assembly lines, and that makes such a big impact on the overall cost.
Yeah, I think we talked about that in the preparation. Yeah, obviously there's a big difference between offshore and the onshore. Yeah, Aurelia. Yeah, I think you made a very good comment on that as well. Yeah.
Yeah, definitely. So basically for us also, we're at the pilot stage, and the floaters that you have seen are quite of a small project. But basically, I think the best decision making that we made was, first of all, maybe to under-optimize, for example, the anchoring design, but just to have the exact same procurement for everything, like standardize as much as possible, avoid any complexity, even if that leads to a bit of oversizing of the equipment. Then it was, just like you said, done basically preponing as much as possible everything that's related to project site. That's basically what happens offshore. What's onshore for the assembly part of things, it's always manageable, right? But if the anchors are not ready while the production line has issued the floaters, then you're in big trouble. So basically what we did is that we had the anchors, the very first, the beginning, sorry, of the anchoring process started somewhere between 1 year and 9 months before the deployment, just to make sure that everything would be 100% ready. And plus, in pilot projects, you don't always have the money, to do everything by the book. I think that's important to say that. You cannot necessarily afford the full geotechnical whatever that costs like hundreds of thousands of euros, and you have to take that into account. So that's basically trying to get the offshore part of the equation as much as possible under control and preponed.
Okay, so well, I mean, you made that point. Yeah, site conditions, make a big difference. Yeah, so we're back actually to the developing stage. Yeah, because that's site selection is a developer's decision. Yeah, at a very early stage. Yeah. So what are the criteria? Yeah, you could share. Yeah, with the audience. Yeah, for the site selection in order to keep that capex. Yeah, in check.
As for offshore, I would tend to say that there's of course the metocean conditions, everyone can understand that, but then the driver, if the site is suitable from a technical standpoint, then you can understand that very easily, right? Bathymetry, rough metocean conditions, you already know whether you are suitable or not. But then what comes into play is everything related to connection. Right? Just to give an example, to connect Megaset, that's 2 kilometers away from shore, we are talking several hundreds of thousands of euros, just because you have to have the onshore, we're using, an injection point that already exists, right? But you always have to add HV setup there, additional HV setup that costs a lot. You have to have the point where the cable reaches the shore. It's not exactly at the injection point, so you still have to bit of civil engineering, right, to bring the cable up to there. Of course, the cost of the cable just for 2 kilometers, you have a fixed cost of the cable installation vessel, even if it's small. All the relevant people in terms of engineering, for example, for 2 kilometers of cable, in fact, you pay almost, it's exaggerated, but you pay almost the same engineering cost as the 20 kilometer, right? You have to design the lazy wave, you have to design everything. So that's it. And so, yeah, I would really put connection first.
Okay, well, I guess talking about design once more, yeah, we've talked already about that standardization in terms of keeping the cost in check. Yeah, so for me it seems offshore might be difficult. Yeah, how about onshore? Yeah, what level of standardization?
It really depends on environmental conditions. That's where it can get tricky. So we're looking at a couple of projects that would have to be able to withstand 290 kilometer per hour winds, and that's going to cost more. The anchoring is going to cost more. We might have to limit the amount of panels per table to limit the force of the wind on each one, so that's going to increase balance of system. So that, in that case, that is significantly more expensive. But in some cases, for example, if there's high snowfall and high snow pressure, we might want to add a little extra buoyancy in, just to be case, and that might slightly increase the cost as opposed to significantly increase the cost. So, but it's site conditions which determine these things. And of course, assuming you don't have to run a 20-kilometer line to the nearest substation.
Oh, I would just like to add one point here that to add to the inland conditions actually, that doing a proper bathymetry makes a lot of difference in the beginning. If you have the right contours with you and the evacuation point which you have identified, there should be a match between that. Suppose the contour is far away from your evacuation point, then you are going to incur a huge loss on the DC losses and DC cables as well. So, those things, if we can connect those dots in the beginning itself, it makes a lot of difference. Suppose you have two options. So if both the options, weighing both the options with all this initial capex can make a huge difference in your decision.
Okay, so well, I mean, all these are obviously important criteria, yeah. But it seems like, well, you have to redo that on a project level, yeah, pretty much, yeah. How about, well, what kind of tools are you using, or what could you share as a best practice, yeah, to go about this, yeah, like decision gates or software tools, yeah, or well, anything else, yeah.
Yeah, I think the objective for us is to have a standardized platform with a standardized assembly method, which you can deploy all around the world. But for the project specific, it's always what's said. It's the cable, how to do that, how to do the mooring, anchors. Maybe you can reuse every project the same, but it's also a bit depending on sand conditions, and that will always be project specific. And of course, depending how bigger the project goes, at a certain point also getting, let's say, 10,000 kilos out of a platform, yeah, it makes a big impact on the LCOE again. So I guess when you go to very large projects, also the floaters you will redesign because on the LCOE it makes sense, but it will be very big projects.
And also, I think in the context of offshore, where we are all looking at, for the moment, small projects, I think that also what we are really what we are very cautious with is to, as early as possible in the project, predefine, the decision gates. What we decide is left deliberately out of scope, and do that out as early as possible in the project. That's where you raise the question of what are the budgetary estimates that you may have for different packages. What's really of important in the budgetary estimates, and that's also something, in fact, that's project specific, because as Don said, our technologies are rather the same, but if we are looking, for example, at the cost of, let's say, logistics in south of France versus trying to do the same in an island project, and it's not the same arbitrage at all, then you have to decide that early on for the island project, where you can wait a lot if you do that just in the Mediterranean in SET, for example. So I think that whenever we go to project, this is really the first thing that we try to get the full understanding is we have the standard decision gates that everyone has at the development, at the pre-feed, feed, etc. But then we try to anticipate as much as possible what we will exactly need for these decision gates, and it's very project specific, in fact.
Okay. Okay, any comments on that?
I mean, I totally agree with him, actually. He said just because every project is very customized, it's very specific, site specific, requirement specific. So every project has to be designed very uniquely, actually. So most of the companies, I believe, that must be having their in-house system, which evolve over a period of time. When you do more and more projects, get the input from the previous one and try to do the, improve it for the future projects. So that's how we also do, actually. We have the practice of building our in-house things so that, we can monitor the projects and the cash flow and everything.
Yeah, and coming back to my question earlier on, yeah, so is there any software tool you're using for that, or is that something custom built, yeah, you're doing based off experience, yeah? I mean, we all know, yeah, these big Excel spreadsheets, yeah, of course, yeah, which take ages, yeah, to develop and then to maintain, yeah. But is there any recommendation or anything you could share, yeah, with the audience, yeah, what you're using?
I can be the first to confess that Excel and Microsoft Project are great tools. So that's I'm the first one to do this confession.
Plus one, yeah.
Okay, yeah, just looking at my question. Yeah, we talked about standardization. Yeah, we talked about, I guess, yeah, extensively design choices and influence, yeah, on CapEx. Yeah, I guess if we move into the execution and the project management, yeah, I realize, yeah, not everybody is doing that, yeah, here on the panel. Yeah, but what would you say is a key competence, yeah, then or mindset, yeah, needed, yeah, from an EPC partner, yeah, to ensure, yeah, that the tight capex control, yeah, you've budgeted for?
My thought process is that the basic fundamentals remain same, be it a ground-mounted solar project or a floating solar project. The only thing is about the supply chain, say for the floaters, because the rate at which modules can be manufactured, at that rate, maybe floaters cannot be manufactured. So it has to be designed in such a way that you are doing everything simultaneously as the production is going on. You are carrying out the execution as well.
Well, that's a very good point. Yeah, I mean, what do you think actually? Well, I mean, it's always obviously the issue happens at the when you hand over, yeah, certain things, yeah, like for example from the developer, yeah, to then execution phase, yeah, to the EPC. Yeah, how do you make sure, yeah, that well doesn't have a negative impact on the capex planning, yeah, you've come up with, yeah.
Okay, if you ask me, I believe that. Proper planning in the beginning itself can solve this problem, so that later on you don't have any points left to be addressed, and that may incur you some additional costs at the later stage of the project. So if you are planning it well, then if you cover almost everything, I think that's all.
Okay, yeah, so no recommendation, or Tonya, you wanted to comment? Yeah.
Yeah, what we saw is also like the factory acceptance test and the site acceptance test, especially during the pilots. It's so important to take the time for that. So don't plan your operation to also the offshore installation too close to when your first platform is finished. It needs some time to really test, is everything there, does it work? Because if it's out there offshore and you have to tow it in, then the costs are significant. So better test up front than do it later on, kind of.
Okay, yeah, Jonathan, I think, yeah, you made a comment on that. Yeah, you're also very cautious about the role you're taking. Yeah, so I think it was you said you're not acting as EPC, yeah, but you're supervision. Yeah.
Yeah, we're lucky. We have our scope of supply, which we know very well, which is standard. I guess the key part is just quality assurance, both on the manufacturer, even though the manufacturer by this time should have it down, you still need to quality assurance on that. And then, of course, quality assurance on the training and installation. Because I think there was a time where Guy was working with an EPC that he had worked with multiple times, but they happened to send a completely unexperienced project manager. So while we're not responsible for keeping track of other people's costs, you know, it is our name on the project. So a lot of it is just, having understanding, have your hand on the pulse and see what's happening and hope people are not screwing up. So.
I have a very funny one on that. We used a very well-known towing company, okay, to do the towing and hookup and also installing the mooring lines. And the guys, they were used to polyester ropes, okay. So this one would tend to sink into the water, okay. But we had nylon ropes, okay, so they tend to float, which means that you cannot, they have dynamic positioning vessels, right? So they can navigate on the sea very precisely. But one of the guys, don't know why, he never managed. It's difficult to know whether the guy has already managed nylon ropes, right? He installed like tens of anchors, so you tend to think, oh, okay, it's fine. But then you need to go very detailed into the gap analysis, because the guy, he went reverse with the boat, the rope inside the propeller, exactly, bing, no more rope. And in the installation phase, and basically this is the kind of stuff where you're like, okay, I'm gonna shout at him for sure, but then beforehand you also need to make sure that everyone has really, in the deepest detail, the very same understanding of what's being done, what's the slightest difference to what they do, and that's a lot of. It's not just coordination, right? It's really being cautious about each and every detail, and that's an example why we were super happy to have kind of design some of the mooring lines so that they are all the same length exactly, even if hydrodynamically speaking it was not needed. And so we had just one spare, but as they are all equal, then it works, and then we could do the operation still, even with that kind of event. But yeah, going very deep into the details with the subcontractors, very important.
Okay, so it's the planning for the execution phase basically as well. Yeah, but well, question is, how do you budget for that? Yeah, or I mean, at some point, well, if there is a cost overrun, somebody has to pick up that cost. Yeah, so how do you budget that, and how do you divide responsibilities?
I don't know what the Don or the onshore colleagues would think of it, but basically for that, I don't see that as a budget topic. You can always say, you are to pay for the next round of inspection. We didn't have to do that in the end, right? And we are all far better off with, just the thinking of let's standardize everything, just have one spare, and further on go deeper into the details with the contractor. But I wouldn't say it's even budget, because the cost of the rope I can't remember, but it was not that much in the end, you see. But I think it's beyond budget. It's the whole mindset, and that starts at engineering, in fact.
I guess that's about the collaboration, between the different stakeholders. We touched on that topic and the importance. And at the end of the day, then, well, if there is a cost overrun, obviously it needs to be either divided up, or an agreement needs to be found.
Making sure you have good contracts. That's coming from an American. Yes.
Well, I guess that's standard. All over. So, well, we've got almost like 15 minutes left, I guess, from my point of view, I would have only one topic left, which is at the end of the cycle, decommissioning costs, in terms of budget. But maybe we can open the discussion also, to the audience, and see whether you have any questions, we could address live, and then we come back here to the end of life topic at the very end. So, any questions from the audience? Looks like everybody is tired. All right. Well, then I guess we can come to the last topic, decommissioning. Well, I'm wondering, or the question is, is that factored into the capex calculation or the budgeting typically, or is that something which is, well, not really taken care of?
I think none of the floating solar project has been decommissioned yet, actually. So presently all around the world, everybody's talking only about the execution of the project. So I think decommissioning, I've never heard any word. For the first time I'm listening, actually.
On our side, the decommissioning actually comes because it's pilots, so the lifetime, is reduced for the project, and you have legal framework where you have to have a certain amount of money for the decommissioning. I think it's a bit the same still as what you say. For example, if you look at offshore wind, not that many, maybe none offshore wind farm that came recently into operation. They didn't get decommissioned. In France, it didn't happen. Netherlands, probably not also. So there's not much there. And plus, what we are looking at is also trying from the engineering also to get some lessons on what basically wouldn't be decommissioned in the end, because there's always this framework of, you have to have a budget for decommissioning, but in fact, right before decommissioning, what you would conduct is an environmental assessment of the decommissioning, and do we really want to decommission? So there are examples where, in fact, some interesting biodiversity has colonized whatever or subcomponent of the farm, and then you would like to put it to leave it in place. You wouldn't like to disturb too much the seabed by removing the anchor at any cost, while in fact it could stay there. So what we're trying also to anticipate for future deployments is also to which extent the choices that we make since the engineering would reduce, in fact, and it's a good argument also towards the customer, would reduce in the end the probable cost of decommissioning.
Okay.
Yeah, and in the Netherlands there are also some rules about it, that you need to take everything out and that you should budget for that. But indeed, it's a bit depending. There are some anchor companies which even add ecology to it, so then you could have an argument to leave it there. We did some calculations on it, and it seems that the residual value of the platform itself, the steel or the aluminium, that is more than the tow-in operation and the decommissioning and the scrapping itself. So it's more or less neutral, I would say.
Okay, or it could even make sense here actually, to, well, not scrap it or leave it, whatever.
Yeah, that's of course a different thing based on your sensors. You could also after 30 years say, hey, maybe we're going to replace panels, but
repowering,
powering or something like that. Yeah.
The best thing about floating solar, which I believe, is that if you compare with ground-mounted solar, that you leave zero footprint behind at the end of its life cycle. And that gives you the real estate once again for the next use. So that itself makes it a very attractive proposition, because that is not the possibility in ground-mounted, where you have thousands of piles, concrete piles. So that's a big difference.
Very good. Yeah, I think we're leaving that on a high note. Yeah, I guess last chance to the audience to ask questions. Yeah, if you have any.
Yeah, for polymer-based floating system, it is recyclable actually. So you can very much recycle it once you're replacing it with the new one. Yeah. So that is for sure. For metal also, I think same thing up.
Yeah, it's polyethylene. So both ours and almost everything that's blow molded, it's like a milk jug. So it's not PVC, it's not something with vinyl chlorides in it.
Okay. Any more questions? Everybody seems happy. Good. All right. Thank you very much.
Thank you very much. Thanks.
Thank you very much.
So, yeah, that's mine. So, thank you very much for the people of the panel and for Joaquin to have taken care of the moderation of the panel. We would continue now with Paulo Cheinho. Paulo Cheinho is the senior offshore electrical engineer of WaveEC Offshore Renewables. He's going to do a presentation about electrical operation and management strategy in offshore floating PV systems and to do a comparison between string and central inverter designs. Paul, the floor is yours. Thank you very much.
Thank you, Antonio. Hi, everyone. So my name is Paulo. I'm an offshore electrical engineer at WAVEC, Offshore Renewables. So today I'll be speaking about offshore PV, operation and maintenance, and electrical layouts. I'll be presenting a study that was conducted at WAVEC during last year by 3 of my colleagues. I'll be delivering the presentation, but the credit goes to them. And yeah, so I'll just start. Okay, just 2 words about what is WAVEC. So WAVEC is a research-based company in Portugal, Lisbon, that was founded in 2003. The original goal of the company was to manage and operate the first wave energy power plant, I believe, in the world. That was installed in Pico, and since then we have expanded our scope, leveraging from all the knowledge that we get from those initial years. We expanded our scope to other sectors as well, offshore wind, and more recently floating PV. We've also expanded our team. We are currently around 30 people with several engineering backgrounds and some economic backgrounds, environmental marine biology as well. At the core of our work is this knowledge transfer, so building bridges between the academia, industry, and public authorities, which we'll be doing with some success, I believe, in Portugal. Can take some of the credit for several of the pilot projects that have been installed in the Portuguese waters. And we have been already participated in more than 80 research projects during the last 20 years, delivered services for more than 60 clients all over the world. And we've built extensive network of partnerships with several institutions. Some of them are now part of our ownership structure. With regards to how WAVEC is organized, we have 3 core groups: the economy and business development, marine environmental and licensing engineering group, which I'm part of. So each one has its own core expertise and scope of work, but I believe that one of the great strengths of WAVEC is the complementarity between the different core expertises that allow us really to develop custom solutions, holistic custom solutions for clients for all the industries that you see there on the slide. So going back to the study itself, so what was the motivation to do this study? This was done within the scope of a EU-funded project that I'll mention in a second. So the real motivation for doing this study, as it's been mentioned throughout today and yesterday, being offshore adds a significant layer of challenges to what are already the big challenge of inland offshore, inland floating PV. Harsher environments, longer distance to shore that face weather constraints, longer transit times to get your components maintained. So we thought that, well, any design choice that potentially affects the number of components of your system potentially adds more failure events. So everything put together will probably affect the overall economic outlook of your project. So yeah, design choices that may be more common inland may not hold offshore due to this more harsher environments and more longer distance to get to your system. So our main goal and research question was to evaluate how different electrical layouts and O&M strategies affect the OPEX and downtime of a large-scale offshore PV project. We evaluated two types of electrical layouts, well, the two existing ones. String inverters, as you know, is a more higher granularity design. There's many more components. More components may lead to higher failure frequencies. However, each failure has a smaller energy impact.
On the other hand, the central inverter layout, you have more, or you have larger inverters, fewer of them, but each failure leads to a larger downtime impact. So fewer failures, but higher consequence. So which one is better offshore? Taking into account the maintainability and potential failures. We also wanted to investigate the different O&M strategies. Should we do immediate repairs? Should we postpone the campaigns? Should we group different maintenance campaigns together? So we wanted to test all this out. And one word for the project that funded this study, U-Scores is a EU-funded project that I believe was presented last year by our colleagues of NIMEC and mentioned yesterday by Pablo. The project essentially focused on demonstrating the potential for multi-source offshore renewable energy farms, so coupling wind with wave energy or wind with offshore PV in this case, and this is done within this scope. So the case study that we used was, the location is an offshore wind site, 85 kilometers from the installation in O&M port. It's a significant distance. So we've collected site-specific data for doing the weather analysis and resource assessment. For the system characteristics, we've received this data from our project partners, both the University of Uppsala, who designed the electrical layouts itself, and Oceans of Energy also supported on selection some of these components. So, well, as you can see, the different electrical layouts, we were looking for the number of components. This was the most important for our analysis. You have, of course, 6 times more components in terms of inverters and associated transformers than the central inverter one. So we essentially wanted to investigate or wanted to simulate how the operation and maintenance throughout the lifetime of a project would look like. And for that, we put together an operation and maintenance simulation framework. We essentially, for the maintenance strategy definitions, I'm going to speak in the next slides, but we, together with the project partners, we put together custom corrective and preventive maintenance strategies. As for the modeling tool, we have used our own that we've been developing for more than 10 years now. It's an open source tool. It's available on GitLab there. I'm not going to develop much on the tool itself, but we can speak later if you're interested. For this specific project, so you've used the following inputs. We had to know the electrical layout and the component specs in order to translate that to logistic requirements, namely in terms of what vessels would you need, what is the deck capacity, what is the lifting capacity required for those vessels. We've also collected failure rates. I'm going to speak about them in the next slide. Site-specific maturation conditions. We've collected the preventive maintenance plan from Oceans of Energy, I believe. And also some economic parameters such as vessel charter rates and the electricity purchase price that I'll mention in a second. So with these inputs and with our tool, we were able to obtain the total operation durations throughout its lifetime, both net durations and weather delays, site-specific, the timeline of failure events based on the failure rates, OPEX breakdown of each maintenance intervention, and downtime and energy losses. Talking about some of the key inputs and assumptions that we use for the study, I mentioned before the failure rates and the repair durations. So we essentially relied on onshore benchmarks because, well, that's what we had available. There's not much experience and long-term experience on using this components offshore, so we relied on onshore. We know that this will likely be optimistic, and offshore the conditions are different. So the repair durations will be longer, the failure rates may be also a bit harsher, but we use this for both layouts, so they are comparable. Our tool allows to distribute the failure events using different distributions, using bathtub reliability approach, so more failures in the beginning or the end of the project. Also seasonal biased distributions, so you have put a bit more failures probabilistic into the winter months. But for simplification, we used a constant uniform probability across all the years and months. And essentially applying this table to our case study, we reached some bold numbers. It's just some extraction of the full results that we got, but so you have an idea of the number of failures that you would obtain with these two types of different layouts. So as expected, you have more components, you'll have more failure events, 6 times more major failure events. And I forgot to mention that we've collected, so we've split the failure types in two main types, so the major failure and minor failure repairs. So the major failure requires the full replacement of the component, and the minor failure would require an on-site maintenance repair. And so here you see the total amount predicted by those the failure rates we mentioned before and the failure repair times. So 6 times more major failure events, 3 times more minor failure events, and 2 times more offshore or total offshore repair time. This is throughout the full lifetime of the project, 30 years project. So bold numbers, but again, as you can see, the string inverter the power capacity is much lower. So for each failure event, the impact on the downtime is much smaller. So you have more offshore time needed for repair, but the impact on the downtime is probably smaller. We'll see that in the next slides. So about, and that was not supposed to be there. So about the input and assumptions, so on the maintenance logistics, we have derived from the equipment dimensions some vessel types that would likely be able to do the maintenance interventions. We've selected the CTV with a specific charter rate. All this came from one internal database that we've also been developing for some time now. There's more than 3,000 vessels, and with specifications and the charter rates as well. So by knowing the equipment dimensions and weights and all that information, we extracted from that database the type of vessels that would likely be required. So CTV for the minor repairs and the working vessel for the heaviest component replacements. Also very important on the logistics side is the operating limit conditions. So in this case, together with our partners, we understood that 0.8 meters of significant wave height would be the highest operation limit that would allow for site maintenance. This is a very restrictive value, especially in the North Sea, and the chart on the right side shows the workability. And workability here, we've tried to compute the number of workable days that you would have per month on that particular site, and with these conditions. So a workable day is a 10-hour shift during daylight time with less than 0.8 meters of wave height. That was obtained with local site data. As you can see, in the winter months, you have much likely less than 5 workable days per month, which increases to 10 to 15 workable days during the spring and summer months. And well, this work helps to identify the best periods to conduct the maintenance campaigns and to understand well the overall difficulty of reaching your site or your project. Okay, so with regards to the operation and maintenance strategies, we've chosen 3, which I believe aligns with some of the discussions we had today about what kind of maintenance would you expect to have in these offshore projects. So the first one, and I think it was the one that was mentioned, is the deferred without replacements. This meaning that for any major failure, you're not replacing any of your components. So you just assume that you lose that component for life. But for minor repairs, you are conducting those repairs, but you are deferring them for a spring maintenance campaign. Spring being the time where with most workable days, so that you're sure that you can get to your system. This will likely have an impact, so you probably lower the OPEX because you're not replacing your components, but you have likely a higher downtime, but because you're losing some power production throughout your lifetime. The second one is a balanced strategy, so you're still conducting replacements, you're still replacing your components, but you're postponing them, you're grouping them in the same maintenance campaign. And lastly, and likely the one that will not be used, but we wanted to test the full spectrum, is the immediate reactive repair. So in this case, you will trigger a maintenance intervention as soon as you detect a failure. This will, for sure, increase the OPEX, but will for sure reduce the downtime. So with regards to the PV panel failures, we just assume that none of them will be replaced during the lifetime of the project. This strategy applies to the inverters, transformers, switch gears, so the other auxiliary components. Okay, so with the case study defined, the methodology defined, and the assumptions also defined, what did we find out? Some things not surprising, some others a bit more. So with regards to the energy and downtime, which we're calling here revenue loss, and I'll say why. So with the two layouts and the first maintenance strategy, and I remind the first maintenance strategy doesn't replace any component and defers the minor repairs. So as expected, you would have here an accumulated energy loss. So and for each year that you'll have more failures, you will accumulate energy that you will not be producing. By the end of the project, for the central inverter, you get almost 18 gigawatt per hour of energy loss, energy that you cannot inject in the grid, compared to the central inverter, which is around 12. So there's a 40% more energy downtime on the central inverter, which is expected because each failure, although fewer failure events, but more energy impact. This is expected. The black lines represent revenue losses, so the translation of energy loss to non-received revenue. And for here, we assumed a fixed price of 125 euros per megawatt hour. The black line is accumulated. The dotted line is a discounted value. So for the second strategy, the deferred with replacements here, it's more smooth because you're indeed replacing your failed components, but you're deferring some of the campaigns. So there's a few months where some of your PV panels are not capable to be producing. So again, there's a big gap of energy downtime between the central and string. And the last strategy, well, as expected, here you do constant intervention, so the downtime is obviously much lower. But it will have an impact on the OPEX, as you'll see in the next slide. This one will show the overall economic outlook, so both the lifetime OPEX and OPEX here means OPEX on the electrical components, so we're not doing the analysis of the overall OPEX. We're comparing the two layouts, so this is for the key components. And revenue losses. So there's a lot of colors. I'll try to explain a bit what it is, each one. So the green bar are the revenue losses. So energy that you're not injecting in the grid. So due to the failure events, the amount of revenue that you're not getting from your farm. And the other colors are the OPEX costs, and OPEX being charter rates of the vessels, the fuel costs, the technicians, spare parts, and port costs as well. So and you have the three strategies and the two electrical layouts for each strategy. So what can we read from this output? Surprisingly or not, the string inverter layouts are consistently more cost effective than the central inverter layouts across all the strategies. So the central inverter layouts experience fewer failures, but each failure has a larger impact, as we said actually in the beginning. So it does lead to higher revenue losses that outweigh any OPEX savings. And you can see, for example, in the first strategy, the OPEX is almost half in the central layout inverter. Yeah, there's much less failure, so much less interventions, but the amount of energy loss accumulated is significant, so it outweighs the savings. Even if you reduce the price of energy, the scale would be similar. So we think this is a consistent result. So looking at the strategies itself, so strategy 1 does result in the highest revenue losses. As expected, you're not replacing your components. Well, lower OPEX is offset by the major energy production losses, of course. But interestingly, compared to the second strategy, where you replace components, it is the most cost-effective, but by a small margin. So the difference between replacing or not replacing your components is not that large. And of course, we've used a lot of assumptions, and there's uncertainty together with those assumptions. So it was interesting to see that actually not replacing your components is not as bad as we would perceive initially. And lastly, the last strategy is, as expected, the most costly. It's mostly driven by the frequent vessel mobilization. The charter rates of costs are higher. You're probably maintaining during the worst weather months, during winter time. So it's as expected, much higher OPEX cost. The last conclusion here is that indeed what drives the OPEX costs, it's not the spare parts, it's not the technicians, it's really the O&M logistics, and here the vessels and fuel, essentially. So this reinforces the importance of grouping the maintenance campaigns, ensuring that you optimize the use of the vessels, especially for sites that are offshore, and the transit distance on this site, which was 85 kilometers distance, was around 2 hours, just a transit. So for a 10-hour shift of maintenance, 4 hours would be lost in transit. So it's very important to ensure that the O&M logistics are optimized. Well, we did a small sensitivity study. Well, we did several sensitivity studies because we were aware that there would be a lot of uncertainty on the values that we've inputted. And very quickly, we did a variation of 20 to 50% of the sum of the input parameters. And well, as expected, the 3 most influential are the ones that relate to the O&M logistics, so the charter cost, the downtime, the failure shutdown, so the energy loss per failure, and the electricity price as well, because it affects directly the revenue losses. So cost optimization here should prioritize minimizing the downtime, and here because of the failure shutdown and the vessel logistics, as said before. So to close, some key takeaways and kind of repeating some of the things I already said. So postponing maintenance interventions to months with better weather conditions is indeed, of course, the best option. Vessel logistics are the dominant driver of OPEX costs, so the optimization here is in terms of maintenance intervention, is really important. So despite the higher failure events of string inverter layouts, it did consistently outperform the central inverter one due to a lower energy downtime for the first 2 strategies, and due to lower logistics cost on the last strategy, because the repairs are shorter and use a smaller vessel with a lower charter rate. Also important that platform designs that are less sensitive to wave motions, and here if I remind you that we used 0.8 meters of wave height, of maximum wave height for repairs. So if you can increase this value, this will very highly, there's a high chance that it will increase your accessibility to site, so significantly increase the workable days offshore. Very important for sites that are far from port. And lastly, something that we didn't consider within the scope of this study, how to access the components, how to maintain them. It's definitely a very important design factor. Large components, if they are required to be replaced or even maintained, must be located for safe and efficient intervention. Otherwise, it would make them the maintenance unfeasible. And this closes my talk. So thank you for attending, and if you have any questions.
Thank you, Paul, for your presentation. Are there any questions from the audience?
Thank you. Congratulations for the study. I would love to have any guideline on DC-AC ratios, or if we should implement from the design standpoint of the site any redundancy, installing more maybe peak power or more inverters, taking into account you are saying that not replacing could be an option. And second question, I would like to understand the string inverter design, because you mentioned a string and then the transformer. If you could explain better the two design standards for sure, but the string inverter, I don't know if I catch it well.
Yeah, well, the electrical layouts were not designed by us. So this was designed by a project partner of this project. We received the components. Actually, I'm not sure if we had access to the single line diagrams or I don't think, Luis also participated in this study. So we received the number of components and the capacity and the dimensions and specs. So I cannot elaborate so much about how they are connected, but this was the specs and this was the number per farm. So unfortunately, I don't have much information on the actual electrical.
You know, on ground you have the string inverter, but also the transformer are large. You know, are bigger.
Yeah, in this case, the transformers for the string inverter ones are smaller, and I believe this was the case because they had to be small. They had to be. They had not to wait.
Maybe for the offshore application.
Exactly. So there was a reason that. So you have a much higher capacity, let's say, platform design that allows for much heavy 12-ton transformers, and then you have another one that cannot sustain those types of components. But we're trying to compare, not platform, we're trying to be platform agnostic on this exercise, but still trying to follow some of the guidelines. But yeah, sorry, I don't think I could answer.
The other point is the AC-DC ratio and how to try to extract knowledge on design to avoid or to balance how to approach the O&M, you know, with CapEx maybe.
Yeah, exactly. Well, of course, CapEx here will have a great, a very important impact on the overall economics. This is just purely OpEx related. So in the future, maybe that would be a good follow-up. Thank you.
Don't want to ask a question, and then we'll finish to move forward. Otherwise, we are going to be late, okay?
I'm from the Netherlands, so I have time. No, but very nice presentation and nice work. With similar simulations, we saw more or less the same, so that I think is good for you to know.
Great.
We also saw like a central transformer. It's not that easy to lift, so it should be on a right location. Should be easy to lift. The same counts for the string inverters. Walking around with them on a moving object, crossing platforms is also a challenge. So indeed, there's a lot to say for, and of course, distance to shore have a lot to impact on how much time you actually need to get an inverter or from the platform, and whether you choose for no replacement or replacement.
Yeah, no, totally. The workability, well, it depends a lot on what site you are and the operating limit conditions. I'm sure probably in your platform you probably have a higher access wave height that would increase slightly the workability at site, but still it's crucial in these designs, and good to hear that the results were similar. Yeah.
Thank you, Paulo. Thank you very much.
Thank you. Thank you very much.
So, and now we are going to have Gaten Bayard, that is the new technology engineer from EDF Renewables, that is going to talk to us about bird soiling impact and mitigation on floating solar PV plants.
That's it. Yeah.
Go ahead.
Yeah.
Nice presentation.
Okay, good afternoon. So let's finish with a shitty topic about bird soiling, impacts and mitigation. So I work for EDF Renewables at the New Technology Department and on floating PV since 5 years. So I will cover those topics into the presentation. So the context, I will give you a feedback on few experimentation that we have done to limit soiling and the impact, also on the module, on soil modules, and finish with some recommendations. So before that, just a little overview of EDF Group floating PV project. So we have started with a first project in 2020 in Belgium. We have one project of 20 megawatts in France. A new one will be built by the end of this year in France, a 40 megawatt project on a pumped hydro site. We have also 3 projects in Israel that have been built on irrigation reservoirs and fishing ponds. There will be 2 others normally coming into commissioning this year. And we have several projects under development, mainly in France, also in Israel. And we are looking also at a few other countries. But today I will talk about floating PV and bird soiling. So you know that floating PV is exposed to bird soiling. Birds like water, they can land easily on the panels. And also sometimes our floating PV plants, they are located nearby seaside or nearby landfills. Sometimes they are even built on fishing ponds, so fishes are there. And so many birds can come to the plants. There is already a few floating PV plants that we know have some severe soiling issues, and we have one of them at EDF Renewables. So the impacts of soiling are multiple. The main one, of course, is the financial. So you have soiling, so less production, less revenue, so it's a financial impact. Also, you will have to clean more frequently your panels, so the O&M cost will increase, also a financial impact. On the long term, there could be also some reliability issues with regard to the PV panels, because soiling could create hotspots, and those modules may degrade a bit faster than the others. And also 2 other topics related to birds. One is that if you start to clean a lot of bird feces at the same time on your plant, you might want to check that you will not degrade too much the water quality of the reservoir, depending on the use of the water that is made on the site. And also, we have seen that on some floating systems, sometimes birds can be trapped between floats, so they can enter, but they cannot exit. So if you have a site with many birds, you might want to check this aspect as well. So we want to reduce soiling, and to study this topic, we did a little experiment on this site located in the south of France. It's nearby the sea, it's nearby a landfill. And you can see all the white spots on the picture, so those are seagulls. There are many seagulls already on this site. We are considering to build a floating PV plant on this site. And so what we did is to install 2 small rafts at two locations of the site. One raft is our reference. The other raft is where we have conducted several configurations to see if there is an impact on soiling. To assess the soiling reduction, we base ourselves on pictures, so pictures of soil modules, and we use a little software just to see what is the percentage of the surface covered by soiling in comparison with the module surface. So this is a free tool that is easy to use. So we started the experiment by putting the 2 rafts in a standard configuration, so 12 degrees. That is the standard for this floating system. So as you can see, many birds, this was expected. A lot of soiling, so after 2 weeks, so we measured a covering rate of approximately 55%. We also conducted an on-site measurement with an IV test device, and we measured the loss of 33% on the power output of this module. So then we started to change the configuration on one of the islands, so to move the tilt to 20 degrees. So there is still birds on the front side of the panel, also on the top edge of the panel, but less frequentation. And after 2 weeks, the covering rate has decreased to approximately 10%. So that's better, but not so good. And during the same period, our reference at 12 degrees was at 40% covered by loss, by feces. We continued the experimentation, so we increased the tilt to 30 degrees. The good news at 30 degrees is that the birds can no longer go on the front side of the panel because they will sleep. They can still remain at the top edge, of course. But you can see already a good soiling reduction. So after 2 weeks, we have an average of 1.7% when the reference was at 45%. So that's good. The issue with 30-degree tilt is that plant capacity will reduce because you need to space your module to avoid shadings. You also have much higher wind loads, so there are some drawbacks. We continued by adding some spikes on top of the panels. So with that, the birds can no longer go on the top edge of the panel. So this is the maximum soiling reduction that we could attain during this experimentation, with a result of 1.5% when the reference was at 55%. So clearly it reduced a lot the soiling. We did IV measurement on this panel and find that there was still a power output loss of 8.5%, so still a big loss due to small droppings. Other results that we had from this experiment, one important is that rainfalls can clean the panel, so that was a good findings, but you need to have a heavy rainfall to clean the panel well. We tested also tension wires, but it didn't work at all. And we also conducted a test at 25 degrees to have, let's say, an in-between between 20 degrees and 30 degrees. We conducted this test for a longer time, for 3 months. So there have been some rain during the 3 months, but this is the result at the end, with the covering rate at around 10%, when the reference was at 60%. We have the picture at the bottom. So yes, 25 degrees is already much better than 12 degrees. Yeah. So we wanted to test laser deterrent systems, but unfortunately we couldn't test it in France because those lasers are quite powerful and they are not authorized for this use in France. Also, it's quite dangerous for human eyes. So if you consider lasers, you need to ensure that there is no people around, and also consider the reflection of the laser beam on the panels. So we played with a little laser torch that we could purchase, but it is not enough powerful to be effective. But we could confirm that there is laser beam can reflect on the module glass. So laser really need to be careful about reflection. After we tested drones, so we tested a Falcon drone. So it's a kind of plane. It's quite fast. You can automate the flight path also. So we tested it for 1 day. It was really effective. So as soon as the drone goes towards the seagulls, they are totally in panic and they leave the site immediately. The issue is that when the drone lands, 20 minutes after, all the birds are coming back on the site. But we continued, so we wanted to see if there was a long-term effect. So we tested this drone for 2 weeks with regular flights every day. We were hoping that maybe the birds will be discouraged and leave the site for good, but not. So each time they come back. So it's not working really well. And also we had 1 collision with a seagull. So this is the last image of the drone. So that clearly it's not good. So the seagull made it, but the drone fall into the water. So yeah, clearly this is a problem with the use of drones. We considered to test a system with a quadcopter drone with some kind of a vision system and artificial intelligence with a drone in a box system. So the camera will detect when the bird are on the modules, send an order to the drone to lift, to take off and to harass the bird. So this could be, in theory, a way to harass the bird 24/7 without personnel. But quadcopters maybe are not a good choice because we saw that some police quadcopters actually are being attacked by seagulls. So it's maybe not a good choice. And also in France today, the regulation do not authorize us to use fully automated drones without a human surveillance. There is also a plant at EDF Renewables in Israel. So it's located on fishing ponds and they suffer from birds. There is a lot of birds, many birds. They are on a migration corridor. They also have dust issues on this site. They could confirm that heavy rains clean their panel, but still they have some impact that is quite important on the performance of the plant. So they tried several means to reduce it. So they were able to test the laser that we could not test in France. So they find it a bit effective, but not on all kinds of birds. So for this team in Israel, this cannot be the only mean to deter birds on a site. They tested also ultrasound speakers, clearly not effective, but this was expected as well. They considered the use of anti-soiling product. So it's a manual application that you have to renew every few months. Finally, they choose not to do it because of concern on the acceptability of putting chemicals in water. I think at EDF Renewables we don't really like this idea, even though the supplier says that it's not, it won't pollute water. Probably it's not the best option. They tested also drone equipped with cleaning devices with water jets. So it's drones that will locate the droppings and spot water directly on the dropping to clean it. They found that it worked on small scale, but it was not a solution that is efficient enough for a large plant with many droppings, etc. But the solution may be improved in the future, maybe. They tested also the well-known crawling robot. So cleaning is working well. The issue is that the floating system that they have on this site is quite flexible, and so the robot has difficulties to pass from one module to another. So sometimes people need to be there to lift and help the robot that is quite heavy. So the solution works, but not on this kind of floating system, or maybe the robot needs to be adapted to work better. Another system that they tested is the use of water sprays. So the purpose is not to scare the bird, but to try to dissolve the soiling during the night. So the principle is simple. It works. The only issue is that it's quite expensive. There is a lot of tubes everywhere on the plant. You have to have a filtration unit. There is some O&M cost associated to the system. And maybe with time there could be some mineral deposits on the glass of the panels if you are using this too often. But the solution is working, so they are still testing it at the moment. Yeah, so I talk about the soiling. So now what is the impact of the soiling on the module? So to better understand that, we have conducted some tests at EDF R&D laboratory. So they have a flasher, industrial flasher. And we made some tests with the module, and yes, we tried to create artificial soiling. We had some interesting conclusion, I think. So the first one is that opacity of the dropping has a huge importance. And you can see that with those two stickers. One sticker is with thick paper, almost opaque. The other one is a thin paper, so some light will pass through, even if it's still white. But the power loss is quite different from minus 0.6 and minus 6 and minus 0.4. Yeah, so this is the first conclusion. Another conclusion is that the position of the droppings also has an impact on the power loss and the coverage rate at cell level rather than at module level. So you can see that on the top two pictures. So same coverage of by soiling, but different position, and you can almost double your production loss. So this is due to the electrical architecture of the PV panel, the way that the cells are stringed inside the panel. You can see also that if you have a large coverage of 1/2 cells on the panel, you can decrease your module power by more than 40%. So it can go really fast if you really opacify a small surface. So we tried to see if there was a difference between a soiling configuration with landscape or portrait orientation. We found that it was slightly better with portrait orientation, still due to the electrical architecture of the panel. And after we played with a mixture, we wanted to recreate a bit the consistency of actual bird soiling. So it was a mixture of water, egg white, and floor. And so we added progressively some soiling on the panel, and each time we flashed with the flasher. What we found is that the power loss, in fact, is not linear. It grows faster. It has a kind of exponential curve. It's not linear. So that was a good findings as well. So with that, we try to do a little model to estimate for our future floating PV project what could be the bird soiling losses. So we developed a little methodology that is quite simple, in fact, but so the first step is to estimate what is the current bird population on the site. So you will need probably ornithologists to guide you through that and to know what kind of birds, what kind of species, what is their frequentation per month. Is there a risk that new birds will come to the site after the plant is built? So with that, you can calculate a theoretical soil surface per day. After, you need to assume what is the percentage of droppings that will actually be on the panel of your plant. So that will depend on the tilt. It will depend on whether you have spikes on top, if you have deterrent measure on the site. So you have to make some assumptions, and you can calculate, estimate what will be the coverage on your module per day for every day of the year. After, you need to make assumption on your cleaning strategy. No cleaning, one every 3 months, whatever. Very important, you need to document what are the rainfalls on the site, if possible on several years. Make some assumptions on what will be the cleaning effect of the rain, depending on the quantity that it rains. It will depend also on the module tilt. And so with that, you can be able to estimate what will be the actual soiling coverage on your modules for every day of the year. So for instance, on this graph, you can see a big spike in summer because there is more birds but less rainfalls. So it will increase a lot. Maybe it's a good time to make some cleaning operation on this site. And finally, you need to have this assumption of what is your production loss depending of your soiling coverage. Okay, so this is maybe difficult to assess, but you need that to actually after to make your average calculation on soiling losses per month and per year. So it's not precise because there is a lot of assumptions. It will depend on bird philosophy that you cannot predict. But it's still interesting because you can assess what is the gradation of risk. You can make several scenarios, maybe a low scenario, a high scenario, to see what is the range of your bird losses that you can expect. So to finish, some recommendations. So obviously, the first one is to document bird presence before you make the project, during the design phase. Document what are the rainfalls, very important, and try to estimate what could be your soiling losses. And if you think there is a risk of high soiling losses, then you need to consider mitigation measures. So this is a catalog. So you may have a higher tilt on your panels. You may put spikes on top of the modules. If possible, you might put your module in portrait mode. It's better also to use string inverters because soiling won't be uniform on the plant. In general, there is more soiling at the periphery of the island or on located position on the island. So better to have string inverters. or even PV optimizers can help you with all these mismatches. You need to define your cleaning strategy, and depending on your cleaning strategy, if you may need to have floating system that is adapted to the cleaning strategy, so something that on which maybe the robots can circulate easily, or people. This is quite important. And few next possible steps on the topics. So I think it would be good to have autonomous, automated cleaning systems. Not talking about robots with somebody with a joystick, and really something automatic. It would be nice. I think maybe on deterrent solution, there could be something to be developed with drones, artificial intelligence. Probably something can be worked. Also to work still to refine those losses estimations that are not well known today. So maybe by sharing some data between developers. Also working with ornithologists maybe to refine this methodology of assessment. And finally to have PV modules that will be less sensible to soiling. So it will be the case with the new generation of TOPCon and heterojunction module that will have back contact. So this will come in a few months and maybe next year. And those modules are less sensible to located soiling. In fact, they avoid the hotspot effects, etc. So it will be a plus for us on floating PV plants. Yeah, so thank you for your attention. I finished my presentation.
Thank you, Gerhard, for your presentation. Any questions from the audience?
One idea I've heard for one of my Thames Water sites was the idea of setting up a wetlands nearby, so the birds just don't go towards the panel and have a preferred landing spot. Did you do any monitoring around? Did you do any monitoring on areas around the lake as well to see if there was maybe more birds going there, or did you just focus on the panels and I guess just do you have any inputs on that idea?
Yeah, so on this experimentation that I showed, we are really close to a landfill. So we know exactly where the birds are feeding, etc. I think even if we put another island that will be dedicated to birds, probably it will not solve the issue on this site. But maybe on other sites, this could be something to test. Yes. Yeah.
Yeah, I'm quite astonished over these things, that your results on wires. I know that works in the marine industry. In many cases, it's very effective. And that's something that I proposed a couple of years ago, I think, on this event here.
Yeah.
But I need to talk to you separately because we're closing up here. But we need to look at that application, how you did that, because I know it's effective.
Okay, but yeah. I'm all ears to talk about this. Maybe the configuration of the wire was not good, but we saw that sometime in landfills they put some wires to avoid the bird population to grow. It seems that it is effective, but what we've done was not effective. Maybe it can be do another way. After having a lot of wires on the floating PV plant, maybe with some inconvenience for maintenance, etc. Might not be easy. Yeah.
I don't resist to make a question also. Did you have any idea of the number of birds previously to the installation? Meaning, are they invaders after the plant being installed, or they lived already there? That is, let's say, it's quite a kind of question, like being the photovoltaic plant being attractive for them to live there, let's say, as an invader, let's say.
Okay, so on this side, they are clearly already there. That's why we have done the experimentation on this site. But we know that there have been some cases of plants that have been built in some areas where they didn't know that there will be a lot of birds, and birds are there. Also, sometimes there is some birds are migrating, so they might not be there when you look, but a few months after, there will be a colony. So you need to look at this as well.
No more questions?
No.
Yes, thank you very much.
Thank you.
So I believe that I'm the distance between your living and staying, so I'm going to be quite short anyway. First of all, big thank you very much for those 2 days, 2 days and a half, let's say that way. It has been a very good time, and I believe that it was more than a very good time. It was a very good sharing of knowledge in several aspects. And just to remember a little bit of what we had in those 2 days, we started to speak about strategies and market development and trends on our industry, and that is quite important. We revised or passed by several markets, namely in Europe. We spoke about permitting and we spoke about environment. And why did I put them together? Because they are really big challenges for us. In both cases, we need to have more studies, we need data, but we need also to make compatible different uses of water, and we have to take in consideration the water quality. We saw that yesterday and we saw that today. Floating solar systems can contribute for the water quality on a certain way, or if not directly to contribute to the improvement of the water quality, at least to mitigate the water quality that has sometimes there are always some problems over there. Anyway, it's an environmental aspect that should be studied and that should be taken in consideration and with more data. We passed by different technologies, different systems, and differentiation between inland and offshore. There are two different worlds, let's say that way, and we have to take them as from the same family, but they are not exactly the same people. Okay, so it's a quite interesting situation that we have to take in consideration. They have different needs, they have different perspectives, and inclusively we spoke also about anchoring systems, about anchors, and there is a some differentiation between them because needs are different. We navigated also in project simulation requirements. We navigate in standards, let's say new developments about standards and good practices, let's say that way. And we spoke also about CapEx, cost reduction, bankability, maintenance, losses, OpEx on a certain way, and something very important also that we have to consider, that each site has their own specificities, so we have to take each project as a project. We cannot take a one-size-fits-all. So, hope to see you next year. Enjoy the evening. Let's continue in touch and continue to see things. Thank you very, very much for your presence, and thank you very much for being there.
And thanks to everyone who stayed this long, and especially our sponsors. And yeah, looking forward to seeing you again.
Thank you, Milagro.